इसी को फ्री कर दो ना, सेशन को फ्री कर दो। हम करने का नहीं यार, नहीं यार, वो सही नहीं लगता।
Hello, check.
सबको बोलो इधर आने के लिए बोलो। ठीक। सुनो, इसके पहले जैसे ही लाइट बैक से गेस्ट यहाँ पे बैठे जैसे ही गेस्ट
Check, check. In the beginning, there was neither existence nor non-existence. There was neither realm of space nor the sky beyond. What state, where, and in whose protection? These timeless verses from Nasdi Suktam, Rigveda 10.129, the celebrated hymn of creation, remind us that the quest for knowledge began long before humanity named it science. The spirit of inquiry, the courage to ask profound questions, and the desire to understand the nature of matter, energy, and existence itself. These form the very foundation of scientific pursuits. Just as the ancient seers contemplated the mysteries of creation, today we gather to explore the fascinating world of liquid crystals, material that exists in a state in between, neither fully ordered nor fully disordered, mirroring the very essence of hymn that speaks of a universe emerging from an indeterminate states. A very good morning to all the distinguished dignitaries, esteemed speakers, researchers, delegates, and participants present here today. On behalf of the organizing committee of the 32nd National Conference on Liquid Crystal NCLC 2025, I, Samarth Misra, research scholar, Department of Physics, BITS Pilani campus, extend a warm and heartfelt welcome to all of you. NCLC, organized under the aegis of Indian Liquid Crystal Societies, is India's premise annual platform that brings together leading scientists, academicians, research scholars, and industry professionals working in the field of liquid crystals, soft matters, and emerging advanced materials. This year, BITS Pilani is honored to host 32nd edition of this prestigious conference. Today, we gather to celebrate scientific excellence, exchange pioneering ideas, and strengthen collaborations in the vibrant research domain. Now, I invite our honorable chief guest, Professor N.V.M. Rao, Dean Administration, BITS Pilani campus, followed by guest of honor, Professor P.C. Pancharia, Director, CSR Siri, Pilani, followed by guest of honor, Professor K. Suresh, former Director, Center for Nano and Soft Matter Sciences since Bangalore, and former Professor, Raman Research Institute, former President, Indian Liquid Crystal Society, accompanied with Professor Ravinder, President, Indian Liquid Crystal Societies, and Professor, University of Allahabad, followed by Professor Rajkumar Gupta, Conference Convener, and Professor, Department of Physics, and Associate Dean, GCIR, BITS Pilani campus, and Professor Manjula Devi, Head, Department of Physics, BITS Pilani campus, to come on the dais. As our esteemed dignitaries take their seats on the dais, it's now time to formally commence this exciting event. Let's begin by embracing a divine aura. I request our chief guests on the dais and distinguished guests to kindly join us for the lighting of the lamp, symbolizing the illumination of knowledge and the warmth of collective wisdom. It's customary in this part of the world to commence any auspicious occasion with divine blessings. The light is our testimony to the positive energy radiating throughout this event. Thank you, sir and ma'am. Goddess Saraswati is revered as embodiment of wisdom, knowledge, and learning. Invoking her blessings is time-honored tradition, especially in academic and intellectual gathering. Through Saraswati Vandana, we seek her divine grace to guide us in our pursuit of knowledge and innovations, ensuring the success of this conference. Now, I would like to request Mayuri, research scholar from Department of Physics, and Shreya, undergraduate student, BITS Pilani campus, to recite the Saraswati Vandana.
दो मुझे आशीष तुम माँ, दो मुझे आशीष तुम माँ, गा सकूं नवगीत मैं माँ, गा सकूं नवगीत मैं माँ। दो मुझे आशीष तुम माँ, वीणा की झनकार छेड़ो, स्वरों में अमृत उड़ेलो, तार दो नववल्लरी माँ, तार दो नववल्लरी माँ, गा सकूं नवगीत मैं माँ, गा सकूं नवगीत मैं माँ। दो मुझे आशीष तुम माँ।
Thank you, Mayuri and Shreya, for your soulful and mesmerizing performance. It is an absolute honor to have our distinguished dignitaries on the dais. Their inspiring journeys and unwavering dedication motivate us all. Let's give a warm round of applause as we present bouquet of flower as a token of our appreciation to our esteemed guest. Now, I request Jyoti to present flower bouquet to our chief guest, Professor NBM Rao. Next, I request Mayuri to present flower bouquet to guest of honor, Professor PC Pancharia. Then, I request Jyoti to present flower bouquet to our guest of honor, Professor K. Suresh. Following to that, I request person to present flower bouquet to Professor Ravindra. Following to that, I request Jyoti to present flower bouquet to Professor Rajkumar Gupta. Next, I request Mayuri to present flower bouquet to Professor Manjula Devi V. Thank you, everyone. Now, I request Professor Rajkumar Gupta, convener NCLC 2025, Department of Physics, and Associate Dean GCIR BITS Pilani campus to deliver the welcome address.
Professor N.B. Rao, our chief guest, Dean Administration, BITS Pilani campus. Professor P.C. Pancharia, Director, CD Pilani. Professor Ravindra Dhar, President, ILCS. Professor K. Suresh, Professor Manjula Devi, Head of the Department, BITS Pilani campus. Distinguished guest, participants, our faculty colleagues and students. A very warm welcome to all of you. It is my great privilege to welcome you all to the 32nd National Conference on Liquid Crystals organized by the Department of Physics, BITS Pilani campus under the aegis of Indian Liquid Crystal Society. NCLC has a rich legacy, and over the decade, it has grown into the most important national platform for the liquid crystal and soft matter community. It brings together researchers, technologists, and students from across the country and abroad, providing vibrant space for exchanging ideas, sharing discoveries, and shaping future of this dynamic field. We are delighted to host more than 120 participants, including several international delegates, like from Hong Kong, France, Germany, Ireland, and USA. It is an honor for us to have among us our chief guest, Professor NVM Rao, Dean Administration, BITS Pilani. I extend my special welcome to our guest of honor, Professor K. Suresh, Raman Research Institute, Bengaluru, and Professor Ravindra Dhar from University of Allahabad, President of ILCS, and Professor Manjula Devi, Head of the Physics Department, BITS Pilani campus. Your presence greatly enhanced the significance of this event. Thank you, sir. This year, NCLC is unique in many ways. Liquid crystal continued to be the foundation of display technologies, but the field today extends far beyond the classical LCDs. LC research now spans sensors, photonics, metamaterial, biointerfaces, responsive soft material, and energy-related applications. The expanding scientific and technological scope is reflected in the diverse theme and invited talks featured in NCLC 2025. We are also delighted to have successfully organized the Indian Display Workshop yesterday at Siri Pilani, supported by the Society of Information Display. The workshop showcased the strong synergy between industry and academia, highlighting India's emerging opportunity in display science and technology. This pre-conference event set a strong foundation for the discussion that will follow over the next 3 days. At BITS Pilani, the research and innovation form a key pillar to our institutional mission. We are more than 400 crores ongoing project and major national program which we are executing at present, such as Sathi, PERS, DBT Builder, and National Mission for Cyber Physical Systems. The institute is deeply invested in supporting the scientific progress across the discipline. Hosting NCLC 2025 aligned with the vision for advancing curiosity-driven research while fostering collaborative network in the national and scientific ecosystem. I take this opportunity to express my gratitude to Indian Liquid Crystal Society, particularly its leadership, for entrusting BITS Pilani with the responsibility of hosting this prestigious conference here. I also thank our invited speakers, session chair, participating institutions, our sponsors, including corporate partners and scientific organizations, and every member of the organizing and advisory committee for their wholehearted support. Finally, I extend my warm appreciation to the young researchers and students whose enthusiasm formed the heart of this conference. I once again welcome you all to the BITS Pilani and wish you a scientifically stimulating, productive, memorable NCLC 2025. Thank you very much.
Thank you, sir, for your kind words. It's our honor to have Professor Ravindra, President, Indian Liquid Crystal Society, and Professor, University of Allahabad, with us. I kindly request Professor Dhar to embrace us with his profound wisdom by addressing this gathering.
Thank you very much. Distinguished guests at dais, Dr. NVM Rao, Dean Administration, BITS Pilani, Dr. PC Pancharia, Director, Siri Pilani, Professor K. Suresh, former Director, Center for Nanosciences, Bangalore, former President, and our dear senior colleague who always advise us on several occasions, Professor Rajkumar Gupta, convener of this conference, who kindly agreed to my request, our request rather, to organize this 32nd conference here in beautiful campus of BITS Pilani. Professor Manjula Devi, head of the physics department. She is ably supporting to Professor Rajkumar Gupta. Our foreign delegates, I can see, I am very happy that Professor Christian Nitz have been able to make it to visit India this time. We have met on several occasions in Poland and several other conferences, but I am happy to see here you, sir. Professor Abhishek Srivastava, Professor Dharmendra Singh, Professor Viz, uh, despite all the age factors, he is beating the age and still join our conferences whenever occasion comes. Members of the Indian Liquid Crystal Society, Professor El Magad, Professor Sandeep Kumar, our fellow speakers in this conference, and above all, our young workers in this area who are future of the liquid crystal research in India and also in abroad, like Abhishek, Dharmendra. So you have to represent, of course, here Pankaj ji is here, Malik Saab is here, I can see. It is difficult to take all the names. It will take a lot of time. I have to tell something about Indian Liquid Crystal Society. Indian Liquid Crystal Society was established way back in 1992 by Professor S. Chandrasekhar. That was very early stage. There were very few centers in India who were working on the liquid crystals. Those were the era of liquid crystal when we had only black and white displays in watches and all these things. And by the end of last century, we had got vivid, fascinating displays from liquid crystal displays. After that, I will not say that only with the effort of Liquid Crystal Society, but of course, number of centers in India grew. And there are now a good number of centers in the India who are working on the liquid crystals and different areas. And I'm happy that this time Manjula Devi told me that we have more than 120 participants in this conference. That is good number for the field, narrow field like liquid crystal. By the society, we had been organizing the conferences throughout the India. As I told, first was held in Mysore University, Mysore in 1993. And then thereafter, we have organized conferences from the northern part, Jammu, to southern part, Trivandrum, from remote eastern part, Arunachal Pradesh, Itanagar, to Mumbai, and so many centers in whole India. And now most of the prominent educational center in India have organized this Indian Liquid Crystal Conference. And there are people working in this area. Now society has a strength of more than 500 members. And liquid crystal research centers have also grown in number. Common belief of the people is that now liquid crystal research is saturated because they see only the displays. Of course, in displays, we have achieved too much. We have, of course, from common people point of view, very good displays. But even in displays, maybe I hope Dr. Abhishek Srivastava has discussed all these things. When I go to market, I see that the frame per second for these displays is limited to only 200 and 250 frames per second. So that way it is very small. For video applications, for high frequency applications, still we need this frame rate per second to large number, maybe 1,000, maybe few thousands. So that way we need to discover microsecond switching materials. Pneumatic liquid crystal materials have switching time of only of the order of 1 or 2 milliseconds. So we need microsecond switching materials, and that way antiferroelectric liquid crystals are important and people are working in this area. Beside displays, liquid crystal research is now expanding in other areas, and those are the areas that are very important now beyond displays. And they are light modulators, LC lenses, photoresponsive liquid crystals, including photovoltaics, communication, soft robotics, and so on. Now there are enough scope to work in the area of liquid crystal for bio applications, such as drug delivery, cancer detection, artificial organs, etc. In this direction, there is enough scope to work on lyotropics. In fact, according to some studies, I was reading in some magazine that liquid crystal industry is next to the semiconductor industry. So that way we have given too much to the society. And still we have large number of scopes to do. From the end of Indian Liquid Crystal Society, we have already decided to support young researchers for their experimental work. This was decided in the Bangalore, that we will support financially to research scholars or young workers to go to other places for doing their experimental work and all these things. Society is giving national awards in 5 categories to recognize the contributions of the senior and young research workers. These awards are, the topmost award is Professor S. Chandrasekhar Memorial Lecture Award, and Lifetime Achievement Award. They are given to the people who are the age above 60 years. And then there are gold medal awards for the workers who are working in the age group of 50 years to 60 years, and then silver and bronze awards. I hope in the year to come, our liquid crystal community will further grow and our research activities will be further intensified. I am thankful to Professor Rajkumar Gupta, Professor Manjula Devi for hosting this year's National Liquid Crystal Conference. I wish that this 32nd National Liquid Crystal Conference will be great success. Hope your stay will be academically as well as socially very fruitful, and you will have nice memories to carry on from BITS Pilani. Thank you very much.
Thank you, Professor Dhar, for your inspiring words. I would now like to invite our chief guest, Professor N.B.M. Rao, Dean Administration, BITS Pilani, Pilani Campus, to address the gathering.
So very good morning. Good morning to all of you. My special morning to Dr. Pancharia, Director, Siri Pilani, Dr. K.S. Suresh, Raman Research Institute, Dr. Ravinder Dhar, President of Indian Liquid Crystal Society, Professor Rajkumar Gupta, our Associate Dean and also convener for today's event, Professor Manjula Devi, Head of the Department Physics. So, Professor Ravinder very clearly given the details of the society and noted that lot many activities are happening, and the young research scholars who are not part of the society kindly make it a habit to join this society and have a great time with the learning aspects are concerned from the experts who are there in the field. So for me, it's a true honor to be at 32nd National Conference on Liquid Crystals, because I am not a physicist. I'm from economics and finance. When I'm looking at the society's activities and all, truly inspired and very much feel that I must appreciate the kind of things what the ICLS is doing. This conference has always been a special place for us, because any conference, if you look at, it's a place where ideas travel freely, where all the curiosity is celebrated, and most importantly, the next generation of scientific breakthroughs quite begins in that. Especially the liquid crystals occupy a remarkable space between order and freedom in the state which is neither fully solid nor fully liquid. So the French physicist and also the father of liquid crystal science beautifully said, the boundary between order and disorder is where the most interesting physics exists. So this area, especially the liquid crystals, are a wonderful reminder that nature always loves to surprise us. They don't fit neatly into one category. If they fit into one category, we are one-sided. So they live gracefully between the two states, not fully liquid and not fully solid, yet capable of transforming the world around us. As someone has beautifully said, innovation often begins where definitions end. And that is exactly the spirit of this field, which I noticed. So from the screens we use every day to advanced optical devices, from smart sensors to new biomedical possibilities, liquid crystal science keep proving one truth, that is, nature hides its finest ideas in the most unexpected places. So in many ways, science itself looks like a liquid crystal because it is dynamic and importantly, it is adaptive and full of potential. So the famous physicist said that there is a plenty of room at the bottom. Mr. Richard Feynman rightly noted, there is a plenty of room at the bottom. But when I look at this particular science, the case of liquid crystal, there is a plenty of room in between as well. So a conference like this is not just an academic event. Most importantly, it is a conference of shared purpose. And I deeply appreciate by looking at the distinguished delegates and the research scientists who are gathered here, when great minds meet, the future takes a shape. So looking up the kind of experience what people are carrying here, the wisdom, and most importantly, the youthful energy, I have no doubt that the future in this field is remarkable in the hands of younger generation if they make use of that expertise. My special advice to young researchers, I want to leave you with a few thoughts. 3 things. Stay curious, because curiosity is the spark that lights every discovery. Stay patient, because sometimes outcomes will not be that easy, because science rewards those who persevere. And stay bold, because the future belongs to those who dare to question the obvious. And always remember that every discovery begins with someone who refuses to stop observing. So let that be your guiding light, and listen to all the lectures and meet the people who are experts in the field who are here today. And I congratulate the Department of Physics and the entire organizing team for bringing together such a vibrant and inspiring community, and all your efforts to create the environment where ideas will definitely flourish, and most importantly, the collaborations will grow. So as we inaugurate the 32nd National Conference on Liquid Crystal, I'm sure and confident that over these 2 days, the discussions, the collaborations, and the discoveries made here will definitely illuminate the new directions and inspire deeper inquiry. So thank you for providing the opportunity, and I welcome once again the guests who come from outside. It's a beautiful place. Please spend some time and meet our young researchers, visit the labs, and advise us what is the best that can be possible to improve from your side, and have a great experience at BITS Pilani. Thank you very much for the opportunity once again. Thank you for patiently listening.
Thank you, Professor Rao. We are privileged to have your enlightening word of wisdom. Without a further ado, let us welcome our guest of honor, Professor P.C. Pancharia, Director CSR Series, to the podium to enlighten us with his valuable thoughts and experiences. Please, sir.
Good morning, all. Respected Professor Rao, Professor Suresh, Professor Ravinder, Professor Gupta and Mrs. Manjula Gupta, all the invited guests, researchers, invited speakers, students from BITS, from outside other institutes, media. First of all, I thank Professor Gupta, BITS Pilani, for inviting me in this conference. though I'm not from the field, but as discussed with Professor Gupta, the behavior of particles and group of particles, like particles are not ordered or disordered in between, but the flow is liquid. So we are at position of a national character. We can see our national character is like that. We are not fully ordered, we are not fully disordered, but our behavior is like a liquid. So we have that ultimate result is we know it is like a crystal. We have a very crystal clear vision. 2047 is a Viksit Bharat, and in this Viksit Bharat, every Indian, every citizen of this nation has a role to play. This such conference, it's not a semiconductor conference, but it's near to semiconductors. But we need to play our roles, and such conference also means give a good contribution to the nation. As far as the research is concerned, we are doing great, but now we need an ecosystem, a manufacturing ecosystem in India for a Viksit Bharat 2047. So I request all the experts, researchers to look and thought into this, how we can make a great India by setting a manufacturing facility in India, especially in liquid crystals. So then I think this conference and assembly discussions, like the next future course of discourse, it should be based on the how we can have a translation research, how we can have a products and a manufacturing setup in India. So thank you very much for inviting me in this conference. I hope you will think on the manufacturing setup in India. Thank you once again, Professor Gupta, for inviting me. Thank you.
Thank you, Professor Pancharia, for your word of wisdom. Now, I kindly welcome our guest of honor, Professor K. Suresh, to put to the podium to enlighten us with valuable thoughts, experiences. Please, sir.
Good morning. Chief guest of today's function, Professor N.V.M. Rao, Professor Pancharia, Professor Ravindra Dhar, Professor Rajkumar Gupta, Professor Manjula Devi, all the distinguished guests in the audience, delegates, faculty, friends. It is my great pleasure to, first of all, to come to this conference and also to participate in this function. So I'm very thankful to Professor Rajkumar Gupta as well as Professor Manjula Devi, who have invited me here to this function. Bits, I would like to share a little bit because our chief guest, who is from BITS Pilani, didn't say that. The greatness of BITS Pilani to the audience, it's slightly different, but let me share because I really appreciate it and so on and so forth. It's really nice that this 32nd National Conference on Liquid Crystals is being held in BITS Pilani, an institute which is well known internationally for higher education in engineering and science. It started sometime in 1964 or so, but since then, this particular campus has evolved. Now it has spread out to other campuses, Hyderabad, Dubai, Bombay, and they are going to have one in Goa. Goa already they have, and Amravati, and so on and so forth. So the management of this BITS Pilani from the very beginning have a great vision. And that is how they have built up this whole place. And the vice chancellors who were here, they also had a great visions and so on and so forth. So they are able to produce some extraordinary technology people, scientists all over the world who are spread over all over the Union. I'll just give you a sample of few people, you see, whom I am sort of familiar. One is Sri Prithviraj Chauhan, who was the Chief Minister of Maharashtra and later the Minister of Science and Technology in the central government. He is from BITS Pilani. He did his BE from BITS Pilani and then did his MS from University of California, Berkeley, in mechanical engineering. There is, as a Minister of Science and Technology, he is also the head of all these DST institutes and so on and so forth. And as the director of CNS earlier, we had occasion to meet him many times. Once in 6 months or so, we had a meeting. I never felt that he's a politician, minister, etc. He was a down-to-earth technical person. You know, his training from BITS Pilani. The other person is a very well-known biochemist, Professor Govardhan Mehta, who was the director of the prestigious institute, Indian Institute of Science, again from BITS Pilani. And then we have Professor D. Balasubramaniam. He is a biochemist and sort of physician and so on and so forth, who was the director of CCMB Hyderabad, Center for Cellular and Molecular Biology, well known for his research and so on, and for his some important contribution regarding vision and eye research and so on and so forth, again from BITS Pilani. And right now, we have Professor Govinda Rangarajan, who is the director of Indian Institute of Science, Bangalore, a mathematician. See the diversity of BITS Pilani, how they have produced different fields, different areas, and so on. And Professor Rangarajan has a background, mathematics background. Normally, in IAC, etc., they have directors from the engineering background, but he's an exception. So he's the director with the math. So all these people are products of BITS Pilani. Now, this is all because, as I said, the vision of the management, the vice chancellors, and so on, so everybody has sort of contributed to this rise of this institute, you see, and made it to a premier institute in India and well-known institute all over the world. And even the present vice chancellor, Professor Ram Gopal Rao, very eminent person. Formerly, he was the director of IIT Delhi, and before that, he was in IIT Bombay. Now he is the vice chancellor of BITS, all the centers and so on and so forth. Not only is he a well-known engineer and scientist and so on, he has done a lot of things to popularize science. Every now and then he writes articles in newspapers conveying some of the problems that we scientists are facing. I would like to share some of them with you, his views, which are very, very important. I keep reading once in a while, and many things he has written, very thought-provoking, very profound views, and so on. But let me share a few other. One is regarding an issue which bothers all of us. How to evaluate a scientist? How do you evaluate a scientist? Citation index. You see? And then we have this H index. Then for the universities, NAC index. All kind of stuff. Good. There should be some evaluation. But at the same time, these are, in many cases, these are not done in a proper way, in an ethical way. Somehow they want to have a higher index. Somehow they want a H index. And you see, so there are many flaws. So his view is, okay, you have some evaluation, great, but don't take it very, very seriously. There may be some scientists who may not have any citation index at all, a mathematician, like Ramanujan. You ask what is the citation index those days, he would say 0, but later on he became a legend. That's a different story. Okay, therefore, his view is all this side of evaluating a scientist has to be looked in a proper way and so on and so forth. See, for example, there is a scientist who said, my H index is 100. H index is 100 means he had 100 papers, each with 100 citations. How he has done it? He has all his students, friends, everybody. Write any paper, you cite my paper. That is how it is. See, this is not a proper way of getting, like this and so on and so forth. So this is one issue. The second issue is regarding publishing of papers. We all face this problem, The very first thing, we send our papers, and then we don't know what to do, editor, and the referees, and we are under anxiety and things like that. All of us have faced. So this is a part of we scientists' life and so on. But his point is that many times the refereeing is not done properly. So the editor also have a lot of problem. Editor is one amongst us. You see, one of the senior people has become editor, chief editor, associate editors, and many of here are a part of that. They have a lot of problems. For example, an editor, when he receives a paper, he has to select the referees. And what is happening nowadays, this is what Professor Rao is writing, is when he sends these papers, most of the people are not willing to referee a paper. So he keeps sending, not available, keeps sending, not available. Many, many times it happens. And in addition to that, now there is a flaw that has taken place in this refereeing business. So this editor give a choice to the author, okay, you suggest referees. So now what happens is, when I have the choice of suggesting a referee, I create some fake referees, some email, this, etc., and suggest it to the editor. Editor, in a blind way, will send it to them, and there is a very good report and all kind of stuff, and even get published. But later on, it is found that it's a fraud. And but Professor Rao, what he says is, in the Village Journal, you see, he has said in the year 2022, in the Village Publishers, the editors found that 500 papers have been retracted because it was found that they are all frauds. In just 1 year, 2022, this is what he has written in the paper, Village Publishers, in their 11 journals, they have many, many journals, in their 11 journals, they have to retract some 500 papers. So, see, this is an enormous thing. See, we as a sincere scientist want to do some research, publish it and so on, but then there are all these fraud people also. The editor is put into lots of problems because he cannot distinguish which is a good paper, which is a genuine paper, flaw, and retracting is one business, many, many things. In fact, we have a chief editor here, Professor Abhishek Srivastava, of chief editor of SA. He was telling yesterday the same thing, how difficulty the problem of editor and so on and so forth. This is what Professor Rao has said. The other thing that he has written on article, just last Sunday, if you see Times of India Express, on 16th November, there is an article by Professor Ram Gopal Rao. This is regarding funding, science funding. We all live with science funding, right? And he, being director of a government institute, IIT Delhi, and presently in a private institute, he says this funding is again a very, very complicated thing. The thing is, many philanthropic organizations may be funding you, but you can't depend upon it. So you have to depend upon the government funding. This is also done in USA. All these Harvard, MIT, Stanford, they are getting funds from government. But now Trump is trying to stop them. You know that. The same thing in India. So we are getting funds from the government, and it is a duty of the government to support education and research. In any society, it is the government that has to look into its citizens' education as well as research, as well as medical things and so on. This is a part of that thing. So it is obliged to support research funds. How do they do that? They give grants. You see? There are so many things in India, for example. We have individual grants, departmental grants, institute grants, and so on. So what his point is, giving a grant is fine, but then it has to be accompanied by some what is called as a overhead charge. You give some funds to the institute to buy some equipment and all. Now, who will sort of maintain that instrument? Who will, some technicians? All those things are necessary. So if you give money to an institute, you should also give money overhead charges to maintain those things. You give me money, there is a FIST program, okay? So if you give money to a department, then you should sort of see whether that department can also give facility to the people. For example, I will tell you, there is a lady from IIT Patna. She made a good presentation in for a FIST program, got about 2 crores or so, and finally she got it. But she said there's no lab space for her, you see. So now the FIST committee says you install the instrument and you have to share that instrument to other people. How can she do it? Because the department is not providing her the space at all. This is the type of problem they are facing. So his point is, if you fund either to an institute or to a department or to an individual or to even to our conference, for example, you see, if you do some award, the money sanction and so on, it has to be accompanied by 20 to 30% of overhead charges for maintenance, support, organizing and so on. So, for example, our Royal Society of Chemistry, they are giving an award to this conference. They have given some 5,000 or whatever it is. But money award to the candidates is fine. But who will do this organizing and then selecting the, judges and this and that? So, sadly what has happened is, not only given some money, they have cut the TDS also. Who will get that TDS? So, this sort of thing. So, whenever there is funding, or either awards or whatever it is, it has to be matched by some supporting fund. That is what Professor Rao has said. So we are really missing him, but of course represented today by Professor Rao, M.R. Rao. And his views are really very, very nice. And that is why I just wanted to share with you and so on in this Liquid Crystal Conference. And Liquid Crystal Conference, I think Professor Dar has told you what is going on and so on and so forth. And as you know, it all started with thermotropic liquid crystals and things like that. And it has now evolved into many other fields like physics, chemistry, biology, medicine, nanoscience, nanomaterials, and all sorts of things and so on. But there is a lot of technology, as Professor Srivastava mentioned yesterday. I think he's going to give a talk also, which you'll learn. But at the same time, the trend now is going to be biologically inspired liquid crystal research. There's a lot of scope. It's too deep. There's plenty of scope for biologically inspired liquid crystal research. For example, we can do in lyotropics, membranes, monolayers, all kind of stuff. So in the next 3 days, I look forward to listen to very interesting things in all these disciplines and so on, and learn something. I'm sure you will also have very exciting, enriching conference. So all the best. Thank you very much.
Thank you, sir, for your kind word. We now invite Professor Manjula Devi, Head Department of Physics, BITS Pilani campus, the dedicated chair, conference chair, to come to the podium and address the gathering.
Very good morning to all of you. All the delegates who have come from all over the world, and all my professors, seniors. I don't want to take the name because if I start taking name, it would become a very big list for me. So I welcome all of you on behalf of the, today I know I belong to the Liquid Crystal Society, but this one is as a head of the department, I'm representing myself, particularly in this function. After that, I am also a member of this one, okay? So I invite all of you and all the young researchers my faculty colleagues from the department and all students, a very good morning to all of you. On behalf of the Department of Physics, BITS Pilani, it is my great pleasure to welcome you to the 32nd National Conference on Liquid Crystals, NCLC 2025, organized in association with the Indian Liquid Crystal Society. We are delighted to host this prestigious conference that brings together eminent scientists, researchers, and young scholars contributing to the vibrant field of liquid crystal science and technology. So, as I already told you, it is my honor to extend a warm welcome to all the delegates on the dais, as well as those who have come from all over the world, especially Christian Needs, and then Professor Jagdish Vich, now also who inspires all of us, and Professor Sandeep Kumar and Professor Ellamgat. Once again, I welcome you all. NCLC 2025 will feature invited lectures along with oral and poster presentations from participants across the country. The scientific sessions will showcase recent advances in liquid crystal materials, soft matter physics, novel phases, emerging applications and device technologies, continuing the conference tradition of fostering collaboration and inspiring future research directions. So the department, our department, Department of Physics at BITS Pilani campus, when Pilani campus, as the Pilani campus got established in 1964, so we have just completed our Diamond Jubilee just last year. So Department of Physics also is, as a department, is existing from that time. So this department is recognized as for its excellence in physics education and research, with 23 faculty currently working across diverse thrust areas, including soft condensed matter and liquid crystal physics, condensed matter physics, biophysics, high energy physics, and astrophysics. The department remains committed to advancing scientific understanding and innovation. The department has benefited significantly from DST FIS support. From the recent one, what we received was 2018 to 23, which has enabled the development of advanced research facilities, such as a high-resolution, temperature-dependent XRD system, thin-film characterization tools, and a sputtering unit. In the past 5 years, over more than 16 sponsored projects worth more than 6 crores have been completed by our department colleagues or as a department. And we currently are having many ongoing projects, more than 10, worth 2 crores. More than 2 crores, continue to strengthen our research ecosystem. One beauty of our department, if I want to say, there are more than 55 research scholars, more than half of them, almost more than 30 students are female students. Today, I really want to say that we actually are so inclusive. So, which reflects the commitment to the diversity and inclusion. Our faculty have collectively published more than 200 research papers in the last 5 years in reputed international journals, contributing to meaningfully to the global scientific community. So as we gather here today, we look forward for very stimulating research sessions and oral presentations and poster presentations. So I wish you all a very fruitful, and I want you to have a healthy stay also, because the weather may be slightly different. You have come from all over the India. So slightly, some of you might feel cold, but I hope that we'll be able to provide you a good facilities, especially in our department. Professor Naveen Singh, who is actually in charge of the Associate Dean of SWD, he is also part of the local organization committee. He is taking care of these things. So once again, I welcome you all on behalf of the Department of Physics.
Now I request Professor Dhar to address.
I missed to name one important participant in this conference. And she is none other than Mrs. Navita, better half of Professor Sandeep Kumar. She has been very regular participant in our conferences in India as well as abroad. And she has learned so much of liquid crystals. Now, your small problems she can solve if Professor Sandeep Kumar is not present. So we welcome you, ma'am, that you have been companion to our conferences in India as well as abroad. Thank you very much.
Yes, please.
Please come over to the dais. Give me a moment. Just a minute.
Ladies and gentlemen, it's our privilege to unveil the abstract book, encapsulating the essence of our conference and the extraordinary contribution of our distinguished participants. I would like to request our chief guest and other dignitaries to launch the abstract book of 32nd National Conference on Liquid Crystal NCLC 2025. Thank you, everyone. It is my pleasure to invite Prasun Parik to the podium to deliver the expression of gratitude.
Good morning to everyone present here. On the behalf of the organizing committee of 32nd National Conference of Liquid Crystals, it is my honor to present the vote of thanks. We take this opportunity to thank our Vice Chancellor, Professor V. Ramgopal Rao, and the Director of BITS Pilani Campus, Professor Sudhir Kumar Barai, for their continuous support and encouragement. The vision and the leadership have played a crucial role in enabling us to host this prestigious conference, and we remain deeply grateful for their guidance. I would like to extend a gratitude to all the deans and the associate deans of the various divisions for their coordination and cooperation, which have significantly contributed to the smooth planning and execution of this event. We truly value your support. A special acknowledgement goes to CSR Siri Pilani for co-hosting the pre-conference workshop. We are grateful for your collaboration, hospitality, and the excellent arrangements made for the workshop. Your contribution added significant value to this year's conference. I extend our heartfelt gratitude to our chief guest, Professor N.V. Rao, Dean Administration, BITS Pilani, for taking time from your busy schedule to be with us today and for sharing such thoughtful and motivating insights. We are truly grateful for your presence. I would also like to express a sincere thanks to our guest of honor, Professor P.C. Pancharia, Director, CSR Siri Pilani, and Professor K.A. Suresh, former Director, Center for Nanosciences and Soft Matter Sciences, Bangalore, and former President of ILCS. Your presence, wisdom, and encouragement truly enriched this inaugural session. A heartfelt thanks to Professor Ravinder Dhar, President of the Indian Liquid Crystal Society, for his continued guidance and for sharing his vision for the ILCS community. We are truly grateful for your steady leadership. A special thanks to Professor Rajkumar Gupta, convener of the NCLC 2025, and Professor Manjula Devi V, head of the Department of Physics, BITS Pilani. Their guidance, constant support, and tireless efforts have shaped every part of this conference and made this day possible. To all our invited speakers, researchers, delegates, faculty members, and students from across the country, thank you for being here with us today. Your participation and enthusiasm are what give this conference its strength and purpose. NCLC has always been a platform to share ideas, foster collaborations, and celebrate the evolving world of liquid crystals, and your presence reinforces this spirit. I would also like to thank our organizing team, including the media and the website management team, the reprography department, the physics office in charge, and the volunteers for your behind the scene efforts. Thank you all once again for your presence, support, and enthusiasm. Thank you.
With that, we conclude the inaugural ceremony of 32nd National Conference on Liquid Crystals, NCLC 2025. We extend our heartfelt gratitude to all dignitaries, speakers, delegates, volunteers, and participants for their valuable presence and support. Now, you all are requested to join us for high tea and the group photograph, which will be followed by the first technical session at 10:45 a.m. I request all the participants to come front for the group photograph, then we can go outside to take another photograph.
वो दे दिए ऑलरेडी बैन इसको तो लिखा है। एक काम ये कर लो, इस सारे अगले सेशन का कौन सा है?
Welcome back, everyone, after a tea break. Now we will begin with the first session. So this session will be chaired by Professor Ravinder, President ILCS and Professor University of Allahabad. I welcome you, sir.
Good morning, friends. I am happy that I have to chair this morning, first session, where we have three distinguished speakers. First one is Professor C.B.L. Magad, and I think he is well known to the liquid crystal community. Still, his biodata is displayed there, and you can see the number of awards in his name. And just he has agreed that he will distribute 0.2% of his awards money to us in giving party. This is, as I told in the inauguration address, that this society gives 6 different awards. So he had got this Lifetime Achievement Awards this year in 2025. And I was expecting that he will tell us, particularly to young people, about his bio sketch, that how he started his journey from scratch. And he did all these work, how he managed so many awards today, that even we could not do. But he has prepared a nice lecture. I think that also will be very useful. But please give your some bio sketch also for 5 minutes or something like that. So, okay. In the end, you will be short of time for your lecture. So,
दो पोडियम दो एक कोई भी खाली कर दीजिए इसको कौन सा फ्री
Well, good morning, everybody. At the outset, I would like to express my deep sense of gratitude to the organizers for having given me this wonderful opportunity to be among you and say something about what I've done during the last 30 years or so. I'm especially grateful to my people. I shall thank them once again later. I'm indebted to the convener, Dr. Rajkumar Gupta, convener, and Mandra Devi for their very, kind hospitality and the way they responded to our calls. Whenever I call them, they are there to attend whatever we said, and we are here today. Well, as I declared today, I move to you on a topic entitled steroidal core-based. Can you put up these lights? These lights are not. Steroidal core-based diverse pathways to fascinating parallel liquid crystals. As is shown in this general template, these cholesterol-based dimers are formed by joining cholesterol with different mesogenic segments having 1, 2, or 3 rings. They are joined together through a spacer of varying length and clarity. Let me declare that we have been carrying out this research only from the viewpoint of scientific curiosity. I have never ventured into application aspect of it because clearly its score is very heavy. So its alignment or its response to the applied electric field is very, very slow. So whatever I have done is all purely because of my scientific curiosity. I have tried to understand what is the structure property correlation. Let me declare. In the first place, it's as of now, today, have been not able to understand the behavior of cholesterol in these pacific liquid crystals. And you see through all slides, they exhibit. Can you put up this slide, please? So can you see that they show very interesting thermal behavior? Rather, I should say, they show very exciting thermal behavior, which is not seen in other types of parameters. Therefore, we have been fascinated. The whole journey began somewhere in 1990. When we have come a long way, about 30 years or so, yet we have not been able to understand what are they, how do they behave. Even if there is small change in the structural parameter, say you convert a double bond to a single bond, then there is an entire transformation in structure property correlation or their thermal behavior. It is extremely difficult for me or my students to understand what are they. As all of you know that cholesterol plays an important role in our life. Without cholesterol, especially that again I will talk about this little later, it imparts various functions in our body. So this is a similar to that. Till today, I'm sorry, I'm ashamed to tell you that I have been not able to understand what are they, why do they behave like that. Now, on the other hand, now young number of current liquid crystals. Cholesterol-based liquid crystals, current liquid crystals on one side, and other current liquid crystals on the other side. I think about cholesterol-based divers that have been showing fascinating liquid crystal behavior. So please be with me. Whenever you have a doubt, please make it a point to ask me. Well, my big thank you to INCS Council members and the selection committee members and jury for bestowing me with the INCS Lifetime Achievement Award 2025. Thank you so much. Thank you. Well, this I would like to dedicate to Dr. S. Chandrasekhar, who appointed me at Center for Liquid Crystals then. Since then, I'm working here. I owe a lot to him. And most importantly, I would like to dedicate this award to all my associate research who have been doing research with me directly or indirectly. I owe a lot to all of you who have associated me with me or INCS. Well, whatever I have done so far, it would not have been possible without the funding support. If you don't have funding support, you cannot do research, the kind of research I have carried out, because the purity is extremely important. You have to do 10 to 15 times column and do the extraction 10 to 15 times, then only your phase functions will be, or basic functions will be reproducible. That has been a big task as far as the referees and me are concerned. All the time we fight with the referee, show that purity is very high, and I think most of you understand cholesterol-based liquid are derived from the natural cholesterol. There is no way you can synthesize cholesterol. Whatever I procure, it is from the source. It is either from the animals or from the man. No, it is from the buffalo. So they extract cholesterol and they sell it, either sell it, whatever the impurities are there. Probably those are contributing factors. I'm not sure what I'm speaking about, but I'm sure that the kind of thermal behavior, liquid crystalline behavior they have shown is really fascinating. You cannot have these sequences in any other type of cholesterol. I would like to reiterate on that point and then let's go. I big thank you Big thanks to all of them. Friends, Mahe, DSP, ANRF, CSIR, and Tata Steel. Well, I must thank Center for Management of Sciences and directors with whom I worked. Professor S. Chandrasekhar, founding director, without whom I would not have been here today before you receiving Lifetime Achievement Award. Sir, I owe a lot to you. Then K. Suresh. I don't mention about Professor K. Suresh that he gave me money regularly. I think you should give a big applause to him. Big money, that's a big chunk of money that I received from him. He said, don't try, you are doing very well. You take this money and then start doing research. And it was really because of him, I was able to do good research. Whenever I go a big win, he would simply sign, and he had a lot of belief in me. Whenever I go, to that 50,000, that then I'm talking about, he signed. Then there was a Kulkarni who transformed me into something else. So he told me that we cannot be just working on cholesterol based. That work, you should switch yourself. You should come out of your comfort zone and start working on soft composites. That's why I was able to contribute in the area of what are known as optical metamaterials that are very important in the context of invisibility. All right. Then I must thank the present director, Professor B.L. Prasad. Every year during last 4 or 5 years, I've been able to grab about 50 lakhs from him. And he gave me a big lab, he considered big lab for me. I think I go after him. I must mention this because without their support, we cannot do anything. All right. So these are my, collaborators and mentors, without whom I would not have done so much of research and I would not have responded to the review comment all the time. Professor Chandrasekhar, late Professor Chandrasekhar, Professor Sri Krishna, Professor Jingal Gill, Conley, Prasad, Sandeep, and then Shankar Bruce. Uma is my wife. And Dr. Shankar Rao, Gita Nair, Achal, Santanu, Markov, and Srinivas Luke. And then we have P.R. Bhattacharya, and then we have Ravi Rudra, Rajiv Manohar, and Dharmendra, Aloka Sinha, and Elvi Pandey. So these are my lovely collaborators and partners in my research. Ladies and gentlemen, I would not have been here today without these gems and stars. Whatever I am today is all because of these gems. And one of the gems sitting here at the moment. And another gem is sitting somewhere here. Two gems are sitting there somewhere. Take over right hand. These are the ones who gave a big shape to my life. They contributed. I think most of you know that I'm very, taskmaster. I'm very, very tough in the lab. I expect them to be from my morning 8 o'clock to 9 o'clock, that has been the practice in the lab. Thank you to them. They have contributed significantly to the growth of the style aspect of liquid crystal. Now we are standing in the position, we have been able to dictate the terms as far as the style aspects are concerned, as far as the frustrated traits are concerned, and their behavior are concerned. Well, Anita, Manoj, Shashi, Achal, Shankar, Rashmi, Swami, Sachin, Madhu, Abhishek, Pooja, Anu, Abhigna, Nilesh, these are postdoctoral fellows, Nilesh, Padmini, Nani, Rashekar, Dev, Yatish, Anil, Santosh, Supreet, and Paresh. Well, these are other kind of gems. They supported all my PhD students. Whenever we wanted the intermediates in large scale, these are the ones who have made we have helped my students because my students always are involved in purification of the compounds. Let me reiterate on the point, when you talk about liquid crystals, they have to be extremely pure. If you are handling a compound that has impurity, it makes no sense. Either be it in terms of chemical impurity or ionic impurity, you should get rid of that. That is the big task. I think the ones who have been trained in the area of chemistry of liquid crystals, they know how to purify the compound. If you are handling the impure compound, it is not the way. You must work on, I'm telling the research, you should put in effort to purify your compound nicely. All right, I shall not go into the details, but I should tell you, right from since 1990, I have been able to focus on different aspects of science. My group is focusing on molecular design, synthesis and characterization of materials that are derived from natural products. We have been working on economically feasible materials for fundamental science as well as applied science. As I said in the beginning, I am not into applied science much, but my materials have a capacity or ability to contribute in the area of applied science. So I have been working on functional conventional liquid crystals, non-conventional liquid crystals, soft nano functional material is one of the fascinating areas these days we are working. Therefore, we have been able to come up with soft nano composites. Then composites derived from nanomaterials, coordination polymers, and so on. Well, under the class of conventional liquid crystals, we have been working on polar and ferroelectric liquid crystals. Yesterday, I was inspired by Abhishek talk. I had given up that there is nothing left in ferroelectric liquid crystal. Thank Abhishek for again, reminding me that there is something in, yet there is something in ferroelectric liquid crystal. I shall promise you, I continue to work and I shall dig out all my bosses and then friends come to you. I'm really grateful to him. Yesterday, it was a nice session with him. Thank you again. Well, you can see these are extremely simple molecules and we have been able to make polar systems. Then, under the class of conventional viscosity liquid crystals, we have been working on SANs, this is Achar's work, and then under the class of what are known as sensors, recent times in association with cows. Let me tell you instance. If you do a good job, you know that King Abdullah University of Science and Technology is the leading research organization in the world. They invited me. Looking at our molecules, you should get such invitation. If you work hard, if you show what your molecules can do, they invited me. 35 days, 5-star hotel, I don't know how much money earned. What I intend to say, not only from the science point of view, we also be exposed to different scientists. I've been made to talk to about 5 to 6 different scientists, including their Nobel laureate. They called me and then put together, we have been able to come up with a sensor to show that the frozen viscosity liquid crystal can sense hydrogen sulfide. You are at the PPB level. So, ladies and gentlemen, my young fellows, you continue to work, things will shower on you. This year, as mentioned, Professor mentioned, so many work, even I don't remember. I am chief member of congratulations. So that is the stage you reach to work really hard. Right. So this we have been able to come up with, up to industry. Some industry persons have come from Italy. They want to develop this sensor. I think we should be able to come up with, one sensor soon. Then under the class of non-conventional liquid crystals, this is the kind of bread and butter. As you can see, we have been working on dimers, trimers, tetramers, and pentamers. So this is the area today which I am going to talk to you for as time purpose. All right. Under the class of non-conventional liquid crystals, we have been also working on what are known as banana-shaped liquid crystals. At the microscopic level, there is no clarity, but still, when you make them, they are possible to give you macroscopic clarity. That is a very interesting aspect of wave systems that I think experts know. In the absence of clarity, if some systems show the polarization, that's a big thing. So people have given up, but I would yet recommend all of you to look into these vertical systems, banana-shaped liquid crystals. Myself and Srinivas started working again. So we have to look into this because there is no experiments anymore whatsoever. These are vertical systems. There is no molecular clarity. Yet they are well possible to give you polar structures. They respond to the applied electrical field as if they are ferroelectric liquid crystals, as if they are current system. That is the fascinating aspect of these kinds. All right. Sensor is able to take two amino acids and join them together through peptide linkage. He made dipeptides and they self-assemble to give you a polar liquid crystal and spontaneous polarization. Please don't, Abhishek, please know the spontaneous polarization is 1400. These columns, they self-assemble, their response to the electrical field is very high. And now we have some more results. We have published one and we have a couple of patents. This self-assemble this particular column, unwinds so fast as if it's the rod mechanism. That is quite interesting as far as I'm concerned. Though it's a columnar liquid crystal, but it unwinds the short period of time, and then you polarization into the bipolar system. So now we have been able to work on what are known as coordination polymers, metal organic frameworks, and polymers that is for the energy generation of energy generation, water splitting, storage, capacitors, supercapacitors. So these are the ones you can see. These are very recent publications. In the last 10 years or so, I've been able to work on what are known as soft nanocomposites. Well, what is it? Soft nanocomposite is nothing but, or soft nanocomposite, we call them as optical metamaterial, soft optical metamaterial. Although physically I am here, I can be invisible. So these are set of compounds we have made. They show what is known as epsilon near zero material. Well, this is how I'm going to talk to you, ladies and gentlemen. First, I will introduce the general aspect of iron liquid crystals very briefly and formally, and then I talk to you about liquid crystal dimers. Then I will switch over to what are known as cholesterol-based liquid dimers, and then their acceptance thermal behavior. You will be amazed to see how they, self-assemble to give you different structures, and they are amazing. They are unprecedented. Nobody has seen it yet. And eventually, I conclude this presentation. Ladies and gentlemen, all of you know that final optically active rod-like calorimetric liquid crystal doesn't matter whether monomer or oligomer polymer. They self-assemble to give you a sequence that can look like this. You have a way of crystal-crystal transition. You may have cubic phase. You may have spectic phase, prospective phases, chiromatic phase, and another set of chiromatic frustrated phases, and then you have isotopic phase. Well, if you look at this sequence, considering all the structures known in chiromatic liquid crystal, this is kind of a advice to all of you that a hypothetical sequence may be generally written as, suppose that you make a chiral molecule, what is expected out of this chiral molecule? So if you are pulling from the isotopic phase, one can get new phase, chiral this is sequence. Nobody can change the sequence until there is a new invention or new entry into the sequence. So if you are coming from isotopic phase, you have blue phase, chiral TGB, Christian boundary, spectic A, spectic C star, magnetic I star, and spectic. This is all fine. It would be highly exciting if the chiral molecule shows the properties such as this. What are they? What exactly correspondence liquid crystals have done? What is that? Re-entrant behavior involving frustrated phases. Re-entry of re-entrant occurrence or re-entrant behavior of a frustrated phase is very, very rare. And then unusual unexpected sequences, multiple frustrated phases like spectral income engineered phase, EGP blue phases, and then frustrated phases for white thermal range, and then technical significant spectral C star and star phases existing for a white thermal range. Cholesterol-based liquid crystals have done this. You talk anything here, cholesterol-based liquid crystals have shown this, unlike other liquid crystals. And recently, we have been able to, come up with ESIPT active liquid crystal dimer that is new entry into my research. That is excited intramolecular proton transfer property. These are fluorescent system. They switch over between the keto and non-monomer. I shall not get into the details because of lack of time. Okay, in the context of what I read, in the context of realizing such novel properties, it is demonstrated over the years by us and others that cholesterol-based dimers, which are the first members of polymeric liquid crystal, are truly promising. They have demonstrated over the years that they can show all these sequences, which is not seen otherwise. All right. So cholesterol-based dimers, in effect, cholesterol-based dimers exhibit unprecedented liquid crystal properties, especially in the context of frustrated phases. Therefore, ladies and gentlemen, I would like to introduce all of you to briefly and very formally to the world of liquid crystal divers, first of the liquid crystal divers under early work and their interesting phase sequence. But liquid crystal divers definition is extremely simple. Liquid crystals or divers are formed when you take two mesospheric segments and join them together through a spacer of varying length and parity. But depending upon what is the length and height of the spacer or their phase function behavior largely critically depends on length and parity of the spacer. You can vary it, meaning that they exhibit a pronounced ordinal effect. Of course, this effect attenuates when you increase the length of the spacer. Okay, due to belt conformation, the odd spacer compounds show low clearing temperature and they show fluidity as well. Now, precisely when you talk about cholesterol-based liquid diver, they are formed, as I said initially, you take cholesterol and then other mesospheric segment, join them together to spacer of varying length and parity. Now, depending upon what is the chemical nature of the mesospheric segment present and what is the length and parity of the spacer present in this system, this is the one which dictates their thermal behavior as you come through, which we realize how important they are. So their behavior depends largely on the length and pattern of the spacer, as others do, and then they exhibit a pronounced ordinal effect. Most importantly, as compared to those of UN-membered counterparts, they show what is known as blue phase. For members, because of their belt conformation, they are blue phase. Ladies and gentlemen, I am very, very happy to let you know that in our research, we have been able to stabilize blue phase over 50, which is very, very challenging. I shall talk to you about that in a little while. Well, this is the, I think, one of the, attractive slide, is the important slide as far as my presentation is concerned. Even I cut my talk, the chairman, this is the one which is very important. Look at the phase sequences you have. It's unprecedented. For example, they show exceptional phase and sequences. I can't imagine the kind of phase we have. It is the first system that shows symmetric incommensurate phase. That's highly concentrated phase. That's how the whole, story started. Well, when we talk about cholesterol-based liquid crystals, the divers. Okay, this slide is important. Let me read through for you. So we have been able to accomplish what is known as symmetric tilde phase, symmetric tilde phase, C phase, incommensurate phase, TGBA, TGBC, TGBC star, blue phase 1, blue phase 2, blue phase 3, and whatnot. There are so many phases which we have been not able to, where is the water here? So which we have been not able to, address or figure out what are they. So these, somebody else. Okay, thank you. I kept it here. Thank you so much. Okay, if you look at the sequences down, very interesting sequence. You cannot imagine. So this is against the thermodynamics of T. Alright, doesn't matter. Let's go. Everything started in the year 1994. Professor Jingle made a first, atomic compound, skip base. This compound turned out to be very, very interesting system. In fact, it's charging the whole chemistry. What's happening? Can you make this compound again? It showed a richest variety and exotic liquid crystal phases. The first LC exhibiting an orthogonal incommensurate phase. That is fluid spectral phase, which was not seen, it was theoretically predicted, but it was the first compound to show that kind of a behavior. Then followed by that, very interestingly, 3 incommensurate phases. Continuous incommensuration in spectral behavior. That was quite interesting. And then 2-dimensionally modulated spectral C phase. That's also quite interesting. So this is the structure we propose. We work together. This is the structure we propose. Then, incommensuration structure we had to propose. So this is a spectral K, this is spectral incommensurate, and there is a locking, and this is the spectral phase. Alright, so this is the X-ray work, excellent work. I have not seen the X-ray so clean. that is done by Professor Harman and Achad. You can see clearly how they are analyzed. You can see the wave vector Q1, Q3 coexist along z-axis here when they are in coming direction. That's the key point. Then Professor Chandrasekhar became, really interested in such molecules. Then immediately in 1990, he appointed me. I started working at the Degree of Science as a postdoc. And then he immediately arranged a talk with Professor Jill. And I immediately went to Korea and then held a talk. Let's talk with Jill. And then everything started. There is a trick when you talk about cholesterol-based liquid crystal synthesis. If you are not putting synthesis of cholesterol-based liquid crystal, you'll be, wasting your time. So I was going to work in his lab for a while, 15 days I worked, and came back. There are some critical points as far as cholesterol-based liquid crystal is concerned. I learned those techniques and came back to India. I knew it, but for the sake of Chandrasekhar, I went to Korea, worked with him. Can you see me how old I was? So, Professor Chandrasekhar introduced me to Professor Krishna Prasad and Professor Rao. They are ASDSR professors now, and began a year, we started working together. But one important point, he figured out that if you have 6 oxyhexanoyl even party spacer, that is, very important in the system. So this spacer makes all the difference, that's what he said. But I switched over to something else, but I worked along with this. So this is the first 4 set of compounds which we prepared in 1991 in association with Professor J. Krishna, who is no more. My 2 mentors are not there with me. I'm very sorry. So these are the compounds which we made. See, this is the compound turned out to be very, very, very important. This is why did we make this compound? We made this compound to realize intermediate phase in our compound. Now, when we looked into this very carefully, it turns out that spectic 1 and spectic 2, they were almost, you can in the DS structure, you can see, they are almost equivalent to the intermediate phase, the intermediate spectic phase reported by single gene. Texture is exactly matching, but unfortunately, they started to decompose. So we decided, we had one group meeting, we decided that we will not work anymore on skip basis. Those who are working on this is to all the physicists and my dear friends chemists, if you are working on skip basis, don't work. It's a waste of time because the decompose very fast. They are very, vulnerable to moisture and heat. So they decompose. So we decided that we will set our goal to realize thermally and hydrologically stable dimers. Since then, we have been able to work on a n number of molecules incorporating in the molecular architecture, toluene, biphenyl, chalcone, bencoal, cyclohexane, phenyl benzoate, salsamine, and sidone. So in some cases, we have extraordinary results. You take any series, we have one or the other compound shows an extraordinary behavior, truly extraordinary behavior, which I'm not able to understand it today. But, ladies and gentlemen, I'm extremely happy to let you know that I've been able to make about 52 different series as of now, and now this summer should go to 600 now. We have been able to make about 600 compounds. Please know you can multiply it by 10 times. I think all the chemists should understand because cholesterol-based liquid crystal dimer synthesis will take lots of time, especially in the context of purification. If you don't purify your compound, I'm reiterating on the point. Who want to work on cholesterol-based liquid crystal dimer or any cholesterol-based liquid crystal, they should be extremely pure because that comes from the natural source. We don't know what are the other secret present, but if you repeatedly crystallize over the years, I've learned how to purify them and make them to show liquid crystal behavior on their own, not because of the impurity. All right. So this are the results that we have so far. Re-entrant phase is going to be the first report of its kind. TGB phase re-enters. It's a ordered system. We have a disordered system. Again, this ordered system comes back. Although given its frustration, given its complexity, it should not come. But these are the systems that show that kind of a behavior that is truly amazing, that is reported by Anita. And then Achal somehow he stabilized the phase for a wide thermal range. He showed that the length of the phase is not important. It is the bend system that is included in the system. That's how he was able to make those compounds having blue phase over wide thermal range. And also, most importantly, he showed that as we call pneumatic liquid crystals, means they show only pneumatic phase, static liquid crystals, they show only static phase. Likewise, the frustrated phase liquid crystals were not known at all. So, Arthur for the first time showed that polyester based liquid crystals can be made, they can be called, TCD liquid crystals. You haven't heard about it. But we did it, we tried to produce the material, and at a very exciting area. White thermal range is existence of blue phase and unprecedented sequences, and then stabilization of complex frustrated phases, and then room temperature carbon phase, and then we have parametric. I will give you, now I'll show you. We have been able to make ferroelectric, anti-ferroelectric, very electric liquids. Not to have gone beyond that. And they are operating very wide thermal range, and I'll show you in some slides. So we have been able to achieve all these, static structures, liquid crystals, right? But here have active dimers, the recent one. I have made 50 compounds, 9 series. First case, we got 18 publications, including, PRN. Actually, because that one. What's that about? Because you are first PhD product, I think. I'm aware. Okay, so he is the first one to give re-entrant to the PFA. I think, it has received lots of attention of the world that re-entrance of any frustrated phase is not thermodynamically possible, very possible. So this came in PRN. All right, now. Shashikala made wide thermal range resistance of blue phase 3 and unusual frequencies, and I owed on to them. Then our heroes, Manoj Matthews, he introduced the polarity in the liquid crystal. It was difficult. He introduced a sit-down system here, and actually, that's why I mentioned about the key stabilized blue phase over wide thermal range. Also, he realized, TGB liquid crystals. Shankar able to make frustrated phases highly, TGB star has two helix parallel running together. It has two helical structure, highly complex structure. He has been able to stabilize over 170 degrees thanks to them. Right. So now then, Tommy made 8 compounds, they are finished. They are fluorescent, highly fluorescent. Then, Madhu contributed significantly. He introduced the concept of excited state proton ESIPT activity in the liquid crystal dimers. So I owed up to him. Then this is the guy, such a very lean person, able to contribute in the development of ligands that can be used to get associated with standard gold scaffold to make softness compounds. All right. So this is one we made. Then these are the ones. This is very interesting. I'll come back to this point later. Re-entered TP phase. She showed after 24 years, there are no single compound showing re-entered behavior. Now, Pooja worked on this. We have now a set of compounds that show re-entered behavior. Not this blended one. 24 years we do. 24 years, we have set of compounds that show re-entered behavior. Okay, now Anu is working on ESMT active dimers, and she introduced what is known as peak chemistry. So Abhigya introduced a rich chemistry into these liquid crystal dimers. All right, blue phases that I'm up to time. 3 minutes. Okay, fine. All right, blue phases, what are they? Then we in chemistry challenge that my aim is to see whether we can realize blue phase as re-entrant. I'm putting it on to myself, and then we have frustrated phases, fixed grain boundary phases. We have been able to, stabilize them for a wide thermal range, and all of them are quite, interesting. Now, in terms of at least one student, I will talk about my first student who made all the difference. Look at the best sequence in the interest of students who are here. Look at the textures. So one of the compounds show re-entrant behavior. So this is TGP phase, vectic K, elements would disappear, and then re-entrant of TGA, all the elements reappear again. Then the pyramids get converted to undulating structure, so you have undulated structure. So these are homeotropically aligned liquid crystals. They are around the optic axis. Now, if you align them, make them to lie along the plane of the glass, then you have beautiful texture, because in this there is two helical system, helix running parallel here. So this is the PGBC star. You have one helix here, another helix there, up there. So therefore, it's very, very interesting. So this is the first re-entrant phase, and this was unequivocally demonstrated. The existence of this was unequivocally demonstrated using X-ray diffraction study. We measured the layers in all the phases. It was expected as this, and then selective reflection. You can see TGPA doesn't reflect the light. So it was last time, then we came back, then we have been able to establish this. So after 23 years later, we have a set of compounds. They show this re-entrant TGPA. We have a large number of compounds now. You can see they show re-entrant behavior. After re-entrant behavior is not easy. It was not possible to have been working. We have not been able to move. Which are able to get this. This is student and those two are working together. We have been able to show this re-entrant. So again, Achal, as I said, I think it will be on my last slide. You can see in cholesterol-based liquid crystal divers, if the cholesterol and resurgent segments are separated by odd parallel spaces, they show blue phase. Unlike that, he demonstrated that if you put in a bent core here, short bent core, you will be able to realize, all the liquid crystals are showing blue phase. All right. So this showed, all of them they showed blue phase. That is in where they have odd parallel spacer or even parallel spacer. So thank you to them. And most importantly, can you see these by pulling from the isotropic phase, you have TGB star. Therefore, they can be called, what are known as frustrated liquid crystals or TGB liquid crystals, or you can say they are the ones who we are the only first system appearing in the literature as the first examples of frustrated phases all alone. All right. Okay, I will escape this and then go to my last slide. I will not worry about all these things, very interesting behavior. Okay, this is the last one. Generally, when you have blue phase 2 and 1, they selectively reject the light because it is without total crystals. Okay? They are oriented in a different direction. They selectively reflect the light. Therefore, you have mosaic texture. Your mosaic texture, beautiful mosaic texture of different wavelengths. They selectively reflect light because they are total crystals. But recently, we have been able to discover blue phase that doesn't do that. Can you see white and dark patches? Meaning that they selectively reflect the light in the visible features. Theoretically predicted about 100 years ago that a blue phase can also be of the kind that selectively reflect the light in the visible features. For the first time in this month, I'm extremely happy. Abhishek, where are you? And so geospatial to be the one who makes it compound. We have set up compound that show that behavior, and I'm extremely happy to see that these are the reflections. I think all we agree that they exist for 4-5 degrees. We have been able to work on this since 2-3 years. We have been working. We are trying to establish. Portrait diagram was not possible, but other ways we have been able to. That's what I was going to you yesterday. Okay, so this is what we are seeing. It's a very exciting result. We have been able to meet the theoreticians that they predicted this. Now, it is just, let me tell you very honestly, we didn't expect anything to be like this. I'm blessed at the sort of beginning of another career after 60 years. This is the first result we got. I'm really blessed, truly blessed. I'm grateful to Almighty and thank you all of you for listening to me. Thank you very much, Commander. So, I expect the Lifetime Achievement Award. I owe that to all my students and associates who made it possible. Thank you once again. Am I in time?
Yes,
Perfect.
very much. Some time back, I met to a medical professional, doctor. He told, I am very famous. Or do you know what? I asked him for what? He told me that I can bring the positive side of frustrated people. And so is about Professor Elmagat, that he has brought the beautiful side of the frustrated molecular liquid crystal molecules. They are very difficult to handle. They are really frustrated molecules. They don't know what to do. I have worked on his sample and produced 2-3 good papers with Achal Kumar and produced wonderful result. So much so that even now people are thinking to prepare displays also from these frustrated people's blue phages. And blue phages have been achieved as wide as 40 degrees Celsius or something like that. So lot of experience we have got from your work and wonderful work. No doubt it is exceptional, no doubt. And I don't know whether they can be given time to ask some question. Okay, okay, you can ask 1 or 2 questions.
I can invite any number of questions in my topics.
Generally, there is a protocol at our place that during award lectures and all these questions are not asked. But I don't feel like that. I don't feel like that. They may ask the question. Okay.
Very exciting talk. I enjoyed a lot. You mentioned a little bit about the spontaneous exploration over 1,000 something. 1,040. Can you comment on that? Because because of the time, you were not able to discuss that thing in details. So the 2 things I will be more interested in that is what is your response time? And how is your hysteresis if you have a study?
It's not that encouraging.
Okay.
Negative part of it. Because, you know, these are peptides, these are supramolecules. They stack and they are locked. There are 2 ways of they interact, talk to each other, they correlate with each other through the pi-pi interaction. Not only that, the hydrogen bonding. So they are really locked. Until that you put in really hard efforts, they are don't unwind.
So maybe it is a very good candidate for the memory.
Later, but now I have a way to come up. Now I have way to overcome this problem. We have way to they show similar behavior. Quick actions.
Okay, yeah, sure. Let's discuss.
They are quite secret.
Okay, I have another thing to tell. Okay, please ask.
Sir, very interesting and very wonderful work. Regarding ESIPT work, if you can give some insight, because how to analyze ESIPT type of liquid crystal.
Keto is talking about keto goes to power. Sorry, goes to keto goes back to phenol. So if you have to measure the fluorescence, that's a short answer, but I shall discuss.
Okay, thank you, sir.
How it can be switched over. So meaning that it will cover entire visible range. The emission range will be from somewhere about 350 to about 900.
Okay.
You have 2 isomers. Because of that, it covers the entire range. So that is quite interesting as well. So it has multiple functions. So I am quite blessed that we have been able to do it.
Okay, thank you, sir. I'll talk to you later.
Okay, so I wanted to tell one more real happenings that will inspire you. When I started my PhD work, I was given the time to work on cholesterols by my PhD supervisor, cholesterol myristate and cholesterol pelargonate. And then when I used to come RRI, people were talking about displays, this, and then I got frustrated. And then I told my supervisor that how old sample sets, sir, you have given me, what I will do and this, that. So he encouraged, no, you should find a look. It is your work that is important, not the material that is important. And ultimately, when I started, then we found asymmetric A star phase in the mixture of cholesterol pelargonate and non-oxybenzoic acid. And that schematic A star has become now TGB A phase. And at that time, even Professor O.D. Leverantovich was working on that material, and he also supported. So you should not be frustrated in your research. No one knows that when your research will be important, and that will give the area to people like Professor C.V.L. Bhagat. Thank you very much. And now I think we should give the awards and medals.
No, awards will be given later. But this I should receive. I request. So great honor for me. Please come here. Please. You can come here.
Yeah, please. Yeah.
Thank you so much. Okay. Thank you. Very kind of you. Thank you, Chair. I hope I have mean time. Thank you all.
So another very interesting lecture is from Dr. Abhishek Srivastava, and he is from industry. So I think he will give you the real glimpse that how you transform the beauty of liquid crystals, the delicate phase of the matter, to industry. And I hope that will be very inspiring lecture. And he was also among one of the young students at some point of time from University of Lucknow. But you see, he has now transformed into the good engineer, and you can get, I think, encouragement, lot of encouragement from his work. CVs, I think it is to be displayed here. Huh? It will be displayed. Oh, that is why it is disturbed. So should I read? Acha.
Right. See, didn't work here, right? It should have to be. No, it didn't detect. Okay, got it. Huh? Yep.
Duplicate mode will be with this only.
Okay, let's do mirror, right?
Mirror.
Yes, mirror. You need a different.
Maybe extend desktop.
Connected properly.
It's connected.
You have a two converter. You don't have HDMI.
No, it's a HDMI.
You have a converter and then. Okay. Sorry for the glitches.
Let's go. Huh? I have another this, but this.
Sorry for the problems with the electronics.
It is not audible much.
All right. Oh, great. Take it right. I think it's something is wrong with the settings of the. In case it doesn't work, then maybe let's try my pen drive. Maybe pen drive can work. Have the 15.
And this the
That is what I'm trying to say. Yeah, let's take a look on this one. Yeah. So the problem that I wanted to discuss today is basically about the vibration sensors, and I have a lot of videos and animations, and because now my laptop cannot work, so probably those animations and video may not work. I'm not 100% sure. Sorry for that. So because the way of making presentation in MacBook is a little different than Windows, so it's always some glitch.
हो सकता है कि मैक नहीं
ये वाला लगा देते हैं।
हाँ ये वाला वो चेक कर
You can use another one, right?
Yeah.
We give it a final try, and if it doesn't work, then we use my laptop pen drive. This is rejecting it. Laptop is rejecting. I think it's not needed, but anyway, if you want to.
Introduced, I think now we request Dr. Abhishek Srivastava to start his talk.
Okay, thank you. See. All right. Unfortunately, I don't have that bigger, energetic voice like Professor Yalmagar to learn over the years. I hope I can meet that pace and energy in the age, in your age. I will keep working. So first of all, thanks to all the organizers first, and particularly the Indian Liquid Film Society. And when I spoke to Raj about organizing the conferences, to organize this display workshop, the motive was how can we bring the community to the pace like, okay, this is a thing which is still very interesting, right? So, and I spoke to Professor Sandeep Kumar, Professor Yamagar, Professor Thar, and all of those big leaders within the community who inspired a lot, right? And they suggested, yes, it is possible to do. And then it happened. And we had a very good, wonderful session yesterday, thanks to Raj and Manjula Devi for organizing that. And so today here I'm trying to talk about the vibration sensors. And actually it is very interesting way to see it. First, I was here back physically, particularly back in 2008 in this conference. And I'm coming back somewhere around 16 years later. I can see old professors and the new friends and new students. It's very, very exciting. Thanks to all of you. So let's see what I'm going to talk today about is vibration sensor. And then you can notice that there is the first term called written as passive, right? What is the meaning of passive? Passive means we don't need any power. And why do we need that? So as usually you see that I am working the display. So we developed some new kind of materials ranging from liquid crystals, nanomaterials, and try to do the different optics, develop different kind of photonic elements. And most of the time we use it for displays, but we also use some of those materials for photonic. And some of these I'm going to talk about today. So Raj mentioned that I should repeat some of the slides what I did yesterday. So I will just repeat a couple of slides from last presentation from yesterday, because just to give you a glimpse where the display industry is going and why we are interested in displays even now. So if you look at this picture, basically I took some of these pictures from CES, which is the biggest consumer electronics show of the world, in Las Vegas. Usually it held in January. So I took this picture in January 2025. LG Canyon, which is basically trying to replace all the surface that you can touch, right? In the near future, let's say maybe 5 or 10 years time, it will become a display, right? Doing different kind of things. Quantum dots, also the liquid crystals, because they are dielectric in nature, they can be used for as a Wi-Fi antenna as well, right? And then AR, VR, of course, holographic displays, stretchable display that now you can wear the display just like a phone, okay? And then different shapes. Now, so far, the way of presentation is just like a flat screen and audience is sitting in front of you, right? Or you're having your mobile phone in your palm and trying to see. It's a flat screen. But now, it's not flat anymore. It has different shapes. So this is a picture, basically, of not from the sphere in Las Vegas, but it is a small demo that they tried to show case in the CES this year. And now you can see there is a big demand of having curved surface, right? Or surface which is like a kind of a sphere. So in that case, you have much more different ways to represent your content and explore new avenues. On this, you have different surfaces they try to use on the vehicle. This is a truck where they replace the surface of the truck with the screen, so you can use another surface for advertisement and all, right? This is a truck from Kia. In this picture, basically, we have only car, which is real, and the rest of the things are virtual. So there is a convergence between the real world and the virtual world. And second important thing is the displays are getting bigger and bigger, and whatever surface you will be able to touch in next few years, it will become a display, right? So and also more pixel, right? We need to show many different kind of content, and these pictures of the displays should not be just working as a visual display, but should also be doing different kind of things like proximity sensor, temperature sensor, humidity sensor, and different kind of sensors too, right? And then the trained. This is a very important slide, particularly for the youngsters sitting on the back. The display industry right now, it's worth more than $200 billion US, okay? And it is increasing. If you look at this, it is still increasing with a CAGR of around 6%. It also depends on what type of component or what kind of product you're talking about. But the most important thing that is important here is that there are two messages from this slide. Number one, LCD is still a market leader. OLED is growing in the mobile phone sector, but it's still LCD is one of the dominant technology right now. And if you look at the growth rate, in America, it is only 4%, right? But in Asia, it is 5.5%. And actually, that is the driving force. In Asia, I think India is in Asia, right? Now we have explored Korea, Japan, and China. Now this is the time for India. So, believe me or not, Korea and China are basically saturated. Now the growth what we'll see is basically will be coming from India. So SID is putting a lot of efforts to develop these two chapters. So one is India and another one is Vietnam. So we are definitely here to help you in case you need any help in connecting with the different companies or in connecting with the different resources worldwide. SID will be very happy to help, right? And that is basically reflected because all the top leadership, including President and publications chairs and all others, are very dedicated. And some of them are actually in the advisory committee of Semicon of Government of India, right? So we have good connections all the way from industry to the government as well. So if you need any help, maybe we'll be able to tune some of the knobs over there, right? So let's see. Let's try to explore this possibility and see if we can get some things going on in India here. All right. So what we do here is, I'm not going to talk about much about display today, but just few things. So this is a typical LCD structure, and if you, this is what I showed yesterday as well. But the key point here, what I want to mention again here is that there are multiple points, multiple problems in this particular structure. If you start with 100%, basically you have only 4% or less than 4% light, sometimes depending on your resolution, for the imaging. That means the display is kind of super less efficient, right? And there are multiple components which are responsible for that. So my group is trying to work basically to avoid these two particular problems, to solve this problem for the polarizer, which is basically resulting in around 55% of the light losses, and color filter, which absorb more than 70% of the light, right? So my group is trying to work particularly on these two problems to solve this problem, and our target is to increase this number from 4% more than 20%, right? So we are working on the light source, which should be polarized light source, also different kind of color filter, find the remedy for the color filter losses. So we use fast liquid crystals such as ferroelectric liquid crystals to use in like a field sequential color display technology. So some of these technologies are already licensed, and some of them we are still working on. So we demonstrated already more than 9% efficiency for quantum rod enhanced film, and also the field sequential color filters, color technology using the ferroelectric liquid crystals. But today I'm not going to talk about the display here. So today when I spoke to Raj talking about what should I talk here, he said talk something which is relatively new. Right? So I'm going to talk about something related with the photonics. So in photonics now we are working on sensors, like the passive sensors, and also some computers. So we have demonstrated very recently the full adder using the photonics, right? Well, I will not talk about it today, but I will talk about sensors basically today. All right. So let's see why we need sensors, particularly the vibration sensor. Now, we are trying to have bigger and bigger buildings, right? Very tall buildings. Particularly in Hong Kong, we have every second building around 50 floors high, right? It's just like a crazy vertical growth, right? And additionally, you have this kind of big mega structures which you need to monitor every time, right? Otherwise, if you have some cracks, and it may result in very big disaster, which we don't want. And that is actually what happened recently in China, where they had many cars were basically, they got a very big accident, and more than 60 cars were collided altogether just because of the glitch in the this kind of bridges. In addition to that, one important thing is the earthquake, right? Earthquake is also a very sensitive thing, because now if you look at the earthquake, this is the data, some of the data from the US agency's National Earthquake Information Center. And what they say is that we have more than 20,000 earthquakes every year, right? And that is what you can feel. So roughly speaking, around 55 tremors every single day, okay? And some of them are really disastrous. So you can see some of the pictures over here. And the important thing is that how can the pattern, you can try to understand how these vibrations are happening. But the technology what we use today are actually not that great, because most of the time they use seismometer, which require a lot of power. And that is okay when you're talking about the surface analysis, where you have your sensor somewhere around the surface, or maybe around 10 or 20 meters down there from the surface. But those gives you very limited information, because 70% of the Earth's surface is covered by water, right? And for water case, when you deposit, when you make this sensor, you have to deploy this sensor on the seabed. And to do that, you are seriously limited by the power, seriously limited by the cost, right? So I was talking to one of my colleagues, if we can deposit, what exactly the cost is if we can put this sensor on the seabed. And he told me the simple cost is one time, $1, and you need at least 4. Okay, so 4 times just to deploy this and extract that sensor from the seabed, because you need to send the ship over there, and the cost is seriously high. Then we say, okay, and the basic problem is because the power ran out, and you have to replace the battery, or you need to get the data and then do something. Then we thought, okay, can we develop something, some sensor which does not require any power? Okay, and because that will solve a lot of problems. Okay, so that was the basic motivation behind it. And if you look at this, some of the research actually already happening. So you can see here, this is it is from Japan. So they are trying to deploy this kind of sensors around the beaches. So yeah, but actually the periodicity is very, very large. So this is like somewhere around 50 kilometers per sensor, right? The periodicity, the pitch is seriously large. But anyway, they are trying to develop this kind of sensor array, and it is not happening only in Japan. Of course, Japan is very sensitive for the seismic activity, but Canada is also doing the same, US is also doing the same, but all of them are deploying these sensors, and they need to power these sensors either through the wire, or you need to deploy the battery and change these sensors every year or two, right? So this is a very simple structure. So this is a buoy, they just put it on the seabed, and then after finishing the task, it comes up and you can collect the data, and this is kind of a very, very cumbersome process, okay? But, so this is the paper that published in Science back in 2018. What they demonstrated is that they used the fiber cable between the Canada and UK and try to see if they can use the existing infrastructure of the optical fiber network to see if we have any kind of seismic activity in this area, right? Because optical network is, fiber is already there. And they were able to detect it by doing very complex video analysis. They were able to detect there is a turmoil, this is the magnitude of that thing. But what they cannot tell you is what is the location, pinpoint location, and the direction of wave propagation of this seismic. So that directionality and pinpoint location was almost impossible to find. Then we came up with an idea, can we use, and also it is very, very expensive process. Then we say, okay, this is not only important for the seismic activity, but also important for the mega structure analysis, right? Because you can deploy this kind of sensor all over the bridges and then keep monitoring the simple harmonic motions and simple harmonic frequencies. If there is some change, that means you have to modify or you have to check the structure if there is some cracks or some physical anomalies there, okay? So then we came up, okay, you have this frequency, and if you change the frequencies, you can actually cover a very large range, right? So you can cover seismic activity, you can also cover the structural health monitoring, and also you can have some small detection for the machinery structure, or you can also use it for the such as traffic monitoring or things like that, right? So we try to exploit that area. So we try to see, okay, what we can do. So we try to first check what is available. So this is a list of sensors which is available and has been used for this kind of analysis. And you can see all of them require actually power, right? The power is using through batteries or through wires or things like that. But none of them actually can work for a very, very long time. This one, network actually does require wires power, so the range is significantly small, very, very limited, right? So, and the real-time monitoring is almost impossible and very, 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 very expensive. So said, okay, if we propose a new idea that, because we have seen this paper from Science, that by using the optical fiber network, you can tell the pinpoint position by analyzing the optical modulation. So if you develop something using the liquid crystal, where you can have this reflective mode over here, and because liquid crystal, if you can tune this liquid crystal with very, very small driving voltages, then you should be able to detect it, right? That was the idea. So we propose this idea here and say, okay, this is a reflective cell. You sense the sensor here, and if you have some modulation over here because of some voltage transducer, then basically you can detect the change in the phase, and you can tell if this phase is related with the earthquake magnitude or seismic activity or vibration magnitude or not, right? If we can find the linearity, it's great. If not, then it's not going to work. So then the first important key point here is that we need a liquid crystal, because all the liquid crystals are characterized by threshold voltage, right? So we need a liquid crystal without threshold voltage. That's the first key point here. So that is basically LC electro-optical modulator we need, but we have limitation of threshold voltage. So how can you avoid threshold voltage? We know that threshold voltage is basically given by that, so you have a big leverage on the delta epsilon. You can increase it, but again, as I said before, if you increase the delta epsilon, then basically you have a problem with the speed, right? And here we need speed because we need to cover a very large frequency range. So that is not a very big good alternative. So we try to use it for like using a photo alignment approach. So here we change the pre-tilt angle. So if you can change the pre-tilt angle, what you see is that the PTH is proportional to the pre-tilt angle, and for a certain pre-tilt angle, basically you can remove this pre-tilt angle completely, and you can use this. We developed this new material where you can tune the pre-tilt angle almost continuously to control the VTH, right? So that was a very interesting idea. And then we optimized the material for the dielectric constant and other things, and you can see we almost removed the threshold voltage over here, right, by optimizing the tilt angle and the dielectric constant, dielectric entropy of the material, and the material is still fast enough. All right, so then we deploy this thing using the, so we also need to avoid some of the polarizer and optical losses, so we use diffraction element. So we designed this diffraction element, and the idea is very simple. If there is no electric field, then basically you see the light is diffracting, and when the electric field is applied, then all this diffraction component will disappear, and basically you will see uniform optical plate, and then your diffraction will disappear. So if you monitor the 0th order here, 0th order will increase with the application of electric field. It will simply increase like that, and the first order diffraction, if you are monitoring the first order intensity, this will go like that, exactly similar as 0th order. That was a very interesting way to look at it, and we try to monitor that thing and try to deploy this thing in the sensor, and you can see we can really monitor that thing. And the idea is because the transducer, we just simply borrowed it from the commercial sample where they use piezoelectric based films, and these films can produce very, very small voltages. And why do they need power is because piezoelectric can convert mechanical vibrations to the voltages, right? But now because you are using electrical transmission line to transfer these signals to the control room, which is like 100 kilometers far. So you need to amplify it, otherwise you will lose the information in the middle of nowhere, right? You will not find the information. So what we did is here, we use the same transducer, convert this voltage into the optical phase, and then because it's in the optical phase, then you can transmit this thing 200 kilometers almost without any amplification or without any loss, right? So you don't need amplifier, and if you don't need amplifier, you don't need power source at the sensor probe. So we were able to demonstrate that yes, it is able to detect all the vibrations, but sensitivity is not enough, of course, because we are using pneumatic liquid crystal. So you say, okay, can we use ferroelectric liquid crystal for that? Yes. The question is, which one? So ferroelectrics are known for a very long time, right? Clark and Agarwal effect was proposed in 1980, and then it is basically bistable in nature. Bistable is not the thing that we are looking for, because bistable behavior will not can be used for the vibration monitoring. So what we need to do? So we need to analyze. The first thing is that we need monostable sample, which is basically can restore itself completely when you remove the electric field, right? So if you look at the switching time as a versus a voltage curve, then what you see is that you can divide this curve into 3 parts. Number 1, when the response time actually doesn't depend on the applied field, and then you see this hump, this peak, and then after it just exponentially decay, just like that, right? So this area is basically we do not have a helix, or you can say the helix is unwounded. This peak corresponds to the helix unwinding, and in this area, basically the helix is simply distorted, right? Helix is still there, but it's distorted. So in the terms of optical performance, what happens is this area, which is basically we call it the formed helix ferroelectric liquid crystal, this is entirely monostable in nature, right? That means it is just, if you imply the electric field, it will show you something, but when you remove the electric field, it restores completely because elastic energy is seriously high, orders of magnitude higher than the other liquid crystals over here. So this is the area where which can be used, and then we focus on our efforts on that. And this is a simple picture of what we just try to show that what we did for ferroelectric liquid crystals. So we developed 4 different new models, new modes where you can use it: monostable, digital, analog, phase modulator. So we also use this one. I think we will talk sometime, some other time. This is very, very interesting, which gives you perfect phase modulation and very, very giant Kerr constant, right? So we recently achieved a Kerr constant of over 250 nanomoles per volt square. That is kind of a record for 1550. I think we will publish that paper very soon. All right. So then we basically focus on deformed helix, and deformed helix optics looks like that. So you have a helix aligned in the planar alignment like that. When you apply the electric field, you have a deformation, and the optical axis basically tilts to one side in the plane. So it just sweeps in the plane, and because it is swept in the plane, you can see the perfect in-plane switching and the modulation of the light. You can calculate the transmission profile just like using these equations, right? So here there are 2 important things here. Number 1, the delta N effective is changing because of the change in the ellipsoidal index of the ellipsoidal. And the second important thing is the variation of the optical axis, which is also a function of electric field, right? So these are very two important factors which we have to use in our sense. Okay. Then we tried to see if we can use it. So if you see here, this slide shows you that yes, it has both the characteristics what we need. First, monostable. Second, it doesn't have any threshold, right? So you can see there is no any threshold over here, and it has more or less linear performance and only monostable characteristics. When you have positive field or negative field, you can see only one state. Now this is the response time, follows the typical characteristics around 300 microsecond of response time. And then we use the existing material what we had in the lab, and we change the beta angle, which is the angle between the alignment axis and the polarizer, to 20 degrees. And then you can see this is linearity within the given voltage, right? Around 2 volts, you can still see very good linearity in the response. That means now if we can use the piezoelectric material and use this cell to detect the vibrations here, right? So we deployed that thing, and this is the area what we use, and you can see this is the result, right? And we compare this result with the commercial samples, and you can see there is a very good matching here. But the problem is the sensitivity, which is basically the measure of this linearity over here as a function of voltage. So this linearity, this slope of this line is not that great. Okay, so we wanted to increase it. So what can we do? Still not enough. So now we have to go back and try to understand the optics a little bit more. So the optics, basically transmission or reflectance, of course, if you want reflectance, then basically you change the retardation factor here. But overall, the transmission, which is the function, as I said before, the alpha, which is the variation of optical axis as a function of electric field, and effective reflecting index, these are the two important parameters. But this is because we are interested in the sensitivity and the frequency range. So you need to optimize all these parameters together. And for ferroelectric, if you are working in ferroelectric, you know, it is kind of a multi-parameter domain. If you touch one, the others will suffer, right? So you need to find a nice balance between all of these properties to achieve a very good electro-optical response. So we did that thing, and what you can see here is that alpha is basically given like that, where G is basically like this, and X chi C is over here. So when you do the first differential, what you see is that this alpha is stand out, right? And alpha, the variation of alpha as a function of voltage is critically important. And then we try to calculate it and try to see how the alpha can be improved. So on this plot, you can see over here, we kept this pitch and PS just up to that level. And if you reduce the tilt angle here, what you see is that your sensitivity is increasing. The alpha can change very fast, very quickly if you apply smaller voltage, right? That means the slope is increasing, right? So in that scenario, what I can say is that if you reduce the tilt angle, you can increase the sensitivity. Okay, that was a great idea. Theoretically predicted. Then we did some material here. Sorry, I cannot show you the information hidden behind this bar because it is still covered. It is under patent production. So maybe next time I will show you this more detail about it. But then this is like basically two materials we made. You can see this is the old material and this is the new material what we made, and the properties are basically here. 39 degrees for this one, the first one, and we reduce the tilt angle to 20 degrees. So that, as expected, if you reduce the tilt angle, then your sensitivity should improve, right? So we try to look into it, and then you can see really the sensitivity. And the response, let me show you, yeah, here. So these are the two response curves. So this black curve is for the old liquid crystal with a tilt angle of 40 degrees, around 39.5 degrees. But when you reduce it, then you can definitely see here the sensitivity increase significantly, right? And then second thing what we wanted to understand is that how your frequency range is depends on the material parameters. So here I'm saying basically frequency range mostly governed by the Goldstone mode, relaxation frequency. So if you play with the material parameter like dielectric anisotropy or dielectric susceptibility and also the pitch, then you can basically tune this this bandwidth significantly. But anyway, the bandwidth for the commercial sample, which is here, which is you can see over here, is around very, very small. But all those four electrics liquid crystals are seriously big. So you can cover all the way from very, very small frequencies for seismic activity like earthquake and relatively high frequencies to detect, like for example, the bridge health, or also you can use it for the detection of mechanical characteristics of some of the components. So we deployed that. And the interesting thing was we did two experiments, right? First is we tried to deploy the sensors onto the bridge like that, and also the second bridge was like that, these two different bridges, and try to analyze. And what we did is we put a commercial sample. This one is a commercial, this one is a commercial sensor, and this is our sensor, right? And you can monitor this vibration, and you can see that both of these two frequencies and response are equal, identical. The difference is the commercial sample, they do need power, and our sensor doesn't need any power. Okay. Now, interesting thing was we were able to detect the speed of the vehicle passing through this stuff, right? So, and the accuracy was 0.5 kilometer per hour, right? So if you are driving your car with 50 kilometer per hour, you can detect within an accuracy of 49.5 to 50.5, right? And we were very excited. We did tons of experiments on the car, on the buses, many different structures. And say, okay, let's go to the transport department, right? Because we have very good tool to measure the speed, and it does not require any power or any big infrastructure for that. And when we reach out to them, they say, wow, it is very good, but we will not use it. The reason is they want to have like plus minus 5 degrees, 5 kilometers per hour. So 0.5 is not that important, right? Because it's too highly accurate, and it is not that they want. They want to have definitely, they want to fine you for the speeding, but not that precisely. So that was the very interesting thing. And then we use this one to detect the cracks into the mechanical slabs. So what we did is we created different kind of slabs, and then try to understand this system of these slabs by placing the signal sensors at different places. Compare it with the commercial sensors and our sensors. You can see more or less identical, and use some of the AI techniques to understand how deep this cut is, how bad it is. So we were able to conclude a lot of different things, but I think I will talk about those AI things maybe some other time. But this paper is already submitted, so I hope it will be available to all of you in a short time. All right. So this is more or less the last slide for me. So here we compare, basically what I can say is the takeaway message from here is that yes, there is a possibility to use ferroelectric liquid crystals in a cost-effective manner for the vibration sensing, right? For example, even if I'm walking here, the sensors can tell me where exactly my physical position is. Okay? And this is actually equally good as commercial sample. So here, the bottom two lines basically is talking about the pneumatic-based sensor, and the last one is basically the Van Helix ferroelectric liquid crystal-based sensor. And another thing that is important is, for the display application, we need large tilt possible, right? As large as possible. But for the sensor application, we need to reduce the tilt. So if you reduce the tilt, your sensitivity increases significantly. But for the display application, when you increase the tilt, then your bandwidth about the grayscale increases, right? So this is like a kind of opposite requirement for the display and the sensor. All right, so that was my last slide, and here is the overall portfolio, what exactly my research group is doing. So we do a few things related with the display. Like you can see on the top, we have quantum rod displays, electroluminescence, and also this is a quantum rod enhancement film, what we use to compare our results with the iPhone. And then, and believe it or not, this film perform better than the iPhone already. And some of the lighting products which can achieve more than 200 lumen per watt efficacy. And on the liquid crystal side, we are working on very fine displays, micro displays. Like this one is 3 micrometer pixel pitch. And yesterday I mentioned we are going to disclose 0.8 micrometer pitch very soon. This is LiDAR, which is basically using diffraction elements to understand exactly how the environment is. And the beauty of this component is that it does not require raster scanning. It can scan the whole system just only by one shot. Okay, and this one is very exciting. It is basically optical computer, photonic computer. So there were some ideas behind it long time back. the people who tried to explore photonic computers, but this is the first time we demonstrated full adder. You can use ferroelectric liquid crystals and some of the optical component to perform the full adder. The full adder means you have, if you add A plus B, then basically the outcome will be a carry, which is going to the next bit, and the sum that will be the residual of the total sum of that bit, right? So you need to perform that optical operations, and this was the setup which basically we have demonstrated. Paper we are trying to write, it's under preparation, and hopefully I will disclose that thing very soon. All right, and then this is the list of publications, basically what has been covered here. And then, of course, the acknowledgement, the team which is basically working on this thing. So as I said, right, my group is working on two different topics. One is the quantum rod materials, and second is on the ferroelectric liquid crystal material and alignment material. All the greens here, they are working on the liquid crystals. All the reds here are working on the quantum rods displays, right? And of course, funding agencies and the collaborators around the globe. Yes, thanks to all of them. And then I leave you with a spectacular view of the campus. You can see Professor Yilmagad was there some time ago. And this is a view of the canteen, and this is a view of from, actually, I think it is from my office, right? So this is a very beautiful view of IS building. It is not anymore like that. We have a new building. I think Christian may tell you more about it. No, not yet. Maybe soon. And then the last is kind of advertisement. We are hosting a conference in 2 weeks, right? So if you are interested in nanomaterials for display application, scan it and try to reach it. Registration is completely free, right? Because funded by the institution.
Very good.
Thank you.
So thank you, Dr. Abhishek, for a very nice, interesting lecture. And this is answer to all those who says that liquid crystal research are over. You can see there how much potential is there to work in the area of liquid crystals. And this material is still have large scope than any other comparative material. So very good lecture. And of course, I think you must be curious to ask some questions, and you can do so. Yes, please.
Yeah, thanks for the wonderful talk, Sir Abhishek. You did mention that there is no need for power to stabilize these sensors in wherever you wanted to install, right? So when you have this kind of LC material, we know it is all temperature dependent, right? So these phases may require to operate in a normal temperature or something like that. You should have some kind of a temperature controller, right? So that may need some kind of power to keep that. Is it?
Very nice question. And the answer to this is yes and no. Yes, if you are using it outside, right? Like in the ambient in the environment. But here, you can deploy the sensor down there under the ground.
Yes.
10 meters down there, 100 meters down there, or at the seabed.
Okay.
So where temperature is more or less steep. So temperature is not a bigger problem. That's answer number one. Second is that all of our material are basically good in the range of -10 to 80 degrees C.
Yeah, okay.
So
that
it's
makes
all ready.
Yeah, that answers. Yeah, there's a wide range of.
Yes, exactly. Yes.
Yeah, thanks.
Thank you.
Okay, Dr. Ganguly.
Thank you for the talk. It's very nice, interesting results. I have two questions. One is last slide you have shown the quantum rods have the higher efficiency. Can you just highlight why? And second one about our packaging and the basically aging effect and all that, the earthquake sensor. Can you highlight on this?
Aging effect for the earthquake sensor.
For the sensor, yes.
So aging effect. So basically, we started this research two and a half years ago. The aging effect, we did not test it yet, but I believe is going to be something similar like any normal liquid crystal, right? Hopefully, I will be able to answer that thing maybe in a couple of years more. However, second question was about quantum rod, right? Why the quantum rod shows the higher efficiency? For that, I need another lecture. So roughly speaking, I can tell you is that most of the Lambertian emitters are basically limited by the Snell's law. So outcoupling efficiency is limited to 20% around. But quantum rod, because it's anisotropic in shape and it's only 2D confinement, so the excitants are shared with the C-axis, right? and therefore this emission from this kind of particle becomes dipole. And if your dipole is in the plane, then intrinsically it doesn't follow the Snell's law, at least in one direction, right? So in that case, basically you can double the outcoupling efficiency. And that is the base reason why your outcoupling efficiency for the quantum rod is supposed to be 2 times better than any other Lenzburgian emitter. And that is not only true for quantum rod, but it is also true for organic molecule, right? So if you talk about, there is a tons of research papers published for organic molecule, OLED, polar OLED, where they talk about dipolar emission, and the efficiency is definitely higher. So any dipolar emission will definitely have higher efficiency, but there are tons of problems. That I said, to explain that I need another lecture, right?
So, okay, if we'll continue the question, there will be another lecture also again. So we will have to stop it here. But we were discussing that by the end of third lecture, we will have lunch time. So now we must take tea. But before that, we have to give memento. For tea, we will have not to go anywhere. Tea will come here. That will come. No, they will go there. Okay. But they are saying that 5 minutes. Right? So just after giving this medal, I request Professor Suresh to please present the memento to Dr. Abhishek Srivastava.
Shall I come down there? I know that I am there.
Thank you.
Twice.
Why?
But it's the Karnataka.
State.
State and
This is third I'm getting from the state this year. Yes. So how was the talk? As usual. Yes. As usual. Yeah, please, all of you come. Please join. Good afternoon. Good afternoon, ladies and gentlemen. And now I have a very pleasant job. I'm truly honored to chair this session. I don't think I have to introduce Professor Sandeep Kumar. He is well known in the field of discotic liquid crystals. नहीं, वो तो है sir, मेरा duty है. I must tell you that you heard my talk and it's because of him. I first started my career as a postdoctoral fellow with Professor Sandeep Kumar. I am here because of him. Sir Guruji, I'm going to start. Your introduction down. He is one of the outstanding chemists of the, India. I think all of you agree. And he's a stalwart in the field of discotic liquid crystal. His achievements, it cannot be read. It goes on, goes on, goes on. So better I, hand over the mic to him. Sir, dais is yours, you may start. Thank you.
Okay, thank you, Channu, for the introduction. And at the outset, last that I really express my sincere thanks to my beloved friend and colleague Raj and Manjula for really inviting me here. And so let me start, I think, because I think we are already very late. And I think I remember some of you probably remember my last year talk, and the last slide of my last talk. So in this talk, actually, I don't have much, because last year I have given the lifetime achievement talk, where I presented almost everything. So this time, Raj asked me, I say I have already presented everything. Lifetime means I've given everything. What I will talk it. So, and in the last year talk, some of you remember the last slide, where I have expressed my desire. Remember? Some of you? Some of you. Where I have told that I am probably taking sannyas. But then Raj and Manjula told that you can take sannyas, but maybe after attending this one. No problem. So I say, okay, I will come for one day, and then again start thinking, should I take a sannyas or not? So anyway, let's start the talk. I think all of you are liquid crystal community, and I don't need any introduction. I will come directly to the discotic, which is my beloved subject. So discotic, I think liquid crystal as such are known since everybody knows 1888 aromatic liquid crystals were discovered, and till 1977 it was common belief that they are only rod-like molecules. So in 1924, Forlander, a German really excellent chemist, had imagined that not only rod-like but disc-like molecules can also show the liquid crystal behavior. But of course, the molecules, it is the same molecules which now are well-known discotic liquid crystals, but sometimes, the ingenious missed the point. So he missed that he used the same molecules but without chains. And he concluded that this type of molecules really do not show any liquid property. So it happened sometime. But then the research continued, and during the 60s, people know that about the carbonaceous mesophase. What is carbonaceous mesophase? When you really heat the coal tar pitch or any pitch to make the graphite products or something. They knew that it passes through a liquid crystalline state or phase, and the property of the final carbon product depend very much on the nature of this phase. So they knew that this is a disc-like molecule which really shows the kinematic phase. So it was known that people were interested to understand what type of, because this is a polymeric and complex mixture, it was difficult to understand. So people were really interested to know, to have a well-defined system which can show this type of phase. And this discovery or this curiosity finally resulted in 1977 when Professor Sadasiv and discovered that this benzene type of hexaester gives the liquid crystalline properties we know the despotic liquid crystals. I'm really fortunate to work with all the three, so Professor Sadasiva, and very lucky that Professor Trace is still with us and very active actually. He may be looking you people very tough person, but particularly for the students, I will tell he's very friendly, catching. He has a huge knowledge. So you just take the advantage of his knowledge to really learn that will be useful in your life. So generally, whenever you have tea time, lunch time, tea time, just catch. He really gives you a lot of tips of successful life. Okay, so this is what the things. Despotic, you know, is 1977, September 1977, and after 2 years or so, it will be 50 years. And so exactly in the September 27, our colleague Dharmendra and Achal, they are planning to have a special meeting on the golden jubilee of despotic liquid crystals. So be prepared, note this date, and be in touch with Dharmendra and Achal for this great meeting. This is going to be a really very good meeting where the proceedings will be published in the crystals. So be prepared from right now, starting your work. Come out with your good work for this conference. Okay, so let's come to the discotics. And before going to the really discotics, let me give one slide on the benzene because that was the first core, discotic core. And this year we are also celebrating the 20th anniversary of the benzene. It was discovered in 1825, 16 Unity 25, a beautiful molecule, benzene. And this was really a discovery where Michael Faraday, he was trying to understand what is present in the oil. Because in those days, oil was used to do the lighting, burning of oil for the lighting system in 1825. And this was oil, not this oil, crude not our what oil we are using. This oil was taken from the whale. Whale oil was available and people used to burn this oil to get the lighting. So when they were burning this oil, there was a problem of the efficiency of light intensity. And this is where this problem was given to Michael Faraday, and he isolated the benzene. And of course, it took long time to establish the structure by Kepler. I think those who are chemists know very well. Oh, it is a different story. I will not go into details. But after that, we know that benzene is everywhere. Earlier, benzene was as a solvent. We as a student used to wash our hands. And from there, it becomes carcinogenic and all the serious problems with the benzene and so. And benzene is everywhere, particularly in the dye, in the medicine, in the everywhere. You can say it's maybe a dinosaur or whatever you guys say. But all the plus points depend upon you can take the plus point or you can take the minus point. Benzene is carcinogenic in medicine, everywhere it can. Okay, let me come back to the discotics. So just after the discovery, after about 6 months or so of the discovery, French group basically discovered that trifling hexaester gives also the discotic crystals. And in the very beginning, so people really focused on trifling because these Viscotic, after vanillin, I don't know why, but not much work has been done on the vanillin or other viscotic. But this has become really you can say, workhorse. Everybody was working on the trifle viscotic liquid crystal, and roughly 30% of all viscotic liquid crystals are based now on trifle. So in the beginning, actually, it was not easy. Actually, it was synthesis is starting from the dimethoxybenzene to hexamethoxybenzene, hydroxy, and then making the ester and ethers. And this was really very dirty. And I started synthesizing this molecule in 90s or so, and I entered that viscotic field. It's very, very dirty work. It was really like isolating uranium from full surface tab, a very dirty black chemistry, what you can say. But then we and Gordon group, as a chemist, really worked for the one-step synthesis. I mean, dialkoxybenzene to directly hexalkoxybenzene in various regions like iron chloride, vanadium chloride, oxygen chloride, etc. This entire things had changed. Now you can make this hexalkoxy in kilograms without any problem. In a few minutes, in fact, you can make the hexalkoxy viscotic. It's very in a large amount. So this really changed a lot. So we have developed many reagents for this, and that I don't have the time, but you can find in many of my reviews. So in the first phase of viscotic liquid crystals, people were really looking on the symmetrical model. So you have the disc like this, and then you are symmetrically substituted with alkyl chains, aliphatic alkyl chains by ester or ether, thioethers, etc. This is the phase which happened in the very early. People were just looking a new core because it was already reported by some of the great scientists that if you really have less than this 6 chains or something or no, you break the symmetry, you will lose the crystalline property. So people just working on the system, you choose a disk, somehow you make a disk, and some symmetrical characteristics. So in the second phase, when we were looking to change the properties of this like molecule, particularly when I was working with one of the French ladies to look the energy migration of these viscotic liquid crystals, he was interested in the fluorescent viscotic, and trifluorine was non-fluorescent. And this we concluded because of the symmetry, so we wanted to correct the symmetry. This is where the functionalization of viscotic starts. So functionalization can be first, if white is required, basically we need the functionalization to change the mechanical property so that we can make the polymers, etc., to have the more rigid system, or we can change the electronic property. So to change the mechanical property, basically we have prepared the lot of hydroxy compounds. So if you have the monohydroxy, dihydroxy, we can convert into dimers or ether polymers. So large number of these materials have been prepared by my group as well as other groups and these things. And the second phase was to change the electronic property, because most of these properties they don't have the polar nature, to change the polarity of the systems or to including the fluorescence and all these things. We have to change the electronic property. So to change the electronic properties, one of the easiest ways we can nitrate this molecule. So when we were working to improve the fluorescent properties, of course, we have gone to a very complicated nitration. We have observed that this nitro group goes here. But the simple technique is that you take the hexalkoxy, you just put nitric acid and you get basically a nitro derivative. Then we developed the different techniques to get the dinitro, etc. So this is the way we can change the electronic properties. Okay, so the first annulation, heteroannulation of this trifluorine, which is a title of my talk, it started actually in around 95. So that if you have the nitro group, we can reduce the amino group, and then if you diazotize, it will automatically get a nitro annulated trifluorine. So this change completes the property, because this compound is a colorless, the trifluorine compound is colorless, and this becomes almost red color. So absorption, emission, all properties, thermal behavior changes because of the presence of the diazo group. So this is was the starting of a core annihilation of titanium discovery. Then obviously, what we are interested to make really have this, we are interested to have a molecule this, which is having a nitrofunctional group and a hydroxyfunctional group. So that this can be used to change the electronic property, and this can be changed to in the mechanical property, so that we can make the dimers, oligomers, and polymers. So we prepared this material and prepared a lot of dimers, oligomers, and polymers. These three items. I'm not talking to today, but what actually happened. And one day when we were doing one of the post of money, very intelligent boy, he was making this compound, but he really got a black material, which we characterized, although that time he was very frustrated, what he was talking about the frustration fact. Because we are looking this compound, and what in the evening when he prepared this compound, but the next day morning what he got only a black material. He was crying. He just came to me crying. After I got only a black material, don't know what happened. Probably some colleague has put some sulfuric acid in this. And so like at a young age, we do all these tricks actually. We don't like it. So if you have something, and we thought, okay, put some sulfuric acid, it will charge everything, all these things. So he said something has happened in the night, and he has just a black material. So I said, what is this black material? I immediately asked him to go to the AIST to take the NMR. We didn't have NMR that time. So we just took the NMR, and from NMR, I immediately realized that what have a oxidized project, that is a diphenol. And this diphenol really changed the entire, because, so then immediately to confirm that we have the diphenol, of course it's confirmed by the NMR, but to confirm this, we immediately coupled this with a diamine, 1,2-diaminobenzene, which is molecule, and we got a phenazine. This is called the phenazine. So phenanthrophenazine, this is phenazine, and this is phenanthrophenazine. So phenanthrophenazine. And this was another first example where we got the phenanthrophenazine for trichine got a liquid crystal, a beauty. That a red color compound, beautiful emission, absorption, and very different from thermal behavior. Well, this is another example which we oxidized at this position and again got different phenanthrophenazine. I will not do this. Okay. After that, obviously these phenazines, what these phenazines we have is a very high temperature. You can see here, 223 and so, because of very high conjugation and no substitution and in the phenazine part. So obviously any chemist will say, oh, you can do the substitution alkoxy or any substitution, you can reduce the melting point. So idea was to basically make the alkoxy derivative so that we have a better melting point, isotropic temperature. But students were not interested to make the dialkoxy diaminobenzene because of it's complicated and all these things everybody wants a quick result. But it took really almost like you said 20 years. In 18, so Gowda was an interesting student. He basically made this dibromo diaminobenzene. This was the key. So once you have this dibromo diaminobenzene, you can react with the same diethyl ketone and you will get a dibromo phenanthrophenazine. And once you have the dibromobenzene group, you can easily replace with a diol. So this becomes very, very interesting and very low melting point, etc. I will not go much details because we are already late, but I just to show you some slides that they are beautiful colored compounds on the columnar mesophase, very good properties, very different characteristics. And more important, I think Dharmendra has measured the charge mobility. Probably it's not measured, but it's like a classical charge, 10 to the power minus 3 centimeter square per volt second of the whole mobility measure. So they are beautiful compounds. Then obviously you have a bromo compound. So we thought to attach the acetylene group. Sonoga company in the country, very important. And one of the reasons for doing these things are also was that because these groups are not planar. And we have done a lot of chemistry and we have discovered groups which are discordant crystals from that. So if we have this non-planar group, we have thought that we may get some that is called enzymatic. So this was one of the reasons we replaced the bromo with the diacetylene, and we prepared this compound, but they give only columnar mesophase because 2-acetylene may not be sufficient. 5-pi interaction is more important. They give only the columnar mesophase, and more important, besides good absorption, emission, and property, they give very good non-linear optical properties, very good analog properties because of the polar groups present in these compounds. Well, this is all the things. Then obviously, then another girl, Alka, prepared the dialkoxy because the dibromo group, which I have shown, one can easily think to replace with the dialkoxy, but that was not possible technically. So what here? To make this dialkoxy group, dialkoxy diaminobenzene, she did a very different route, prepared the dinitro dialkoxy benzene, and then replaced the ditro group, which is little unusual reaction, but replaced this nitro and this diamino group, and then test this dialkoxy diamino group with the dialkoxy derivative, which also gives the beautiful liquid crystalline property. This is again the charge carrier mobility measured by Hermann, gives 10 to the power minus 4 centimeters per volt second. Okay, then so again took the same diketone, and this is a commercial benzoic acid, diamino benzoic acid. So you get the attached this phenazine, but now you have the two isomers. One COH group in the top, and the COH down. This commercial. 2 minutes only. Okay, so then I think I have to go. I will not go much in details. So we prepared all these derivatives. And again, I think these are the very good. So we have prepared the again mononitro monothio group. And the most important thing is this, that these are basically regioisomers. So in the history of this liquid crystal, regioisomers have not been isolated. So this is first time, and now of course Achal is also doing the separation of the regioisomers. We isolate the regioisomers of the same compound. And we found that, like in medicinal chemistry, stereoisomers or regioisomers have totally different properties. So here also, in material science also, these regioisomers have a very different thermal. This is very important. So when we are making a mixture, that may not be true melting point and of that different type. This is very important. Well, I think I will just close my talk. This is another compound, heteroannulated triphenylene discordant liquid crystals, and we have prepared many compounds with peptide Spengler reaction, and one of the basic idea of putting the nitro group, so that because this is electron rich part, and this is here we are putting the electron deficient part. So idea was that such compounds may show us MB polar charge. This was one of the most important ideas with this we have started with materials, and we indeed found that this type of compound and all other compounds shows very good electron. This is electron mobility, this is whole mobility. So this compound was both. So these are the very interesting compounds which have the, I think we just close down the talk because of all these. So just the serendipitous discovery of the diketones really gives a large number of the triphenylene derivatives having the huge nitro or oxo group. And these compounds, as expected, very wide temperature range, very good emission, very good emission and absorption, and give both ambipolar charge carrier ability, both electron and proton. So these are very, very good, and most of them are stable at room temperature. So this is what actually we are looking for a semiconducting property of it. So they are very interesting. We have not done this can be extended to many. Now my group is not very active, but yeah, those young chemists who are doing, they can really continue with this work. And they will be very useful for solar cell, particularly light emitting diodes. They are right. Doing. Okay, so with this, I think I will close my talk. Thank you very much. comment.
Hello. We have time for just one question, short question. Anybody? Just one question.
Not many comments. Okay, yeah.
Thanks sir, for a very wonderful talk. As you mentioned in the last few minutes about the whole mobility of these films, right? So we, as you know, we have tried to do together with the Dharmendra, try to make this kind of film for the quantum rod LEDs.
Yeah.
The basic problem what we face is that we need to make a film which is aligned with the vertical columns.
Yeah, correct.
And it is kind of very difficult when you do the spin coating, or so you need to use either Lungberg Blodgett films or something like that technique. So is there any possibility to arrange this kind of columnar phases just by using inkjet printing or spin coating or some self-assembly processes which can do the same thing for a large area?
Well, obviously, I have not tried myself, but people say that alignment in this direction, homeotropic versus periodic, is people say is very common actually. You just need annealing of the, put it on the surface and anneal the edge, very slow annealing, extremely slow, whatever possible annealing, 0.1 or even less. So this annealing will give you the homeotropic alignment. And of course, homogeneous alignment is very difficult, but then there is some method, some syringe method, pulling of the molecules in one direction, which can be tried. But for homeotropic, it looks like a reasonable, and in many cases we have seen that it can be done with very
slow heating, yeah. So we tried to do that, but we failed somehow.
Extremely slow.
Yeah, extremely slow is a big problem.
Yeah, that could be a problem. This can be done. Oh, good, sir. Good. Thank you very much.
Please join me in giving a bigger applause to Professor Sandeep Kumar, who is working in Sarda University now. Yeah. May I request Professor Jagdish Vij to honor him? Yeah.
It's a very pleasure to receive this thing from such a really great scientist and probably the senior most person now. Thanks. Big applause. Good, sir. Thank you very much.
Yeah, ladies and gentlemen, we have yet another great speaker and distinguished scientist, highly accomplished person. He has about 340 publications, guided about 18 PhD students, and though he is in foreign, but he makes sure that he invites Indian scientists or Indian students in his lab. He has made it, sort of a practice that he would invite people to work in his lab. Sir, that is yours, and 30 minutes. Thank you. Big applause to him.
Can you give me a microphone? Advanced, yeah, this one.
This is for advanced.
This is for
Going back, this is for
advanced. Well, I thank the organizers, Professor Gupta as well as Manjula, for inviting me. I thought, I must come. I visited here 3 years ago, and I see the last 3 years there has been enormous development on the campus. When I was a student, I think it started in 1964. I did my MSc in 1965, that is 60 years ago, and I contemplated to do a master's course here in electronic engineering, but for some reason it was not possible. But one of my colleagues did his master's, and through the UPSC, he was appointed a lecturer in electronic engineering in Punjab Engineering College. And after 3 years, the Punjab Engineering College said he doesn't have a degree in engineering, so he comes from physics, so he should not be retained, he should be thrown out, and the person left for the United States. So I think in India we have a very sort of a limited view of degrees and so on. And abroad it doesn't matter. I always worked in engineering department, having a degree in physics. And there are many chemists working in physics. There are many physicists working in chemistry and so on. Okay, so I just want to talk about this ferroelectric pneumatic phase with wide temperature ranges. Now, we listened to Professor Srivastava talk on ferroelectric schematics and the applications. But if the ferroelectric pneumatics may be much more useful because they combine fluidity with ferroelectricity, whereas schematics are mostly solids and they do not, they're not that useful, although Professor Srivastava indicated that he has made many devices. Now, how about this ferroelectric pneumatic phase? This has been discovered only some 8 years ago. So, well, pneumatic phase is known for maybe 150 years ago, but the ferroelectricity in the pneumatic phase was never discovered. So I just want to say that this work arose out of a collaboration between us at Trinity College Dublin and the Queen University of Belfast, Northern Ireland, and the Kent State University, Mike Fish. So I just want to, what is these ferroelectric pneumatics? So, well, they were not observed as a ferroelectric phase until 2017, though Max Born had predicted it as long ago as 1960, that similar to paramagnetic to ferromagnetic transition, a transition from the isotropic to pneumatic phase should exist and be paraelectric to ferroelectric. What are the criteria of ferroelectricity? You must have a spontaneous polarization of the order of few microcoulomb per centimeter square. The polarization can be reversed by changing the direction of the electric field. And usually there is a hysteresis between polarization versus electric field and large dielectric permittivity. So the susceptibility is polarization divided by the electric field, which is epsilon -1. So if P is large, the ratio of P to E is very large, very small p, then permittivity should be of the order of 10⁻³ to 10⁻⁴. So what are the various forms of polarization? So if you apply electric field, polarization increases linear with respect to the electric field. So that's a linear polarization. If we have some kind of a nonlinear polarization, initially the polarization jumps up and then saturates, or we have ferroelectric polarization whereby the polarization rises as a function of the electric field. When it's reduced, there's a remnant polarization, and then we have to reverse the field to bring that polarization to zero and in the opposite directions. So in solid, especially in perovskites, ferroelectricity is commonly observed, like barium titanate is a common example. And it has application in memory chips used in ceramic capacitors, sensors, and memories. But if that ferroelectricity can be given to fluids, or especially ferroelectric pneumatics, then we may have a range of applications, and so that is the reason why we have been interested in it. So what is this ferroelectric pneumatic? Over a century ago, Max Born predicted an existence of ferroelectric pneumatic phase NF with this symmetry C infinity. Now, normally these pneumatic liquid crystals, you have head to tail, so they head to tail, they are equivalent. So either, but the molecule is looking from head to tail, and when they combine together, equal number of molecules of head are in one direction, and equal number, almost equal number of the tails are in the opposite direction. But here in the if that is possible, then all the heads would combine together and the tails would combine together, and the polarization would be in a single direction. Now, in a book by Chandrasekhar, it's written that the Max Born theory is incorrect. And so obviously nobody believed in what Max Born had said, but now people say that what has been discovered is not really the phase that was predicted by Max Born, and it is something new. So there were, in 2017, there were two materials that were synthesized. The first one was by Mendel, who worked as a research student in John Goodby in New York University in England. And the second was this, the Riken sector of emergent technologies near Tokyo. So they call this DIO. This molecule has dioxane at the end, this one, dioxane, and DI stands for dioxane, but then there are esters and a lot of fluorines and so on. And this was by Nishikawa. So really the discoverer is this Japanese group, Nishikawa, etc. And although this was discovered for RM734, but for the next 3 years, they produced many papers, and they said it was a splay pneumatic, not a ferroelectric pneumatic. So it's only 2020, Noel Clark and his group showed that this is really a ferroelectric and not a splay pneumatic, as had been characterized in a number of papers published from 2017 to 2020. Whereas this is a real discovery of DIO molecule, and it shows a pneumatic phase over a very wide temperature range. For example, this NF phase is from 40 degrees centigrade to 64 degrees centigrade, 22 degrees centigrade. So I just want to see what are the various forms of polarization, and especially the characterization, ferroelectrics, paraelectric, super paraelectric. So if you we have normally ferroelectric, the polarization increases, then saturates, then reverses back, so there's hysteresis. In the case of super paraelectric, there's no hysteresis, polarization rises, saturates, and so on. And then there's a paraelectric where the polarization is small and it's a linear rise. So this red bit is the energy stored, and this green bit is the energy lost. So if we want to have some device and we want to have, you see, energy storage efficiency defined by UE divided by UE plus U loss. So UE is the energy stored, which is here. So ideally, we should have a super paraelectric, which no hysteresis, but a lot of energy storage, no energy loss, and that would be a real sort of a material. So while designing nonlinear dielectric for energy stored, the goal is to maximize UE while minimizing the energy loss from this point of view, the hysteresis-free, the super-paraelectric materials are more effective for electric storage, ideal materials for supercapacitors. Now, what are the criteria for the formation of the pneumatic, ferroelectric pneumatic phase? They were given by Lee et al., and they work in South China Advanced Center for Soft Matter Science. So actually this Guangzhou, so China is investing a lot of money now in liquid crystal, and there are some people who are the heads of that from Japan. And what are the criteria? The criteria must be the molecular dipole moment should be of the order of 10 to 12 dBi. Normal molecules how disappear. Oh, that's so the 10 to 12 dBi. It depends on the length of the molecule. It depends on the geometrical aspect ratio of the molecular structure, ratio of the length to the breadth, the angle that the resultant dipole moment makes with the long molecular axis, and the spatial distribution of the dipole within the molecule itself, and magnitude of the resultant dipole moment. This fifth criteria was given by Madhusudana in a paper published in PRE 2021. And I think we have proven, and many others prove, that his criteria is the best of criteria given by Lee et al. So there are 4 examples of molecules that have been discovered to display the ferroelectric pneumatics. Only 4 from 2017 to 2025. So the first one on the side is DIO, which I described already. This one. And the next is this RM734 of Mendel compound. So he had nitro group there, but it is normally a poor chemical stability. Now then the third one is this UUQU4, and I don't know how the chemists name it, but here this is the central part with the carbon, 2-fluorine, oxygen, and so on. And it's very difficult to synthesize. And then the last one of this is NEC. So there's a methoxy chain, and so on, and nitro group. So what the chemists who synthesized it, which is Saima Ansari and Peter Knipe and Queen University Belfast, is they took this one and they used some of the properties of that to synthesize several compounds. And I just talk about 3. Saima, and SA stands for Saima Ansari, and she's from India, in the state of Uttar Pradesh. But she's a very good chemist working with Peter Knipe. So he has, so it depends on here, the end chain here in the RM734 or any end chain, this one end chain. So it should not be very long. It should be either ethyl or propyl. Then you would have these nitro would be replaced by fluoro as or cyano group. And here we'd have propyl group, 1-fluoro-ortho-CN. So really we modify this to put a cyano here, maybe fluoro here, and so on. And so this is the symmetrical accessible thing. So we can change these, which CN is highly fluorinated, and we can change something here, and so on. And that way, we make materials. So in the case of these 3 materials, we would have wide temperature range of more than 100 degrees centigrade. So why the discovery of ferroelectric phase now? in the period up to 2006, there was a large interest in the biaxial pneumatic phase. Many people were studying it. And what is a biaxial pneumatic phase? It has the refractive index in the three directions must be different. And the biaxiality is delta N2 minus delta N3. So some people said biaxial pneumatic phase exists. Some said didn't. Even Chandrasekhar was very interested in this biaxial pneumatic phase. We showed that there is a biaxial pneumatic phase, and we could really measure the biaxiality, and we showed that the biaxiality is slightly larger than the experimental error. So many people miss it if they don't perform the experiment correctly or they don't have the right instrumentation and the others. So even if the biaxial pneumatic field is a reality, which we proved it was a reality, that the biaxiality is so small that it cannot be made use of in any useful device. While studying these biaxial, we by accident came across, when studying biomasogens, and we found out that there is a spontaneous periodic deformation, that these materials show pneumatic to pneumatic transition. Prior to that, people had studied these biomasogens, but they showed that they were smectics. But actually, we found that they are not smectic, and we published in 2010. And we characterized this new phase as splay pneumatic. And that was incorrect because later on modified to be a twist bend pneumatic phase. So several people following this paper started studying pneumatic to pneumatic transition. Many groups in America, in Canada, in Japan, and so on. And so we could make the initial discovery, but actually we couldn't realize it because obviously we needed equipment, we needed manpower, and the funding has really finished. So we collaborated with Leventrovich. We told him that they have a sort of a helical structure, but the pitch of the helix is in nanometer, not in micrometer. So they will have to have special technique to measure it, and they had it, they did it. And in the meantime, these people, Kasteri et al., with the Luckhurst as the leader, found out about our work, and he restarted studying the biomasogens, which he was doing it anyway long time ago, and he named this new phase as the twist bend pneumatic liquid crystal. So it turned out that Ivan Dosev had predicted this phase in 2001, or the helical pitch he predicted was in micrometer, but now it turned out to be nanometer. So many people say that this phase that has been discovered is not really the one predicted by Dosev, and it is something new. So what is the reason for doing that? The reason is that because there were many pneumatic to pneumatic transitions, so many people got interested in studying new compounds and studying these pneumatic to pneumatic transitions. So they discovered many phases, temperature-induced and field-induced new phases. So when they were doing this kind of a thing, they also turned out that when they're studying pneumatic to pneumatic, so there is something new happened. And this was the discovery of the ferroelectric pneumatic phase and the splay pneumatic phase. So as recently as early this year, we had these materials. Well, this is DIO actually. So this was replaced by Georg Mahal group to a pyridine, and this fluorine was reduced to CN. So they increased the dipole moment from about 10 dBi here to 10.4 dBi to 14.8 dBi. And normally one would expect that there will be ferroelectric pneumatics, but actually they turned out to be super parallactic pneumatic phase that I described previously. So there's the existence of the ferrolactic pneumatic phase doesn't only depend on the magnitude of the dipole moment. It also depends how these dipoles are distributed within the molecule itself. These are large dipoles, but they're distributed within, and that was the concept given by Madhusudana. And this was the fluorine replaced by the cyano group. Now, what we have done, I just summarized it, that we have these three materials, SF-140, 152, and this is the ferroelectric pneumatic phase. So from 50 degrees to 140 for this compound, and for this compound, it is below room temperature. At least we can measure down to 20 degrees centigrade, and below that it may also be ferroelectric pneumatic, and it is ferroelectric under 120. So that is nearly 100 degrees centigrade. And then this compound here, which we have SA153, so it is a ferroelectric pneumatic from the room temperature to about 90 degrees centigrade. So what is this is the polarization measured. So this is about 6 microcoulomb per centimeter square. And then we study transition from ferroelectric to isotropic. So either it is second order transition, in some cases it's also a first order transition. So the usual sort of factorization, that with the DSC, we can do it under heating and cooling, and some materials only show these ferroelectric pneumatic under cooling, others show both under heating and cooling. But the transition is pretty large from the change in the enthalpy is pretty large, and these are the values of the dipole moment. They're all large, but tend to approximately 12 debye units. So the polarized optical microscope. So what is the criteria? How do we find out is a ferroelectric pneumatic phase? The usual studies, we use these textures, and we have, say, anti-parallel rubbed planar cells. We get these chiral domains. So what is a chiral domain? That these molecules are achiral, but the domains are chiral. And so what is the cause of this chirality? So previously, it was thought that maybe it is the symmetry breakdown or breaking down chiral symmetry, or there may be some other reason of twisted domains and so on. But so the chiral domain, when we do the experiment, we have cross polarizers, then we uncross it in one direction, then we cross it in the other direction by a certain angle, and there's exchange in the colors of the domains. So green becomes dull sort of a thing, this becomes red. So this, for example, change the colors. So exchange of colors, and the angle we have to optimize, etc. And we can also measure birefringes. Birefringes in a ferroelectric pneumatic phase is much larger than in a usual pneumatic phase. So this another material, again, large birefringes. So this jumps from isotropic to So I skipped some of these. And so, for example, from the pneumatic phase to the ferroelectric pneumatic, there's a large jump in the birefringence. And if we do the experiments, one surface rubbed planar aligned cell, we sometimes gets these chiral domains. So in the dielectrics, well, we can study both under planar alignment and homeotropic alignment. For example, this is doing under planar cell, large permittivity of the order stands for 3. Then we can analyze. So we have a ferroelectric mode. We have a ferroelectric mode of P3 here with a large dielectric permittivity and so on. I'll skip some of these slides. So the main criteria of ferroelectricity is existence of the spontaneous polarization. So we apply a triangular waveform at different temperatures, and we see if there's a switching of current, and that integration of that will give rise to spontaneous polarization. So this is the polarization in microcoulombs. So this is as large as the solid ferroelectrics. So this is something new that, pneumatics can display as much spontaneous polarization as these ferroelectrics, solid ferroelectrics. So in this case, when we are pneumatic, we have some kind of a second order transition. So the pneumatic partly becomes ferroelectric and so on. So the origin of chirality is either the triggering of the de-racemization of a chiral molecule, or twisted domains, or twisted molecular structures, or combination of polar interactions, depends on elastic constant, twisted domain. So then you do the X-rays. You see here, then these are despacing. So the maximum despacing, which corresponds to the length of the molecule, decreases in the NF phase. So the NF phase, the maximum despacing, that is the length of the molecule, really decreases from the pneumatic to the NF phase. And one can explain the existence of these chiral domains by the spontaneous polarization, and in the NF phase and the N phase, no polarization. So the N director is the same as the minus N director. In the usual pneumatic, there is an NF, they are not equivalents. So the mechanism to explain the existence of these chiral domains. And the simple one is, well, if we have some rods and we bind them and we rotate them in one direction, then the opposite direction, then they are chiral. So again, these X-rays give rise to this reduced length despacing. And we see this people who do X-rays would realize that this X-ray pattern is different from the ordinary pneumatic phase. So the conclusions are the NF over wider temperature range of some 100 degrees centigrade, and this includes room temperature, and RM374 structure can be modified by chlorine and CN substituents. So this structure property relationship can be developed. The origin of the chirality needs to be investigated, and the ferroelectric mode is observed in parallel planar aligned cells. So I must thank, this is work is carried out by 3 groups, ours in Belfast and in Kent State, and funded by US Ireland funding by SFI in Dublin, NSF in the United States, Northern Ireland Agency in Belfast. Thank you for this.
Thank you, sir. Thank you. Thank you very much. In the interest of time, one quick question, just one. Anybody?
So thank you, Professor Vij, for a very nice talk on ferroelectric pneumatic, which is, of course, a burning topic among the liquid crystal community. So, in fact, I would have one comment and one question. So, comment is that not only the 4 ferroelectric pneumatic liquid crystal compounds are known, there are very several till 25. Obviously, the basic compounds came from RM734 by the Mendel group, and second one DIO from the Japani group. And very newly, the group of Professor Kula, they are very actively, and the Merck has already developed room temperature ferroelectric pneumatic mixtures. Obviously, they didn't disclose because this is under confidentiality things. I have a question regarding the dielectric, very huge dielectric constant. So basically, as Clark Group recently showed that this very huge dielectric constant is not coming due to the material, there is influence of the alignment layer.
That's wrong. That's incorrect. And I think Noel Clark has made a terrible mistake in the paper that is published.
So
he doesn't know that the displacement current that is considering is not the same as the conduction current. Displacement current never leaves the capacitor. He is saying that it is leaving the capacitor. He's confusing the two things. In that paper is totally incorrect.
Okay. Okay, maybe we can discuss later because he also published several consecutive
Yes,
papers
I know. He says that he has developed models for electro-optics, that's fine, but that particular model cannot be applied to dielectrics. There's no way that you have a large spontaneous polarization, the small electric field, there's a huge change in the polarization. There has to be a very high dielectric. And he says that it's very small.
Okay, thank you.
Thank you very much. Thank
No.
I am here because of.
Yeah, you took care. Thank you. Thank you. One other.
Now we break for lunch. Okay, only 30 minutes. Otherwise, I'll call.
You have a call. Thank you very much. Huh?
known figure in this field, and more biography can be seen over there. So I would now request Professor Needs to come and start the talk.
Good afternoon, everyone. Welcome to my presentation. I'm happy that you are well in time. I know there was just been lunch and you have to hurry. There's not too much time. So I'm very happy to be here. So it's only my second visit to India, and the first one was 20 years ago. So I'm in Hong Kong University of Science and Technology, HKUST, which is a very nice university. Before, 2 years ago, I moved there. And before I was a professor at Belgium, at Kent University. So today I would like to tell you a story. I think you have already had a very nice overview of different components related to liquid crystals. So my story is a bit different. I would like to talk about photo alignment. Okay? So that can be combined with many materials, with many kind of components and applications. So the outline of my talk is shown here. I will first talk about the principle of photo alignment, and we will see that you can do that with many materials. And then towards the end, I will also talk about chiral liquid crystals and also the photo alignment of chiral. Okay, what is the principle of photo alignment? Well, you need a special material for that is photosensitive. So, and we spin coat a thin film of about 20 nanometer on a glass substrate, and it's made of azo dye, for example, SD1 or brilliant yellow. And if you do that and you illuminate that material with linearly polarized light, then these azo dye molecules can react to that. And there are two options. When the polarization is parallel to that molecule, then you have a cis-trans isomerization, because there are here the nitro groups which can isomerize. Then you change the shape of the molecule, and if this happens many times, then in the end the molecule will find a position where it is perpendicular to the polarization of light, and there it will be stable because the light is not absorbed. Okay? So we can realize a homogeneous alignment when we illuminate everything with the same polarization. We have a homogeneous alignment of the photo alignment material, but we can also do something more complicated. We can also illuminate with an interference pattern. And that's illustrated here on the next slide. So if we use the interference of two circularly polarized beams, we have two circularly polarized beams, and the electric field of those beams is rotating clockwise and anti-clockwise. And if you take two vectors that are rotating in opposite direction, the sum of these two vectors is just a vector that is going in one direction. So that helps us to define in which direction we have the polarization of light. And then when the electric field is in this direction, the molecules will orient perpendicular to that. But you see, depending on the phase of these two, if they have different phase, then the orientation will also be different. So here, in this situation, when we have an angle, we will have different orientations. Now, you can do that with two plane waves, but you can also do that with two spherical waves. Or you can have one beam from the bottom and one beam from the top. You can have here a converging beam. Here is a converging beam and a diverging beam. You can let them interfere. So you can have many different types of patterns. So we will come to that later on in my presentation. Okay. Slides. Yeah. Next slide shows the fact that after we have done this procedure, for example, we have made a rotating pattern where the director is rotating, then we put a thin layer of liquid crystal on top. And there is an interesting principle. If we use a thin liquid crystal film, that is exactly the half wavelength, because we know half wavelength means that the phase delay between two modes is just half a wavelength. We know a half-wave plate in optics, that changes the polarization of light when you have incident left-handed circularly polarized light, and you go through this half-wave plate, you create right-handed circularly polarized light. Okay, everywhere. However, there's something else. The polarization, so the polarization is right-handed circularly polarized, but depending on the azimuthal angle on the surface, that also has an effect. So if the azimuthal angle rotates, as shown here, so the angle phi here increases over the x direction, so then there will be a phase delay. That phase delay, the result of that linear phase delay as a function of the x position, will make the light tilt at an angle. So the plane wave that comes in like this will be tilted over a certain angle, and the value of the angle is given by the wavelength divided by this period of the grating. Now, this efficiency of this principle is very high, so we will have close to 100% of the light that is diffracted in one direction. So it's a type of diffraction which is very different from diffraction from such a biphasic pattern, which has only 41%. Okay, so with that, you can make very nice diffraction gratings where all the light is going in one direction. If you have unpolarized light, then the unpolarized light will split in two, because left-handed and right-handed will feel a different difference. This principle has been used by companies. So imagine Optics, which has been acquired by Meta and Beam Corporation. They make such holographic or diffractive devices based on it. Okay, so we have also tried that in an experiment. So we worked together with a company that was making lasers for projection, like cinema projection display. If you have typically, these are very powerful lasers. And because of the high power, the lasers have to be separated to cool them. And then you would like to have the two laser beams closer together because your optical system can be made small. So how do you bring them together? Well, you can put here two gratings to tilt the light, and then two other gratings to make it parallel. And if we do that, so we tested here with a simple helium neon laser, and you see we start from a distance of 2 centimeters to a distance of 2 millimeters. Now, you can also do that with very powerful lasers, which on the order of 1 watt. And liquid crystal doesn't have a problem with that because it's very transparent, so nothing is absorbed. It still works for high power. Now, there is a problem in this nice principle that I showed, and we see 100% diffraction efficiency. There is a limitation, and that is the angle over which we can do the diffraction. Why is that? Well, if we have liquid crystal and we have a rotating pattern, then if you make that thicker and thicker, or if you have a half-wave thickness, but you make the period smaller and smaller, then the liquid crystal has to rotate faster and faster, which means a lot of elastic energy. And at some point, there is a threshold, and the liquid crystal will tilt out of the plane, because rotating like this is easier than rotating in the plane. So we see, we can measure that, and we can also simulate that if this period becomes smaller, we have an out-of-plane tilt. And if the period is even smaller, then we have an even more complicated pattern. And you see the diffraction has now many orders, not what we want. However, we have used a material which has a delta epsilon that is negative. So you know, these molecules, they like to be perpendicular to the electric field. So in this way, the molecules that were tilting out of plane, we can bring them back in the horizontal plane and recover the high efficiency. So in this case, we recover by applying an electric field. We have this orientation of the director, and we have again almost all the light in one single diffraction point. Okay, now instead of using this simple pattern on the substrate, in a spin-coated film or cell, we can also make grating one direction on the bottom substrate and in the other direction on the top substrate. If you do that, it's a bit complicated. The liquid crystal doesn't know exactly how to orient, but liquid crystal is a liquid, so it finds a situation with the minimal energy, and that situation looks like this. So remember, at the top and the bottom, everything is planar orientation. There's a variation, but everything is parallel to the substrate. Now, to relieve this variation in two directions, the liquid crystal automatically orients perpendicular to the substrate. And in this case, we see that there are some regions in the diagonal where the molecules orient perpendicular. So it's a nice grating, and it gives a nice diffraction order, and we can understand, simulate that. We can also apply a voltage. Now, calculate the periodicity. The previous case, here the period is 6 micrometer. 6 micrometer is the period between two 180-degree rotation. And the thickness was 3 micrometer for this cell. Now, slides. Yeah. The next slide, we have added a little bit of chirality in the material. Okay, why do we do that? Well, it turns out that if you fill the cell between this complicated pattern, the liquid crystal likes to have some chirality. And instead of following the pattern that we have seen before, it makes a different pattern, which has chirality. So there are regions where the director is up or down, and also horizontal. Okay, that's because of the chirality, it forms a kind of helix perpendicular. Now, if you apply the voltage, then at some point the situation switches to another state, which looks like the previous structure that I have shown. Now, at this voltage, all the directors are pointing in the perpendicular. And the interesting thing is that there's a hysteresis. So in this switching behavior between this twisted state and the perpendicular state, there's of course some modulation, but at 2.2 volts, you switch back to this other. Now, this has been advanced a bit more. So in this paper, same structure has been used, and there is a state 1. But you can also make a trick. Normally, this is again without any chirality, but normally we have this situation. Now, if we apply very suddenly high electric fields and we drive the molecules that they have to be parallel to the substrate, so we can do that by using negative delta epsilon. So this is a dual frequency material. That means at high frequency, we have negative delta epsilon. So what happens? These molecules which are perpendicular, they suddenly want to switch down. They want to go to the horizontal state. And if you do that fast enough, then you can create disclination lines. You can create lines in the structure where the orientation is not defined, and you can see that here as these black lines. So this is a state which we have seen before. This is a state with disclination. Now there's still a third state. If you first switch all the molecules perpendicular by applying a high voltage, but then in the region with the low frequency, and then suddenly you switch the voltage on again, all the molecules want to become horizontal, then you also create disclination lines, but now there are horizontal disclination lines and vertical disclination. So you can, by the switching history, you can change that shape. And finally, you can also go back to state number 1 by a special pattern where you decrease the frequency of the applied voltage. At some point, all the disclination lines. Okay, so in this case, we have 3 states, and all of them can be stable at 0 volt. Okay, now I explained the illumination of some pattern on the substrate. Let's have a look at patterns which are a bit more complicated, but in a different way. So in this, we will first have a periodic pattern illuminated, which is rotating the x direction. And after that is finished, we will rotate our sample and do a second illumination. And then we have the rotation here, where you have horizontalized, the variation is now in the vertical direction. So if the T3 is small, then the most important illumination will be this. And we see indeed a vertical pattern because there's no variation in the vertical. Now, if we then increase the time of the illumination here, then you will see that the pattern will become more horizontal, or a mixture between. So by doing illumination sequentially, and by using this formula, you can also change the orientation gradually. Okay, now this has been used to align blue phase. So it has already been discussed, the blue phases. So it's a wonderful structure in liquid crystal, coming from the fact that close to the isotropic nematic temperature for a chiral material, you can create a structure which is cubic, which has disclination lines, and it has a very small structure on the order of about 200 nanometers. Now, we have made photoalignment structure. We can also make it very small, because if you use blue or UV light, and you have a large diffraction angle of incidence of the two beams, then you can make the period very small. And we did that. We made a period of 240 and a period of about 270. And what happened? Well, for the 240, which is close to the period of the blue phase, we saw that the blue phase oriented the cube just flat on the substrate. And we saw a certain color, which corresponds to the reflection of the bandgap. There's a photonic bandgap of the blue. However, if we increase to 270, 270 is closer to the diagonal of this cube. Then what happens? Well, automatically, because of our photoalignment, the cube rotates over 45 degrees, so that now it becomes parallel or more or less comparable to this distance. And then we see a totally different color, because now we are reflecting on the substrates, but at a large angle. So then the color looks here blue. This is the Kossel pattern. So the color is here very different from there. But you see, we have now a very homogeneous alignment. So we can make blue phase with a large area. So last year, we also did some more calculations where the original pattern, the background pattern, is here vertical. Here it's 45, and here it's minus 45. And afterwards, we added horizontal areas where we illuminate with the second interference. And in that case, you see that our Kossel patterns are somewhat different. They are here tilted over 55 degrees, plus and minus 55. And we also did simulations to show that this is really what happened. So these are simulations where the yellow shows a disclination line, which are very important in phase 2. Okay, now let's go to a more general structure. So using interference, you can do a lot, but with interference patterns, you can have very high resolution, but you don't have a lot of freedom, because it's just two beams, and the interference pattern is what it is. And if you want to do more complicated variable patterns, then it's interesting to use spatial light modulator. So a spatial light modulator is a device made of liquid crystals, and it has 1 million pixels. It's like a small display, and it induces a phase difference between the horizontally polarized light and the vertically polarized light. There's a phase delay. Now, with that phase delay, and with the help of a quarter wave plate here and a quarter wave plate there, we can translate the phase delay into an azimuthal orientation. Okay, so it means for 1 million pixels, we can define for every pixel what should be the azimuthal angle. Okay, so that gives us a lot of freedom. And for example, in the next slide, you can see, of course it has to be calibrated, because these spatial light modulators that you buy, they are not always perfect. They are not always according to their to the rules that they prescribe. So it's important for every individual spatial light modulator to adjust and to find a kind of decoding. See, so if you do nothing special, you see there's a variation. That's a digital angle. And if you do a calibration, you can reduce that by a factor of 10. Okay, now with that new toolbox, we can make many different things. So instead, I talked about this rotation of the liquid crystal director, which was continuous rotation. But here we have changed the period of the rotation continuously. So we have here a little bit smaller period and here a little bit bigger. So we vary, we rotate faster, slower, faster, slower. And what happens if you have a variety in the frequency, then if you have diffraction, you see many diffractive components. If you have one frequency, you have one component. If you have multiple frequencies, you have multiple components, and that's what we see here. So here we see that in the diffraction pattern, we see now many dots, and we can explain where all these dots come from. They come from all these different variations of periodicity, and for different dimensions, we see different interesting patterns. We can also make another type of structure, and we have seen that if you rotate the director on the surface over 360 degrees, that then you can make the director tilt. Above that structure, you can tilt the director. So we have used this here to, on one substrate, we make here a ring where there's a rotation of the director over 360 degrees. So from here to here, we rotate over 360. On the top substrate, we had a homogeneous alignment, which was everywhere parallel in this direction. And in between those two substrates, automatically, we also have this effect that the director now becomes perpendicular. And if you look at the microscope, you can actually see that. So you can see a ring. Why is there a ring? Well, because in that region, the director has a smaller, the director shows the ordinary refractive index. We have a smaller refractive index, and this gives a diffraction. So this is without any polarizers. Even without polarizers, you can see that ring of different orientation. If you use the polarizers, cross polarizers like this, or polarizers at 45 degrees. Now, in some cases, if you treat the sample in the right way, you can also make a disclination line above this circle, and then the pattern looks a bit different. You can analyze it and simulate. So when we have a director that is vertical, we can also think, oh, this is now a structure where light that is polarized in the perpendicular direction can have a waveguide, because it has a high refractive index in this direction. And that's what we made here. So we made a kind of linear structure where the director is perpendicular, because this is our pattern on the substrate. We have here -1 discrimination, -1 defect point. So we can assume that light will propagate there. Now, how do we see that light really propagates? We first have to couple some light in. So it's an optics experiment. So we do that by entering light here with the prism into the structure, and we enter, in fact, in this point where this region with vertical alignment stops. So here you see the region with vertical alignment in light blue. And here it goes to the surface because it stops where we have the defect. So you can also couple light from the other side. And if you do that, so here you see we have made some structures which are curved, just in the beginning here. But if you enter light in the structure, you see wave guiding. You see that the light is really following this curve. So we have made actually a full liquid crystal waveguide that guides the light. Okay, now interesting is also in liquid crystals that you can make defects and disclination lines. And if you have a defect on the substrate, for example, a +1/2 or -1/2 defect, that means the orientation there is not well defined. And liquid crystal cannot deal with that. So if liquid crystal follows that orientation, there must be a disclination line where the orientation is not defined. It's topologically protected, so that disclination line must continue. And where does the disclination line end? In another point where there's a defect. So automatically we see that if we have 2 points with defects, then they are connected, sometimes vertically, sometimes horizontally, sometimes like this or like that, sometimes also through defects which are on top of each other. So we have measured all these different defects and disclination. They can have a different shape, and they can also be curved. They can be curved when the elastic energy here is higher than here. So then the area where the elastic energy is higher will be smaller, because that's a less favorite region, and the disclination line will become longer to find the new balance. Okay, then next slide. Okay, the next slide is about the ferropneumatic liquid crystal. So Professor Veach explained already this morning, ferroelectric pneumatic are very important. And so we have done here some experiments of ferroelectric pneumatic where we use the alignment, we use rubbing, parallel rubbing in the vertical direction. And when you do parallel rubbing, the vertical direction, you have a pre-tilt. And the molecules, so it was explained that the molecules have all the polarization in the same direction in this phase, but these molecules are also not exactly the same. Head and tail is also not. So typically, they have also a kind of splay, a typical splay. So there's a coupling between the splay and the polarization. So you see, if you have a pre-tilt structure, there will be preferred orientation for the polarization due to the intrinsic splay. And yeah, we can also see when we apply a voltage that in the region where the electric field is pointing in the same direction as the polarization, we see no effect here. The liquid crystal orientation is continuous, but here we see a very big effect. So we see that the polarization is actually rotating because you have a strong electric field near the edge of this.
Last 2 minutes.
Okay, thank you. Okay, so I will have to go a little bit faster. So in the display, we have also done photo alignment to use this display to align the director. And this, you see, if you have a display on photo alignment, you can tune the polarization in this direction, or a display in this direction rotates the polarization in the opposite direction, and that worked quite well. So that was the result. Okay, now. Next slide. Okay, we have also done some experiments with this RM734, and sometimes they form droplets. And in these droplets, the polarization doesn't like to stop. So how can a polarization form in a droplet without having an end in the polarization? Well, it can do that by rotating continuously, having a polarization which is actually rotating that direction around the particle. So this is called the spheroline. Okay, there are many other things you can do with photo alignment. So these are some results from the State Key Lab. So the State Key Lab for Displays and Optoelectronics is an important institute in Hong Kong University of Science and Technology, and these are some results from colleagues obtained there. So photo alignment can also be used to align particles in a certain direction to have this linear polarized. Now, the last part of my talk is about chiral liquid crystal. Now I will do that very fast. You know, chiral liquid crystal has band gap, so I will not explain much more. And you can calculate this band diagram, and you can look at the reflections on the substrate. And you can also use these very good mirrors, which are chiral liquid crystal mirrors, to create lasing. So if you have a light-emitting material between two mirrors, you can create lasing. When you excite this layer, the light will start lasing because it oscillates between those two reflectors. But then, okay, and you can also make particles, but this I will skip this part. What I would like to explain is the combination of my chiral liquid crystal and the photo alignment. So if you have a photo alignment material, normally the liquid crystal, pneumatic liquid crystal will follow that. If you use a chiral liquid crystal, well, a chiral liquid crystal prefers to make a helical structure. And if you cut this helical structure with a plane which is not perpendicular to the helical axis, you can understand that the director also rotates like this. So when that happens, it matches, in fact, exactly the structure that I have shown you. So vice versa, if you start with this structure and you put some liquid crystal on top of that, some chiral liquid crystal, that chiral liquid crystal will automatically organize itself, so in a helix, but now the helix will be tilted because that matches exactly. So it's a very nice structure where you help the liquid crystal to orient in a certain direction, and you create a helical axis, and the helical axis is now tilted, and so also in our vector diagram, the wave vector diagram, you see the band gap is now also tilted, and you can use that for interesting applications. So here you can see that the angle can be quite strong. It's also very efficient. All the light is really reflected, and it's reflected now over a very big angle, much larger than for the pneumatic liquid crystal. And so this application is augmented reality. So if you have a grating with such a large diffraction coefficient, you can really reflect the light inside the waveguide, and here you can bring it back. So this is the architecture waveguide architecture for augmented reality. Liquid crystals are a very good component to realize. Okay, you can also do a head-up display with that. So if you have a grating here, you can also reflect the light to the eye, which is for a certain wavelength of the display. The rest of for the other wavelengths, it is transparent. Okay. Now, in the lab, we have made some devices like that. Of course, we didn't make a windshield, which is very large. We made a small sample, and that sample acts like a spectrometer. So light from the spectrometer, from the slit, is reflected, but it's also focused, because this has not only a diffractive component, it also has a focusing component. And in this way, we can separate the colors and measure their intensity with the spectrum. I will stop. We can do that in different ways, and I will skip those slides. So, this is my conclusion. Well, my conclusion is that you can do a lot with liquid crystals. You can do photo alignments, you can do pattern structures, you can make three-dimensional structures. You can also use diffraction, and you can have very nice optical components. And so to finish, I would like to stop with this slide. This is my university, Ghent. So some of this work has been done in Ghent University, and this is the campus at HKUST. It's very beautiful, close to the sea, and yeah, I hope that you are also able to visit us at HKUST. And with this, I would like to thank you for your attention.
Thank you, Christian, for such a wonderful talk. I myself don't want to stop, but I have to move around. So one question.
Christian, it's very interesting. It matches, complements my talk. If you can go to the slide number 27, there you speak about the layer that emits the light.
37?
27. Yeah. Here, why not we have the cholesterol molecules themselves emitting light? What would be the difference?
So here we have some quantum dots, cadmium selenide, cadmium sulfide quantum dots between two mirrors, between two cholesteric mirrors. And so we excite it, and then there's light emission. The light emission from these quantum dots is...
Molecules themselves are emitting light.
If the molecules, you could also put some dye molecules in. Then you can obtain the same results. But with dye molecules, typically, their lifetime is not so long. So organic dye molecules in such a lasing system, where you excite with blue or UV, is a bit more difficult. But if you have some good materials, we are... Okay, yeah, I think that... Yeah, that can be done, yes. That's also interesting.
Okay, a huge round of applause to the Christians. Now I will... Thank you. Yeah, please. Thank you so much. It was a very wonderful talk. So now we actually will have the parallel sessions. So 6106, the Professor Sandeep Kumar is the person.
So this is the presentation, right?
नहीं PDF फाइल कहाँ पे ये वाला
You can
yes.
We just introduce. We just have to just say like say the name of the just the student and the question of the teacher. We start the title is and so timing we have this timing that timing that we have right. So this includes That unit, 23 plus 2 times 3 is around.
Now we have with Dr. P. Vishwanath. Yes, so he'll be presenting his work now, and we all know his work. And he's presently a scientist at Center for Nanoscience and Soft Matter. He has already awarded, from Liquid Crystal Society in 2022, and yeah, a lot of our credits are already mentioned there.
Thank you, sir. Thank you very much.
Welcome. So after 22 minutes, I will remind you.
Yeah.
Yes, sir.
20 minutes.
Thanks. Good afternoon, everybody. So today I'll be presenting some of the ongoing work on the nature of the phases and the surface pKa estimation of some acid derivatives of cholesterol at interfaces. I work at Center for Nano and Soft Matter Sciences in Bangalore. And so what I'll be sharing is basically from the work of Mr. Naidu Moram. He has done this work. And this is collaborated with Dr. Santosh Katavi and Dr. C.V. Alamagar. They have synthesized the sample. And we also have the other group members here. And I also am thankful to Dr. Manjula and Dr. Rajkumar Gupta and the team of volunteers and the Department of Physics and ILCS for this opportunity. Yeah. So in our group, we basically focus on some aspects of polymeric films and dilational rheology. This is done at interface. So you can do in principle rheology in shear formation or dilation formation where you can compress and expand the monolayer, and you can get the response of this polymer here. We specifically look at blockopolymers because these have interesting phases, and it also gives interesting morphology because of two covalent linkages between them. So we also pattern some structures using colloidal lithography technique, wherein we form a monolayer of colloidal spheres. We tend to size reduce them, and then we put some metal there and look for plasmonic applications. So this is some area which we venture. And we also look at how the contact angle gets modified as you change the fraction of the metal to the voids. Okay. So today's topic, which we also focus here, is the self-assembly and phase transition in 2 dimensions. This is basically carried out by the amphiphilic molecules. They act as model systems to understand phase transitions in 2 dimensions. And in addition to positional order, these have tilt and bond orientational order in these phases. The phase diagram is very rich. You have 17 and odd phases, and there are analogy with the smectic phases in plane ordering of them. You can equate it to the very many smectic phases there. It is a very rich phase diagram as mentioned here. So, so what we are presently looking is the pKa estimation, where you have the acid here, which when you change the pH of the solution, it goes to an charged form, a deprotonated version of this acid. And you can relate this pH and pKa based on the deprotonated ion concentration and the neutral ion form here, neutral form of the acid, this one. And this is very essential parameter in many physicochemical and biological process, wherein people would like to estimate this pKa in bulk as well as at interface, which will be the focus of today's talk. So basically, there are very many techniques here. You have potentiometry, spectrometry, partition, HPLC, and then to measure these techniques, which spans from 1900 to 2000 to measure this parameter here, because I know at this point how much of these molecules are fractionated into deprotonated version or charged form or neutral form. At this 50%, you measure this pKa value of this. So this is what is traditionally measured in bulk. So the importance of pH on the solution is, for example, in the case of oleic acid, it tends to form different phases here as you vary the pH of the solution. So this is done in phosphated buffer saline. You take a microemulsion and below 6.8 pH it phase separates, and you have discontinuous cubic phase, vesicles, gels, lamellar phase as you vary the pH from 6.8 to 9.5. You form an interesting vesicle patterns there. So you can control the self-assembly by manipulating the pH of this simple acid, oleic acid. So this has been very prominent in the case of allotropic liquid crystals, wherein they have used again an acid which is 3 weight %, and they control the pH there to make it dissociated in one form. Because this is important as you take this allotropic liquid crystal is loaded with a drug, and when you take it in your oral cavity, it has a pH of about 7 and it has cubic phase, and this helps in fast diffusion there of the drug. And whereas in the stomach it is about pH 2, and wherein it is slow division because the drug has to be slowly released and the stomach has to be treated here. And you also have the intestine region where it is going to pH 7. So this phase again comes back here, and these are the signatures in the X-ray patterns wherein you have different phase signatures there from small angle X-ray scattering. You have the cubic phase and the hexagonal phase there. So this is very important for the case of drug delivery. The pH also plays a role. In addition to this, the small molecule acid being used for stabilizing the foam. What is shown is the foam fraction here, volume fraction of the foam here. And this foam height depends on the pH. You can see that at the pKa value, it is all having its maximum and optimal efficiency here. So what is shown here is the foam height versus pH, foam stability, which is peaking here, and for single bubble stability, that is also peaking at pKa value. And evaporation rate, this also comes down at the pKa value. Surface viscosity is improving at the pKa value and the contact also. So this highlights the importance of studying the pKa of this solution and how it governs the foam stability. In the case of small molecule like pyruvic acid, this goes from the protonated form to deprotonated form, which is charged here. And people have tried to use these ATR, FTAR, attenuated total reflection, Fourier transform spectroscopy, as well as some frequency generation spectroscopy to infer the bulk pKa and surface pKa here. So what it shows is there is a difference between the bulk pKa, which is about 2.3 for this molecule, where it goes from one state to another state, and apparent pKa is about 2.9 for the case of the surface pKa. So there is change. The surface is, the pKa value is shifted towards more in this direction. So the protonated form is more stable at the interface. This is the larger conclusion of this talk, and they attribute it to the local solvation characteristic of the protonated form and the deprotonated form, because this solvates the water molecule in a very different way. So interestingly, for amine case also, people have tried to explore this aspect, and then they try to look at for various pH, how is the solubility governs, and they find that at high pH, it's neutral, whereas at low pH, it is soluble. But once it is charged, then there is a contact ion pairing of this ion, and this makes it again insoluble there. So you can manipulate the solubility of the molecule by looking at the pH, and it is also extended for the case of short chain acids. And you can find that the surface pKa, as you vary the chain length here of the acid from C8, C9, and C10, you can change the surface pKa from 4.9 to 6.4. So there is a difference here. What is plotted is the surface tension change in the presence of acid as you vary the pH. And you can, from the sigmoidal part of this curve, once you fit it, you will get this midpoint there, which can signify the surface pKa. So you also have similar there studies for looking at the degree of unsaturation and aspect. So I'll skip this one. So what is largely found is there's arachidic acid, when they change the pH, you also have different phases as I discussed earlier. There are very many phases in the phase diagram. And with increasing pH from 9.2, 9.5 and 9.7, the phase boundaries get shifted there. So this is an important finding that the phase boundary between the two phases, it gets far apart as you increase the pH when there is electrostatic interaction in place. So this is good work by Professor Rajkumar Gupta, Suresh and Professor Sandeep Kumar here, wherein they have taken the molecule like cholesterol and they have, which is always shows some surprising behavior, all the chiral compounds, and you find some anisotropic tilt pattern which varies as you change the relative humidity. So there is some interest in looking at these systems at interface because this has unique phases. So what we have tried to ask is basically among the protonated or deprotonated form, which one is more interfacially active and what are its signature at interfaces? Can we tune the interaction by varying the pH and what are its implications on phase behavior at interface? So this is the structure of the molecule which is synthesized by Dr. Elamagad and Dr. Santosh. You have basically a carboxylic acid group. This is the part and which is connected to a benzene ring, and you have this cholesterol moiety here, and this spacer length is varied between 3, 5 and 7 here for this case. So this +1 we call it as even spaces there, and this presence of cholesterol moiety it always favors aggregation. It promotes van der Waals interaction and it favors aggregation between the molecules there. So it leads to formation of gelators. It has a gelation characteristic of this moiety. So it features in the design of gelators in very many ways. So what we have focused here is to use a simple interfacial mechanism. Can we study these molecules of different spacer length? And we use a Langmuir trough here where we continuously vary the area per molecule and we measure the surface pressure. We look at the textures by shining light at the Brewster angle of a p polarized light or transverse magnetic polarized light incident at a Brewster angle, and we can visualize the textures and phases of these molecules. And we also looked at the AFM1. In addition, we also did some relaxation kinetic studies. So what we find basically is there are distinct difference between pH less than 10.5. When these molecules are largely in neutral state, you have a different kind of isotherm, surface pressure area per molecule isotherm, in comparison to the pH at greater than 10, where we have very high collapse pressure here. This shows that the interfacial stability of these phases is enhanced at pH greater than 10.5, whereas as less than 10.5, it forms unstable films. So you have characterization, the modulus value says that they are all fluidic phases, and they also have some dependence with respect to the spacer length, wherein you have a low ordered phase and high ordered phase at different pH here. So what this says that is like as you tune the pH, you can change the phases and stability of molecules at interfaces. In one case where it is largely in undissociated state, it's largely unstable, whereas when it is dissociated and when the electrostatic repulsion comes, it is stable. So what is important to note is this parameter collapse pressure, it is higher compared to the one in neutral state, and also the lift-off area per molecule is lower here, and whereas here it is much higher for the case of dissociated state. So this shows that electrostatic repulsion of the head groups play a major role in dictating the stability. So you looked at the collapse pressure behavior with pH, and you find a sigmoidal behavior for all the three derivatives, and fitting this we extracted the pKa value to be 10.6, 10.8 and 10.9 using this method, and the area lift-off area per molecule at 10.8, 10.7 and 10.7 for this. With this error we could estimate that. So there is a difference in the values of the pKa by 0.1, 0.2 units if you use collapse pressure as a measure for monovalent ions, or lift-off area per molecule for the spaces, for different spaces here. So we also perform some hysteresis characteristics, and we find in the neutral form it is more hysteresis, and whereas in the dissociated state it has less hysteresis. This says that the dissociated state is much more stable at interface than the neutral state, and there is also loss of material there in more in neutral state. So we carried out surface pressure relaxation kinetics. We looked at the molecules in the neutral form and the molecules in the dissociated state, and we find that the molecules in neutral form, it decays rapidly to 0, whereas the molecule in dissociated form, it is having a long time constant here. And this is fitted to a single exponential fit for these cases. Whereas that intermediate time scales, wherein you have this mixture of these two entities, you have a complex relaxation behavior. So there are two kind time constant here. One very short time constant, which follows this decay, and one long time constant as you increase the pH. So these are two important implications. And we looked at the textures using Brewster angle microscope. And for the case with neutral pH, where the molecules are largely in undissociated state, you tend to get anisotropic fringe patterns here. And this is more in contrast also. And this transforms to crystallites for the case when it is undissociated, as you vary the surface density here. And when it is pH 11, you tend to have the protonated form, you have uniform spaces there. There is some signatures of some thread-like patterns here, which you can see that here. So this shows that even in the fluidic phases, you have some differences as you vary the things, and it also depends on the spacer length here. So this is the phase sequence which you obtain as you increase the surface density. So we also looked at the topography images in the neutral state, and we find largely multi-layers. This is the amplitude images, and this is the phase images there, which says that they are all multi-layers coexisting, and the step size varies between 3 nanometer and so on, 2.2, 2.3 nanometer here, and it's a much heterogeneous thickness. For the monolayer case, you have these pinholes there for these three derivatives, and it shows a height profile about 3.1 nanometer if you take this pinhole as a reference there. And this is in the collapse state, you get a surface step of about 2.4 nanometer for all the three cases in the plateau region after the collapse. So we came up with a model now. This model says that the neutral pH, it largely favors multi-layers, whereas in the dissociated state, it is forming a monolayer. Here it is forming possibly dimers here, as it is in neutral state, whereas in the case of the charged state, due to electrostatic repulsion, as also seen in the increase in lift-off area, this has good interfacial stability, as is seen in the value of collapse pressure here. So as you vary the pH, when it is less than pKa, it favors multi-layers. When it is greater than pKa, it favors monolayer. And you have unique fluidic phases, which you could see. So with pH, we see an increase in the value of collapse pressure. And with pH also, we see increase in lift-off area per molecule. So to summarize, I just want to say that the Langmuir films of 3 aromatic acid derivatives of cholesterol were investigated at different pH. For pH less than 10, you have undissociated or partially dissociated CHBA. And it forms predominantly multi-layers. Dominant van der Waals interaction is present there, and it is tendency to aggregate is more here, which forms a dimer or cluster here. And whereas we could use this interfacial activity or from the measured surface pressure response and the lift-off area per molecule to infer the surface pKa between two methods. And we think that the collapse pressure measures from the L1 prime to the 3D transformation, whereas this is measured from the gas to L1 prime. And I think that is the reason why there is slight discrepancy in the value of the pKa measured through different response. And we have pronounced interfacial activity at pH 11. This is much greater than the pKa value of the molecules. And this is the phase sequence, which we have these two fluidic phases present for these two molecules, whereas we have only one fluidic phase there. So this is the summary of the whole work that, and we have published here in this article. I thank you for your attention.
Thank you very much. So we have finished well in advance. So now the house is open for questions. Yes, please.
Your slide number 23, what exactly I want to ask is in this aromatic acid derivative of cholesterol, you see some kind of fringes, but is there any evidence for collective motion?
No, we didn't have it here. Because this is forming anisotropic multi-layers.
I see. No. What I'm telling is, at the interface,
we don't find. We find that's the.
No, this is very similar to what I'm going to present tomorrow. Yeah, you cited that.
Yeah.
And I'm curious whether there is a very good chance it may show similar vortices.
Yeah.
Thank you.
Yeah, in your summary slide, you said that van der Waals are dominant there and they're resulting in the attractive forces, right? Yeah. So, I mean, on theoretical front, people are still confused about the magnitude of van der Waals, that A, right? Okay. So, with what support you are claiming that they are behaving in that sense? And do you have any conformational values for that A? No. I mean, van der Waals constant.
No, we don't have that, but we have indirect influence from the gelating behavior of cholesterol, which forms these aggregates. Now, if you have the cholesterol moiety, even if you take the esters, for example, long chain esters of cholesterol, it tends to form bilayers because of chain-chain interaction and the cholesterol moiety and the short chain interaction and cholesterol-cholesterol interaction. So the van der Waals interaction, or when you increase the hydrophobic units, are very prevalent more. But I don't have a quantitative method for what you are.
Yeah. Because when you're talking about the bilayers, I mean, that is very important term here, wherein there are mode switching takes place. I mean, theoretically, I'm saying. So mode switching decides, and that is based on the orientation of your directors. So that influence largely whether that A would have a positive impact or the negative impact, or the attraction, or I mean, the opposite of that.
I'm not sure whether it's handled simulation-wise or experimental-wise.
I'm talking about the theoretical, I mean simulation part, what people have reported in the literature, yeah. Thank you.
Yeah.
Somewhere that the loss of material due to the hysteresis something. So loss in what sense, like is it dissolving?
It goes to multi-layers.
It goes to multi-layer. So
the
aggregates.
2D material, it's no longer a 2D material. It goes as multi-layer because this can't be soluble, no? Because its hydrophobic tendency is more when it is in neutral state.
Mm-hmm. So multi-layer, or it's any random crystallization or something?
The AFM study shows it's about bilayer type. Each step size is about 2 nanometers, 2.2 nanometers. So we expect there is a tilt there.
Okay.
Tilt of the molecules.
Thank you.
Thanks, sir.
I have one quick question that in surface PK measurement, so you have electrostatic. What's the role of dielectric environment at the surface?
We are not. We are currently looking at the influence of ions there. Trying to shift this PK value there.
Okay.
And there we are the hydrated head groups there. Okay. It is playing a major role. The epsilon, it modifies the permittivity because it's a function of Z.
Okay.
So that's the
SDMI.
Oh, okay, thank you.
Thank you.
देख लीजिएगा
सर एक बार आप रख दीजिए कौन सा ये वाला HDMI वाला लगा दो लगाया हाँ लगाया
क्या रहा है थोड़ा सा इधर कर देते इसको ये जा रहा है
Talk. And second speaker is Dr. Alpana Naik. Is currently assistant professor in the Department of Physics at IIT Patna. She did her PhD, I think it will be shown here also, a PhD from Raman Research Institute, Bangalore, in the field of soft condensed matter physics, particularly focusing on the self-assembly properties of discotic liquid crystals. After completing her PhD in 2009, she joined NIMS Japan for her postdoctoral research. She spent 5 years at NIMS working on a conceptuality new device called the atomic switch for developing binary type of computation system. Then she joined Tokyo University in Japan for a second postdoc. So her research experience is interdisciplinary, involving concepts from chemistry, physics, biology, material science, and device technology. And she has published over 35 research papers, to review articles, to book chapters, and about 1,000 citations. And some of her noteworthy contributions are published in high reputed international journals, namely Nature Materials, and then Nature Nanotechnology, Advanced Materials, Advanced Functional Materials, etc. And let's welcome her talk. And she has been recognized for her work by the Liquid Crystal Society. She was awarded ILCS Bronze Medal in 2023. Yes, welcome to the stage, and we are looking forward to your talk.
Thank you, sir, for the kind introduction. Good afternoon to all of you. So I'll start.
Yeah, there are some technical glitch maybe, yes. Oh. We thought we saved some time. Yes.
And I would like to thank the organizers. Professor.
Yeah, we thought that in the last lecture we saved some time, 5 minutes. Now it's gone. No compensating.
Which one? This house. Yeah. वीडियो है वही से पेन ड्राइव लगा रहने मुझे वही से चलेगा पेन ड्राइव लगी हुई है ना उसे रहने से प्ले कर
ये लगाना पड़ेगा ना वीडियो के लिए
पेन ड्राइव मत खोलो पेन ड्राइव से चलेगा NCLC यहीं से हाँ और से रन करें
Good afternoon, all of you. So I'll quickly start because already I have taken some time. So today I'll be talking about the promise of discotic liquid crystals from self-assembly to neuromorphic devices. So my understanding of discotic started from my PhD work that I did with Professor Suresh from RRI, and this discotic was discovered in Ramanujan Institute and also published in Pramana in 1977. We all know about it, that this belongs to India, and we have discovered it in India for the phase itself, and the molecule that was discovered was this one to exhibit this particular phase, benzene hexa-N alkanoids. So what is important for kind of work that I do is the core. So it started with single benzene, and then I have seen, because I'm not a chemist, so I keep on observing that the discotic core gets on increasing, and so this hexabenzocoronine and many modifications of this, and then I come across many papers that Professor Kumar and many others do write very beautiful articles on the progress on discotic liquid crystals. And then I also came across some very nice articles on this, like from how the core enlarged, and thinking about something like graphene and all, like as big as like continuous like graphene and all. So in my work, the kind of molecules that I have used so far, in my work, I have used the molecules synthesized by Professor Sandeep Kumar's group during my PhD under Professor Suresh here. And then the molecules also from Professor Santanu Kumar Pal, who is with Mohali, Aisal Mohali. So still I continue using the molecules from them. And so in the morning, Professor Kumar said that he will take sannyas, but he's not here. I would believe that if he would be here, he would have changed his mind. because I have something to say on discotic, which is probably new. So for me, what is important is the self-assembly, the self-healing, and the anisotropic conductivity for the applications that I look forward to. Now, since 2003, the beginning of my PhD work, I have been using different molecules with this trifluorine core, and Professor Kumar has already emphasized the importance of this core itself. And all these molecules that I'm showing here are part of my thesis work, and all of these are synthesized by Professor Pal, who is here under the supervision of Professor Kumar. And then, after joining IIT Patna as a faculty member, I started my work again with discotic, because in Japan I did a little bit of application, application-oriented thing, device making. So she is my first PhD student, who is already a faculty member at IIT Dhanbad. So in our work, we got this molecule from RRI. After she joined, we went to RRI and got this molecule. This is very interesting because the core looks same, but this is not covalently bonded. It is electrostatically held, and that gives a very new kind of a system that I had not studied before during my PhD at least. And then another kind of work, so another kind of molecule that actually my second student did, so PhD student, so this heterocoronine, which is very interesting. This heterocoronine DLC molecule, and we do look into the self-assembly properties. And then Ibangsu is also working on this another heterocoronine molecule, which is the oxadiazole. So this is the difference, and having only this difference can lead to a huge difference in self-assembly and huge new things that we would otherwise not have achieved. So my talk today will be focusing on these two molecules. So, and luckily all these molecules have been amphiphilic. So they have hydrophilic and hydrophobic so nicely balanced that it makes a very good fill. So that's surprisingly very interesting and important. And for these discotic molecules, two configurations are well known. One is press-on, where they lie flat, and the other one is edge-on, where they lie like this. So this is just a cartoon to show that the molecules should have something to anchor with water, like a polar, and something should stay away from water, that is the hydrophobic part. And if they have a good balance, then they make a film at a water interface. So the technique that Dr. Vishwanath presented, I mean, the same technique we use, like the language technique to understand the self-assembly interface. And we do go through understanding these phases, but the molecule is discotic that we look into. And all the molecules that I have studied so far, they all form very nice uniform film, and with a good collapse pressure, with good rigidity and other things. And also because the trifluorine core matches so well the size with the DNA double helix diameter. So we prepared this complex with DNA, and we could see that this film could be transferred over several layers. So we could make multi-layers very nicely. So this was all during my PhD. And here, this was the kind of new kind of molecule, because it's not covalently held, and in bulk, this molecule was known to show lyotropic and thermotropic. This was synthesized by, I think, Swaminathan under the supervision of Professor Kumar. And then it was a little bit challenging for us because we didn't know how this molecule would assemble at a water interface, because here this part is, they're electrostatically held, they're not covalently bonded, and it's a very big molecule. Like if you see it together, so then it will have 1, 2, 3, 4, 6 of those double chains around here. That makes a very big one. So then we took help from this molecular dynamic simulations done by our collaborator at IIT Patna from chemistry department, who helped us to understand that the assembly is actually like this. The discotic cores, they are actually lying somewhat flat at the interface, and these double chains, they are at the interface staying away from the water, and this is actually what is governing the self-assembly. And so this was actually advanced materials interfaces. So the Coulombic interaction actually dictated how the assembly would be. Now, coming to the topic that I would really emphasize today is this particular molecule, which is heterocoronine, and this is very interesting, and it was published in 2019 in JACS by Professor Falk from Aishaz Mohali. They reported this ambipolar DLC with the highest ever electron hole mobility And we took this molecule and we started observing the film forming abilities. And like we do for all molecules, we studied these things under this Langmuir trough and crystalline microscope is whatever we have to see it, like the film making properties. We could see that this particular molecule forms a very good film with a very high collapse pressure, very good rigidity, with a very high, very good elastic modulus, and the film was very compact and rigid non-stuck. And then when we prepared those films on substrate, transferring those on substrate by LB technique, we could see that they formed this nano wire kind of thing. So these are actually stacked discotics, like nano wires, and they assemble, they form this film. Like it forms a very compact, very large area films we can make on a substrate. Now, the interesting part here is that this particular molecule showed for the first time that they just don't need any substrate to make a film. They can freely stand, that's freestanding film. So he lifted the material out of the water. He used to say that he could see the film floating on water, so rigid that he can lift it up. And then he saw that this film, this is a TM grade, or he performed FEACM and TM, and he saw that these are a monolayer of whatever film was formed on the water surface, and they freely stand and they're pretty much stable, but and also there is some kind of a tear and other storage foldings, because this kind of film, when it's taken out of water, cannot stay like that. It has to fold and buckle to stabilize its thermodynamics. So this is how it was formed. And he also tried to actually image the suspended film, the freestanding film, which is really challenging when we do AFM to stabilize the tip. And he could see that the film actually has this kind of rod-like things and like some aggregations, which is expected because the film on the surface also shows similar things. Now, the point is that the fact is that from benzene to graphene light, that was kind of thing that people focused on when we talk about the discotics, right? So if this is the first molecule and if this is the aim, or I don't know if it is aim or like it's something that is progressing towards this, what we made in the lab is this. So if you say graphene, so graphene was very much well known because it could stand alone. It was a freestanding film. It's a monolayer. But then, of course, graphene, this thing that we say as graphene is 2-3 layers of graphene, still we call it graphene. But here we are able to make for the first time that a film of discotic, which is also a monolayer. Now the packing is different, it is edge-on. And the important thing is it can also suspend itself freely. It doesn't need any substrate. And Nishan used to say, my student, that he can lift it up, he can put it on any substrate he likes, and he doesn't need any substrate specifically. He can just put it on anything he likes. So that opens up opportunity that it can be used irrespective of the dependence on the substrate itself. So one important thing we studied that, okay, if it is like a freestanding film, and if we have something in our mind like this, of course, chemically it is not like that, but it's a film of similar material, then the transparency also was very high, 97%, like the one that usually people claim for these graphenes and all. And another thing is that it was hydrophobic. So we have another molecule that I will show after this. So this is hydrophobic, and by changing the system, we can also have hydrophilic. And so now this particular class of molecule that we are studying currently is extremely important, extremely new technologically, and opens up a very new scope of all the kind of applications we can think of. So this film actually is made up of this kind of nanowires, and these wires are actually stacked up discotics, and they're very, very stable. And this is kind of a very rare example because only we could find, I mean, to our knowledge, only one paper, one report is there in Nature Communications. Otherwise, we do not see any such report of freely standing film. Now, another work that we are doing on the same molecule, only with the difference of this oxodiazole, we do see a very different property. Here, the area of the molecule increases very to a large value, and then this elastic modulus also increased more than double, slightly more than double. Now the point is the molecule was all the same. There was no difference except for just one thing, that oxodiazole was added to it. But how could that can change the full cell assembly drastically to such an extent was our surprise. And then, so to observe because the film would look uniform if you observe under BAM, and if we do this isotherm, it always looks like a making a film. But then how do we contrast them at the same place? So when we did that, we actually, sorry, I want to play this video. There is a movie which shows two molecules together, and I would like to do that. I don't know how to do. I have to escape probably. How to escape? So, oh, sorry, it's not coming here. It is playing here. So this one should be, I want to play. No, no, we just click on that. Okay, thank you. So, no, it's not playing. Okay, so what we did is that we put the two things together and we observed under the microscopy to see the real contrast, how these things are. We could see this material, this green oxidizole, was more fluidic as compared to the one that had oxidizole. And its very sharp boundaries, these are actually oxidizole containing viscotic material, and the one that was very fluidic or didn't contain oxidizole. So that confirmed that these two really have some difference in properties. And then if you also look into this film transfer on the substrate, then you see that there's a difference in the thickness. One is about 1 nanometer, 1 or 1.2, and the other one is actually 4 nanometers. So one is kind of edge-on, and the other one is face-on arrangement. That was kind of net prediction. And these are some of the images of BAM, discrete microscope and AC images, which clearly showed that one system, like the heterocoronium alone, had this kind of a morphology, whereas when the oxidizole is added, it makes the morphology completely different, completely uniform and flat, and extends over a large area. Oh, sorry. Okay, so now these films were transferred at different target pressures, and we saw that this particular oxidizole containing film was almost uniform, and they formed a very, very large area of film and good for application. Okay, so the thickness, as you can see, it is about 1 or 1.2 like that, and throughout it was like that. Now the point is that by just changing one group, we could see that the molecular arrangement itself changes. And again, we also studied the film's freestanding property of this particular oxidizole thing. It also forms freestanding film. So we are interested in this freestanding film because there is no report on that, except for only one report that has come recently on freestanding. Otherwise, there is no report that to our knowledge exists on this particular film. And okay, and so we try to study the mechanical properties. So by doing this force distance curve on this suspended film, we try to calculate how much of the elastic modulus. By doing so, we have found that elastic modulus is about 4.84 megapascal. So this is, of course, lower than the value that we get in the substrate. Now, they coming to this point that how can we apply such materials? So the idea is to use it for neuromorphic chip development. We know what the synapses, that is the smallest unit that makes the memory in our brain. These are the neural networks, and all these things are present in our brain. So nowadays, there is a lot of attention on the membristers and membristic crossbar arrays and finally the neuromorphic chips. So we want to use these viscotic materials in this direction. And the whole idea is to go along with the AI, because the AI things are coming up very profoundly nowadays, and everything is probably will be affected by this AI that is coming, and we all need that for progress and other stuff. And then neuromorphic computing chips are going to be developed, and government is also starting many missions on that, or AI mission and other stuff, which is promoting or this kind of research. So, and on organic memories, there are of course many reports, but from India, IASC group led by Sito Goswami, they are doing very good, and they are published several Nature papers. Also from India, 2024, they published Nature. By using organic material, they have shown these properties. The idea is that we want to do it using viscotic. And because viscotic has many, many inherent properties, they are using for other molecules. They're using this ruthenium containing molecules, but not viscotic. So viscotic is something like probably it's not explored in this area and has a very huge scope. So we do measurements using AFA in our lab, and we do IG measurements. And if we put these viscotic molecules on silver substrate, we see that the silver precipitates on there, and this can be also erased by applying bias, positive, negative, like that. So we can control the growth and precipitation. Accordingly, we have this IV marking this on-off ratios, and many details are there that makes it suitable as a very good membristic candidate. Like it's a very good membristic material that we can work with. We can do this kind of a thing, and another very interesting thing is this, multi-state memory or quantized conductance. So this quantum conductance is known to appear at low temperatures for systems that has been known since the beginning of semiconductor industry. But now we can see this quantum conductance even at room temperature for this, and quantum conductance for inorganic materials or organic materials do have different values. And for despotic systems, we do see that they are following some particular fashion, and like this, and this quantum of conductance, when you see this H mark of this quantum, actually now in metrology, like international metrology department, they want to use this as a standard to as a measure of the conductance. So, now my work in Japan was with this pioneering group who actually invented a technology, quantum conductance atomic stress technology, and they published this method paper 2005, where they said that at room temperature we can achieve this quantum conductance, like this stepwise conductance. And so I would like, and that was 2005 that the paper came, and 2019 they established a company. Because when I was working there, they used to work with NEC, Nippon Electrical Corporation, so, and they used to make small chips and all. But by 2019, whole new company established, nanobridge semiconductor, and they, for the first time, they made radiation tolerant, non-volatile, low-powered nanobridge at PGA, world's #1, and they used it in their satellite, which is still orbiting RAPIDS-1 2019. They launched it through this rocket. It is still there. So the institute that I worked in, JAXA was just in front of that. And then it's like I have seen how this thing has developed actually. So, and they use inorganic material, not organic. They use inorganic material. So, and watching this, watching Japan build a powerhouse company on their atomic stress technology, I can't help thinking as an Indian researcher how I dreamed of this, doing the same, but our ecosystem never lets the idea breathe. Okay, so what we want to do is actually this thing. So this is also a movie I want to play again, but maybe I can skip. So what I wanted to show is that it would be nice if I could play it, but I'm afraid it would. What do I do to play this? Okay, so here what it shows is the inherent thing that happens in this.
You got another 4 minutes. Just I thought to remind you.
Okay, okay, so this is what it is. So in our brain, we have these millions of neurons connected by billions of synapses. So what we really want to mimic is the synapse, the unit that actually controls the memory. And using viscotic liquid crystals, we can do so. In our lab, we have a memory experiment that proves that it is a very suitable material. We can actually design something like that, and that by doing so, we can actually have sensory memory, short-term memory, long-term memory, and which actually multi-store memory of human brain, and all those things which connects to this psychology, which connects to the brain, this anatomy of the brain, other stuff, and very much related to like neuromorphic things that one, in order to develop a device, what we need is this thing. Now, so again, this is a movie. This is the last movie probably. Okay. So what we want to do is that we can make a device, and this device can actually have the storage. So we can write something and we can record it. So it's like, you know, we want to include 1 or 2, so we can input it as a long-term memory or short-term memory. You can see, depending upon how frequently we are applying the bias, the digit 1 will be stored as a long-term memory and 2 will be erased. If you see the final image that will come, 1 will be there but 2 will be gone. So all these things we can do in our lab using viscotic materials, and which shows immense potential of the viscotic material itself going into a very new field, which is neuromorphic chip designing. So 1 is there. Okay, So I'm almost done. Now the point is that, sorry. Now the point is that we have many more ideas to go along with using discotic itself. So discotic, with the help of our collaborators, Faisal Mohali, we can design different kind of materials which are kind of photosensitive, and then we can also go for membristors which are photosensitive, and we can think of many new applications. Even we want to design something like a neural network using these materials for this kind of chip designing or some predictions and some nanobrains. There are a lot of things. The only thing is that probably in liquid crystal field, this kind of application is new because we always think about displays or other applications. But I can say that neuromorphic has a huge potential. It's very new and it is just at the edge. It is the AI. That's what everybody is looking forward to. And this is what actually is. So only 3 lines to conclude. Controlling the self-assembly of distorting liquid crystals is both fundamentally and technologically important. Freestanding films of DLCs is the first of its kind, bringing it closer to the concept of graphene. DLCs has the potential as quantum systems for neuromorphic applications. And finally, I would like to acknowledge all my dedicated students who sincerely work in the lab to have this research output. My supervisor, Professor Suresh, is here. And without his guidance, that marks the beginning of my research journey. And my postdoc mentor and my collaborator from Germany, Professor Ilya, Professor Hasegawa, and Professor Sandeep Kumar, Professor Pal, and Dr. Mishra, I work together. And the point is that Sandeep Kumar sir is not here, but he said he will take sannyas. I don't know if he would still say sannyas. Point is that he said he can make 1 kg of the sample. We really run out of sample. I would have asked him, could he at least give me 1 gram of that sample? Because we really need sample to do something technologically applicable using some discotic materials. And thank you all for the kind attention.
Okay, thank you very much for a very nice talk and new direction of liquid crystal research in neuromorphic device. Now, open for question. Is there anybody taking my?
Yeah, so very good talk. So just wondering that you have this heterochronin and oxidized or heterochronin when you see under BAM. So you see that one is basically the more fluidic, another one is not fluidic nature. So from there, how do you know that which one is as-on and which one is face-on?
Okay. First of all, we have added it that way. We know that this side will be this material, but anyway, it will mix. But we have also done separately and together. So we know how they behave. And the heterochronin itself is nanowire-like. They can ride upon one another. They're more fluidic. But in the other case, they are so crystalline. They're so, even the elastic modulus had very high value. Even the AFM also showed. So that's why the more fluidic one is the heterochronin. Oxidizole one is more crystalline. And face-on.
Okay.
And so that's by adding that it is face-on, but without that it is edge-on. Very drastic difference in self-assembly, which we didn't expect also.
I see. Okay, thank you.
Okay, there are many questions. That's good.
Very good work and very good challenging that you have taken. The very simple question, the material used by the Japanese scientists for this particular thing, it is a macromolecule or a small molecule?
They don't use molecules, they have used inorganic material.
Yeah, you said it is inorganic. Huh?
The concept is what we want to do, they have used inorganic material.
That's what you said.
But what we want to do, sir, discotic layer, we will use silver, we will have silver filament through discotic layer.
What is their material?
They use some kind of inorganic material, and also they have used some PEO, polyethylene ethylene oxide, some polymers also they have used.
Okay,
Not discotic. Discotic belongs to India.
No, sorry, no. I meant inorganic, but what type of molecule?
This phenomena is possible with inorganic also, and they have done with inorganic.
Thank you.
We want to try with discotic.
Yeah, okay, thank you. Yes, I understand. Thank you.
Something should come out of discotic, that's the point.
Yeah, excellent talk actually. As inorganic chemist, we are also excited. Is there any possibility, because there are some half discoid molecules, like for example, metallomesogens, metal sulfur complexes, together they make a kind of a columnar phase. What is the possibility of using metallomesogens in this kind of work?
So you can try this thing, these are very interesting. Only thing is that the film should be uniform, thickness you have to control.
Okay.
If we really want to look for the quantum behaviors, so don't let it go beyond few nanometers. Then it will be so. It's like, for example, now we have a very good system, two systems, one giving us 1 nanometer, one giving us 4 nanometer. So now we'll take this up with viscotic only.
Okay.
Now for your materials, you can try keeping the thickness a little bit in that regime, so that when you have this filament growing through them, how many steps we can allow them. So let's say in 1 nanometer, 3 atomic layers.
Okay.
In that way, we keep in mind.
Okay.
That's the point.
Thank you. Thank you.
But it will work. It has worked for many materials.
Yeah.
It's inorganic material or organic material? This is at room temperature.
Yeah, actually it is coming out of the precipitation. I didn't go into the detail. We have silver that precipitates. It's like atom, it's breathing. So that comes from the single atom contact. Like we know from the textbooks, like the 2 square by H. But for graphene, it comes 4 square by H. Now we are seeing that this is not exactly 2 square by H is for inorganic. We are seeing something derivative, but the steps are very interesting. It was said before that we can see this behavior only at low temperature.
Yes.
Now we are finding it at room temperature. Now already in this year, so my own collaborator, and for other work I collaborated. So with metrology team, international metrology, they are using this technique to standardize this unit of conductance.
Yes.
Having it, because now the time 1 second is also through quantum system, length 1 meter is also through quantum. Now they are bringing conductance also through quantum. They are redefining the concept of standard value, like standard when time 1 second, standard length 1 meter, standard this having 77 microsecond, means 2 square H.
Very interesting.
It has already come. This year they have published. Sorry.
So at room temperature, this is
At room temperature, we are getting quantum conductance. That's the beauty. At room temperature, because usually people have a feeling that it will only be seen at low temperature. And for semiconductor, it's not like that. We can even have it at room temperature. And very precisely controlled, enabling multi-state memories, many more things.
Okay, I think as you have one very short question. Okay, very quick, short one. Yes.
Yeah, it's not actually a question or a query. I just need your insights or a help. In last slide of your summary, you are saying that forming a thin film of this kind of, liquid crystals, it's important technically. Last line of your summary was, it is technically important forming a thin films of liquid crystals, right? Yeah, but since last couple of months, I'm struggling with that to form a pneumatic liquid crystal thin film on a water. So I just would like to ask you that before forming a thin film of a discotic liquid crystal, whether you have modified your water bath, because when I was...
I think we can take this discussion later.
I have not modified water. It is just this, we have millipore system. So this ultra pure deionized water.
But it is more challenging for discotic liquid crystal to form a film compared to the pneumatic.
No, I think, we can discuss, yes.
And the amphiphilic balance is chemists will answer.
Okay, I have one.
We have designed in such a way.
I have one very quick question. For all this liquid crystal you are using, this is ambipolar DLC you are using?
Not all are ambipolar.
Okay.
So last 2 things we got ambipolar.
And how this role is your filament formation? If you have not ambipolar, we'll discuss later. Yes. Okay.
That gives me symmetric IVs. Yeah. That's important.
Yeah. Okay.
Thank you.
Okay, Dr. Achal Kumar, can you please come? Okay, please take.
Session at 5:10 by online session.
Duplicate.
Completed thoroughly.
Okay, now our own Dr. Rajkumar Gupta. I don't need an introduction, maybe. Professor Rajkumar Gupta from BITS, yes? Okay.
Time is limited.
Yeah.
Audible.
Good afternoon, everyone. I think today Professor Yelamgar has started this, and we are continuing it. And let us see how long we are going to continue with the cholesterol derivative. So, yeah, so I think the credit goes to you, sir. I'm going to talk on interfacial behavior of biological molecules from cholesterol derivative to drug-lipid interaction. So, this is what I'm going to talk. Yeah. My previous two speakers, they have made my life easier. Essentially, they talked about the system on the two-dimensional surface. So when we talk about the system which is 1D confinement, then it is spread into the two-dimensional surface. You have the degree of freedom only in the two-dimensional area or whatever it is. So the discretization of density of states and followed by the change in the properties of the thing. But one important thing here to be noticed here, the system that they spoke about, yeah, is something like this, where we have water surface. On the water surface, you are putting the calculated number of molecules, and you can alter the surface density and then measure the surface pressure. So changing the surface concentration over here of the system, and then seeing the phases. So this is belonging to the class of lyotropic liquid crystal. It shows different phases like this. So Alpana spoke these things, and Vishwanath also spoke on this. So I'll take the liberty of carrying it forward. So these are the two-dimensional system. Now, when you are going for any kind of device application or something, then necessarily what we want is that molecule in a particular state to be transferred to the active area of the device, right? And then we see its possibility for having any kind of sensing application, photovoltaics, or a number of things. So what governs the properties of those devices is the intermolecular separation, or what is the characteristic of each molecules and how they are interacting, what are the separation between them. And this Langmuir logic technique, this is giving you a freedom to alter all these things. So the surface density can be altered, the surface phase can be altered, the number of layers can also be altered by this LB technique. Very interesting system to investigate. Yeah. So some of the biologically important molecules are like fatty acid. So these are, some kind of classical molecules. It can spread on the air-water interface, forms very stable monolayer, and the two-dimensional perspective of this molecule, this system can be investigated thoroughly. So this cholesterol, as Professor Yelamgar was telling, it's a very important biological molecule because it regulates many physiological phenomena. For instance, in case of biological membrane, where we have two bilayer sort of things, and then the presence of this cholesterol, this regulates the localized, the elasticity of the membrane. And then it regulates what is called endocytosis or exocytosis kind of thing. So, so cholesterol is a very important molecule. And of course, cholesterol derivative like steroid hormones, bile acid, and vitamin D, it has biological relevance. Phospholipids and proteins. So these all of them, they form very classical Langmuir monolayer, and Langmuir logic film can be formed out of this. So this is the molecule that I'm going to present over here. So cholesterol moiety over here, and then we have some hydrophilic part over here. In tomorrow's lecture, you will hear what Professor Suresh is going to talk on. This region has some kind of aliphatic linker with carboxylic acid. So that was the work that we have done long back. What we have observed is that in case of pure cholesterol, it directly goes to the condensed phase. Like, the molecules are in the gas phase. The moment it interacts with each other, it directly goes to the condensed phase, very solid and a very rigid film kind of thing that you observe here. It does not go intermediate liquid-like phase where we have a tilt or any other different kind of liquid state of the molecules. So then we thought, can we do some things? Can we give some kind of flexibility to the molecule, retaining the amphibilicity, and then see whether it is going to form some kind of Langmuir monolayer or not? Then we found that yes, it forms a monolayer. It shows not only the liquid condenses but a variety of other phases also. So the linker is important over here. The presence of amphiphilic, the hydrophilic part, that is important here to have different phases exhibited by the cholesterol derivative. So we have taken this kind of molecule, and then you'll see that how it is going to behave at the air-water interface. We'll see that. So now here, so this is what we have observed in terms of surface area, surface pressure, and surface area isotherm here. So now, unlike in case of cholesterol, here we see different phases here, different kind of phases. Right? So there is something called, we have identified these phases. This is called the liquid expanded phase, liquid 1 phase, and liquid 2 phase, things like that, depending on, their elastic modulus here. So what we have done is that we have plotted this elastic modulus and then identified the highest pressure, highest elastic modulus pressure at which we will further investigate that what is happening, what is the orientational state of the molecule in these phases, these three phases here. Okay, so we have deposited at these phases, and okay, so this is the Brewster angle microscopy over here. Nothing great. Maybe Professor Suresh will show you some interesting feature tomorrow's talk. So here we have the usual gas and liquid-like phase, and then this is the collapsed state of the monolayer here. We have done the atomic force microscopy. What we see here is that the film, the thickness of the film is roughly, it's not very different as compared to if you go from one phase to another phase. So this was not conclusively, it was telling that what is the molecular state if the molecule are deposited in these three phases, LE phase, L1 phase, and L2 phase. So we further extended this. We have gone to X-ray reflectivity, and for three different phases, we have found this as a X-ray reflectivity curve here. We have modeled the system, and we found that the thickness of the film is something like this in three different phases: 18.37, 25.16, and 24.16. So what we can conclude here is that the molecules in the low density, high area per molecule, low liquid expanded phase, it is, it is tilted more, and that is why, if you have the tilt, then naturally the thickness of the monolayer is going to go down, right? So this is what it is showing. So at low pressure, we are having the high tilt, and as we increase the pressure, then the tilt is changing, like, it goes from 48 to 28.9. Then we have the electron density profile over here. Hydrophobic, we have some changes over here. Hydrophilic part, relatively less change over here. So, so hydrophobic part relates to the tail of the molecule, where we have some changes if we increase from, the low pressure to the high pressure. So the molecule are getting compact and thickness increases, which means that the tilt of the molecule is simultaneously, it is changing from once we go from one phase to another phase. So there is a tilt variation as we talk about from liquid expanded phase to liquid expanded phase, and liquid 1 phase and liquid 2 phase, there is a change in the tilt of the molecule. Then we investigated that if the molecule are tilted on the surface, two-dimensional surface, so there is a possibility of optical anisotropy in the film. So suppose you have the molecule which is lying onto the surface, if it is perpendicular, then the optical anisotropy in the plane, there will be no optical anisotropy. But if it tilts, then you have different refractive index in different direction, orthogonal direction. So if the monolayer system is tilted on the surface, then there is a way that you can able to quantify the refractive index change with respect to the tilt of the molecule onto the surface. So that's what we have done. We have, so this is our home-built surface plasmon resonance instrument, using which you can able to measure the refractive index at a very high resolution. You can able to measure the tilt of the molecule, which gives rise to the change in the refractive index in the orthogonal direction. So we use this, and what we have found is the following. So this is the anisotropy in the refractive index when it is measured in the orthogonal direction. So low surface pressure, tilt angle is something like 48 degree, and the anisotropy is highest at this particular point. That is quite natural. So the molecule is lying flat here, rod-shaped molecule lying flat here. You have a high degree of anisotropy when it is measured in the orthogonal direction. So if it is tilted, we have, the anisotropy in terms of changing the refractive index in two directions is high, and when we increase the surface pressure, then the tilt angle is decreasing and anisotropy is also decreasing. So this follows the classical theory of the tilt of the molecule, and then the orientation of this cholesterol derivative at the air body. Yeah, so again, this was again a very interesting thing. So what we have done is that we have changed the temperature of the surface, and then we recorded this surface pressure area isotherm over here. So unlike in many other cases, when we increase the temperature, then the isotherm should be expanding, because you are giving the thermal energy to the monolayer. But here in this case, it is condensing, right? So it has something to do with the the van der Waals interaction, the attractive interaction, which is being facilitated with the increasing temperature. We plotted the elastic modulus. Elasticity of the film is also going to increase when we increase the temperature. So this is unlike any other case. Here we are getting the reverse trend here. Okay. So we proposed this model, and we published this in 2024. I think we got it published in Journal of Molecular Electronics. Now, this is another work that we have done. So Langmuir monolayer of dipalmital palmitoyl phosphatidycholine, very difficult to pronounce chemistry name. So we remember this as DPPC, physicists. So the Langmuir monolayer of DPPC in presence of tamoxifen citrate, TAM, a model study of drug-lipid interaction. So here, why we have chosen this system is that, this tamoxifen citrate, TAM, this is a drug molecule for curing cancer. And for prolonged uses of this TAM, people have observed that it leads to some kind of, complexity with the lung. So it affects the lung surfactant by the prolonged use of this particular drug molecule. So is it interacting with the constituent of the lung surfactant? That is what we are going to study in this particular work. So we have taken this is one of the main constituent of the lung surfactant, DPPC. We have not made the system very complicated. We have taken the simple system, the essential constituent of the lung surfactant, DPPC, and then this is the tamoxifen citrate that we have taken and wanted to see how it interacts. That is what our objective here. Then we have formed the surface monolayer of the system with increasing doping of this TAM into the DPPC monolayer. So it starts from here, the classical isotherm of DPPC. We have the coexistence of two phases over here, liquid expanded, liquid condensed phase, and things like that. So the moment and this one is for the TAM, pure TAM. So looking at the isotherm, TAM seems to be, it doesn't form a monolayer, right? It's a area per molecule is very low here. It shows some pressure here, and doesn't look like that it forms a very stable monolayer here, but it affects the DPPC monolayer significantly. The moment you dope it, even with 0.058%, you can see that it completely eradicates the coexistence phase here. There is no coexistence phase. It's completely gone, even in the presence of a small amount of tamoxifen citrate in the DPPC monolayer. So it interacts very enormously with the DPPC monolayer. Okay, so then we increase and then we calculated we have recorded all this surface pressure area isotherm changes very systematically. What we notice is that the change in the elasticity, finally we were talking about the elasticity of the lung surfactant. So we measure the elasticity of the composite system, and then this is how the elasticity decays with the increasing concentration of the tamoxifen in DPPC monolayer. So it increases rapidly, and then after some time, goes decay here. So the presence of very small amount of TAM in the DPPC monolayer, it reduces the elasticity of the liquid condensed phase drastically, and this is how it is going to affect the lung surfactant. So let us see that. Further, we investigated the system using the Brewster angle microscope. This is for the pure DPPC. This is for TAM. So even this is the gas phase. The moment we put the TAM, the contrast changes here. You can see that it's little bright over here. This means that it is not fully going into the surface, or it is not aggregating. Both the possibility we ruled out. So, but how it is presenting at the surface at this moment of time, we don't know. We don't have an answer. So surface pressure 1 millinewton, here the surface pressure is 2 millinewton, and this is the 15 millinewton. We see some granular texture over here. So it is not completely dissolving, it is not forming any aggregate. It is there on the surface at some state. We don't know at this moment of time. So this is the mixture of TAM and DPPC. TAM is 0.25 and DPPC is 0.75, taken at room temperature here. Now again, we transport the film on the substrate, and then we have performed the XRR, and then we have fitted with the model it with the system and model with the theoretical thing, and then we got this kind of trend here. So this is the LB film of DPPC at 5 millinewton liquid expanded phase, and this is the liquid condensed phase. Right? This is again 5 millinewton liquid expanded phase and supposed to be liquid condensed phase. So we see some variation over here. The analysis. So we fit the model, we assume that we have a head group, we have a tail group, and then we fitted the model and we found out the height of the aliphatic chain and the polar head group over here in the presence of TAM and in the absence of TAM here. So this is the pure system here, and this is with the TAM. So we can see that although the pure system, when we increase the pressure, the tail of the DPPC rises and we get the increase in the height, whereas in case of in the presence of TAM, very small minuscule change is happening in the height of the tail. So something is happening at the tail region of this DPPC monolayer incorporated with the TAM molecule here. And in case of polar head group, there is no change. So from this, we come to a conclusion that, okay, TAM is there, it is going, and then it is getting embedded into the tail region of the DPPC. That's what we got to know from here. Then we have taken the electron density map over here. So electron density map also conveys the same thing. So something is happening, not on the head group region, at the tail group region only something is happening, which is happening because of the incorporation of your TAM molecules. And then we proposed a model here. So we have a monolayer of DPPC, and TAM, when it is incorporated, it is going and sitting very nicely with the tail group of this DPPC monolayer. So surfactant, DPPC surfactant, or lung surfactant, if you incorporate a TAM molecule, then most likely it is going to get embedded into the tail region of the bilayer system of your heart, lung surfactant. Yeah. So this manuscript is under preparation. I think I completed my talk. I think yeah. Because the pressure lies to me because I have to see the entire session. So yeah. So my acknowledgement to my students, collaborator, funding agency, ILCS, organizers of the NCLC 2025. Yeah, so this is my group here, very active group. So this was taken yesterday. You can see Professor Suresh. So he is an encouraging member of our group. So we get inspired from him. And these are our working force. All these conferences, whatever is, the facility you are seeing, your hospitality, other things, it is because of all these experiences here.
Okay, so thank you very much. Now, a very quick one question, one or two. Yes.
This mixing of TAM and DPPC that you are mentioning, this kind of things we have seen earlier with HCB and stearic acid, and we did see the appearance of new phases also there. Have you seen anything like that?
So this monolayer system, they are heavily dependent on the nature of the molecules that you are using. So HCB and stearic acid, you say, right?
Yeah, we had seen some new phases come up.
So as Alpana said, that if you change with N to N and some molecule, a minor change in the some part of the molecule, it is going to give you a heavy change in the isotherm or the surface behavior. But here, HCB and stearic acid is completely different molecules. So it's largely dependent on the nature of the molecular interaction.
Professor Gupta, this model you have shown, this TAM is incorporated. Yes. This TAM is going inside, not at the below of this head group.
So it will be with the tail group. It will like to be with the tail group. No, what was the question?
No, my question is that it's not going like this. How you confirm that?
That we don't know. That need further investigation. Maybe synchrotron XRD or something.
Electron density.
At this moment in time, we don't know. It may need further investigation using synchrotron because you need to know a very localized information over there. So using XRR, we could able to tell only surface, electron density is changing at the tail region. So that changing is happening because of the presence of this TAM.
Okay, yes, thank you very much. Now, may I request Professor Yalmagad to give the. Thank you. Speaker. Okay, our next speaker, Professor Amitav Bhattacharya from Sikkim University. So 15 minutes and then 5 minutes question. Thank you.
Yes.
Close this one. It's loaded at this corner. This one. Yes. Yeah, it should be this one. Yeah. Yes. Okay. Okay, good afternoon, everyone. And I begin by thanking the organizers for giving me this opportunity to speak here. I'm going to present a work by my MSc students, Krishna Sharma, Bhumika Sharma, and Anup Regmi. That is, we have done two things. One is to study Solanum virum as a fruit extract, as a surfactant source, and banana bark ash as a green fabric whitener. So this is the group. This is Krishna, this is Bhumika, this is Anup, and this is Pewang, who did some other work. And let us look at it. There is a growing environmental concern over petroleum-based surfactants, and we are looking for safer and natural alternatives. So this time we looked at Solanum virum. It's a plant, a bushy plant that grows in the hills and produces a fruit. This fruit has some medicinal uses, and it is known as, the plant is popularly known as Boxicocada, which would literally mean the thorns of a witch. It has huge thorns, huge and dangerous thorns, which are compared to the thorns of a witch. So we have seen that the aqueous fruit extract reduces surface tension, gives good dirt dispersion, cleaning, and the relative density has also been studied. And we do notice a micelle formation, though we have not studied it in detail. Cleaning increases with increasing concentration and goes more than 63%. So can we say that Solanum virum is a green detergent? We will debate on that. And we have some very preliminary results using banana bark ash. So this is the plant and this is the fruit. So the fruit was collected from a place called Barmiok in Soreng in western Sikkim. The fruit was washed and air dried, and then it was cut into small pieces and then left in good quality water, not millipore, but double distilled water for 24 hours. Then it was filtered with filter paper. The filtrate was used for our experiments. So the surface tension was measured using the Wilhelmy plate technique, the time-honored Wilhelmy plate technique, and we do see that the surface tension dropped from near 70 all the way down to 30. But we ran out of sample and we could not continue further. We will do it this year to find out exactly where the CMC occurs. The foaming ability increases with concentration. It goes almost as high as 9 centimeter, but the foam stability goes up, comes down, goes up. This has to be read. The result is either it is something very new or we are making a mistake. This is dirt dispersion, which is basically the amount of dirt that is retained in the foam. We mix a little bit of dirt in the surfactant solution and shake it, and then we check the amount of dirt that is in the foam by taking a photograph and doing the grayscale analysis. We find a maximum at this point, which is something like 2 into 10 to the power minus 3 gram per cc, which we find from previous experience that it corresponds with the CMC, the critical micellar concentration. We'll look into it later. Cleaning, we see that it starts with 30% at low concentrations. At high concentrations, it touches 63%, which is a good sign because we do it in a very cursory, simple way. We first take clean cloth, take its weight, then we dip it in simulated dirt, dry it, take its weight again, then we clean it in a simple way and take the weight again after drying. And we find that 63% of the dirt is removed then, which is comparable to what we find in the same way from any commercial detergent. So that way we can say that it has promising cleaning effect. Here is how the relative density changes with concentration. Should we expect a linear change in the linear density, in the relative density? That is possible only if the volume remains a constant and the dissolution system is same. But we have always noticed that there is a sharp increase, then there is a decrease, and then all sorts of things happen. This is here the scale is linear, here the scale is logarithmic, and if we do changes, see change in slopes. If we extend this and we see it here, at this concentration, which is something like 0.0000201 gram per cc, there is a change in the slope, which seems to indicate a change in the pattern of dissolution, which could be a kind of CMC. So from here we see, from dirt dispersion, we already saw that the CMC was 1.2 into 10 to the power minus 3 grams per cc. From surface tension, it's sure it's more than 10 to the power minus 2 cc. From relative density, we see something at 1 into 10 to the power minus 2 gram per cc. But if we notice the surface tension curve again carefully, we see there is a dip here. There is a flattening here and a flattening here. This flattening is what is probably coming in the dirt dispersion. So something is happening there, which we are seeing in a big way in the dirt dispersion. Cleaning goes very high, 65%. Foaming is also high at such a low concentration. So we can say that this is definitely a promising candidate as a natural detergent. And after this, the work has to be done, and this fruit is available only in winter. It's not yet available. It will be available only in January or February. So maybe this year we will again start with it. And we have only worked with the fresh fruit. We have to also look whether the fruit can be dried and stored. We have not done that work. That will have to be done this time. And it is a wild fruit. Nobody has cultivated it yet. It grows in all sorts of places, so it has to be collected, brought in and studied. In addition, we started another work. This work is on banana ash. The banana plant, once the bananas have been harvested, is normally the leaves are either used for different purposes or used as fodder. The plant itself, the stem, the outer stem is normally wasted. The inner white part of the stem also has some use. Outer part of it is normally not even eaten by animals. So in some parts they boil it and give it as fodder. But here is one more use which was done in some parts. It is burnt, it is dried, burnt, and ash is used for different purposes. It is used in Africa and Asia for soap making, for caring of wounds. It is used in dental hygiene, and for very alkaline soils, for very acidic soils, it's used as a fertilizer. And it is in some parts of India also, it is used for cleaning utensils, especially brass and bronze utensils, copper utensils. And it has a very alkaline nature, and it has some water soluble minerals. So how was it made? From the outer bark? It's not the correct word. I believe the botanists call it a sheath, the leaf-like things on the stem. So those were separated, left in the sun to dry, and the inner stem, the white thing, or the pith was not used. And this was thoroughly sun-dried and then burnt under controlled conditions to get a consistent fine black ash, which was then filtered using a cloth, fine cloth. And it is used, historically we have found references to it being used as a cleaning for utensils, fabrics, additive in natural soap, dental hygiene, for brushing teeth, soap making, fertilizer, natural toothpaste, and many more things. But what we did was, we took a full plant and then it was sun dried for 7 days, and then it was in an open place in a big stone. It was burnt. And this ash, we are calling it banana bark ash, was the primary thing. So 2 aqueous solutions were prepared. One had 1 gram in 80 ml of water, one had half a gram in 80 ml of water. And these solutions were used. The small pieces of cloth were chosen, first new cloths, then they were first washed thoroughly to remove any traces of starch. Then they were dried, and then they were put in a mixture with mud in it to make them dirty. Then they were cleaned using detergent. Then they were 2 of them were left as it is, 2 were passed through this solution, and 2 were passed through this. And these solutions were stirred a lot to make the uniform dispersion. So 2 were put in the high concentration solution, or A, 2 in low concentration solution, and they were soaked for exactly 5 minutes. Then they were taken out and rinsed thoroughly under running cold water to remove any excess ash. And then they were dried for 24 hours. Then they were, how do we know how white they are? It's not a question of how clean, it's a question of how white they look. So we photograph. And then using high resolution images were made and under uniform lighting conditions. Then using ImageJ software, they were converted to an 8-bit grayscale. And then we took a horizontal line along it, the whole thing, to measure the pixel intensity. A high grayscale value of 255 is white, really white. Anything less than that is less white. And this was used as a reliable measure of whitening effect. And the one unwhitened piece and one whitened piece were placed side by side to compare. So here is the low concentration thing. This line goes like this. This is the untouched cloth, and this is the whitened cloth. And we can see that the whitening here is low. Whiteness is low. This side the whiteness is high. This is the background paper that is white. This is not necessary. So this side we can see that it has got whitened in the low concentration. This is the high concentration. This has also got whitened. To go along this line, there is this side is whiter than this side. And if you cannot see it here in the photograph, believe me, if you see the 2 pieces in hand, you can make out it is white. So with this, we can make our cloth slightly whiter. And so we come to see, the interesting thing we see is the whitening effect is better at low concentration, and it is not so good at high concentration. But of course, we have to try more concentrations and different ways of doing it. So the grayscale values show there is an effective whitening. The difference between concentrations is that low dose is giving a better thing. ImageJ provided a good and reproducible method to quantify visual changes. And the treated samples showed higher whiteness. Whether can we call it better stain removal is a question that we still don't have an answer. So the advantage of this thing is it is compared to the fabric whiteners which we get industrially made, which might actually damage the fabric. This we can more or less believe will not do much damage to the thing. It is cost effective, locally available, safe for the fabric. Quantity required is not much. And the limitation is, the ash concentration for different varieties may be different. Composition, the alkalinity related issues may be there, and ash particles may stay back which may not be able to remove, but we have not faced it. And the scientific validation is still not present. And in conclusion, we report that Solanum virum, or the witch's thorns, the fruit of the plant which has thorns that can be only compared to the weapons of a witch, is giving us a good potential biosurfactant. And banana ash has a whitening effect on cotton fabric. And I have to acknowledge these 2 gentlemen, Mr. Lambodar Jha, who was my teacher, who first told me about this. He passed away some years back. Mr. Gaur Karmakar, who told us about the same ash used to clean brass and copper utensils. And the geology department, because for using their balances, that's what you use it. All of you organizers for inviting me, and thank you all for your attention.
Okay, thank you very much for your talk, Professor Bhattacharya. Yes, so I have a question.
This measuring of intensity value, it depends highly on the the way you have illuminated your system. So illuminated like lightning conditions.
Yes.
So if you change the lightning conditions, the reference will shift. So how did you take care of those things?
What we did was we put them in the same light and took the measurement, and we did it under 3-4 conditions, mostly in daylight. And actually, yes, your question is valid, and we have to do much more before anything comes out from here. So under the standard, we have to define that also. We have to decide. Yes, sir.
In this banana ash studies as a fabric whitener, is there any similar studies in literature where you can compare and so on?
We have not been able to find anything.
No, because at least you can sort of compare and see.
We are looking for such
also
possibilities.
try to quantify and so on.
There are some very limited things, not in the scientific literature, but in old
Even in your
literature,
fabric, studies and so on.
Not. Very nice presentation and very interesting topic. So this banana tree fibers, those are used for making a particular fabric. Yes. Some particular cloth in South probably it's very much. Some places they do it. Banana, yes. Yeah. So originally those are very white, is it? And then they are dyed probably, isn't it? No. This has nothing to do with that. No, I know. This is like you're using burning and then using. But what I'm saying that without like, as it is these banana fibers, which are used for textiles. Yeah. So what is the level of whiteness of that? Not sure. Never actually tried to find out. But mostly they may be colored and maybe bleached. Yeah, they are done later on. But what they actually use as a fiber? I don't know. I've never studied. I didn't try to find out. It's never struck me. Now that you have asked me, I'll try to find out. Okay, thank you.
Okay, I have one quick question, not from banana, other side of your surfactant. So did you measure the polarity of the surfactant, what you are getting, you believe you are getting some, okay. And also you have started, I see your values of surface tension, which is nearly water, like 70 from 72.
Yeah, with very concentration.
Or is it just water? I don't know, it started from.
It is almost, you can say it's almost water if you look at it. Very, it's not water, but mostly water.
Mostly water, okay. Okay, thank you. Yes, Professor Dhar, can you please come? Yeah. Okay, here is the final talk of this session. Dr. Susanto Kumar Naik. I'm not giving to save time, more introduction.
इसको दूसरे पे इसको Yes. Yes. Yes.
So, good afternoon, everyone. At the outset, I should thank the organizer, Professor Gupta and Manjula ma'am, for giving this opportunity and present our work in front of all of you. You know that the last talk of this today talk, so always it will be challenging to give a talk at the end, either interesting or most of you are already bored. Anyway,
There is one more talk.
More interesting. Thank you very much. So, the title of my talk is Exploring Halogen Bonding Supramolecular Liquid Crystalline System for Filtration Property Study. So, let me just introduce myself. I am basically from VNIT Nagpur. VNIT is the renowned person Bharat Ratna Vishwesvaraya Institute, National Institute of Technology, Nagpur. We are the center of India, that is, you can say Orange City, that is 0 mile, that is situated in Nagpur. So I would like to invite all of you, if you are coming here, I am happy to welcome you there. So this is the statue of our VNIT. And moreover, all students, for you, there is opportunity for postdoc position availability. Every year they are just started with good fellowship amount. As well as you have opportunity to do PhD twice a year. So if you are get and net qualified, you will get fellowship. So you are always welcome. Anyway, let's come back to the topic that I am going to talk. So a little bit different way of presentation today that I am going to emphasize. So I will first of all talk about what is non-covalent interaction, then how supramolecular liquid crystalline materials can be obtained. Then mainly I will focus on halogen bonded complexes. Then I will talk about also hydrogen bonded complexes. So let me talk about, as you have already observed, the liquid crystal can be designed two ways. Basically, whatever you have seen so far, you can obtain liquid crystalline materials by making covalent bonding approach. In this way, basically you make covalent bonds. That is where you have a Masonic core part and you have terminal chains. So in this way, you can design different type of moiety, and you can accordingly your desired property can be obtained. But there is also possibility to utilize non-covalent bonding. What is non-covalent bonding? Non-covalent bonding is nothing but it's called supramolecular approach, which gives another tool to build liquid crystal molecules which are more dynamic. So these non-covalent approach have increased the possibility of introducing chemical process such as molecular recognition, molecular assembly into materials. Also, this approach can be recognized as play a key role in the development of new dynamic functional materials. So as you can see here, when molecules form supramolecules, basically these non-covalent interactions are utilized. Basically, like all of you know that van der Waals forces, but there can be differentiated depending on how much energy associated with this. For example, pi-pi stacking, dipole-dipole interactions, or you can say cation-pi interaction or ion-dipole interaction. So this supramolecular assembly can be simply composed of two molecules or a definite number of stoichiometric molecules. And it can be often to denote large complexes composed of indefinite molecules that can be of sphere, rod or sheet-like species. Depending on that, you can design the molecules. For example, these supramolecules are very well known in colloidal molecules, liquid crystals, biomolecular condensate, micelle, liposome, biological membrane. So these supramolecules, before going to supramolecules, I just want to remind you the story that is Gulliver effect. You might have come across the story of Gulliver effect, the person who raised in an island where he found himself is like giant and the people there are surrounding are like teeny particles. But you know that when he woke up, it was bonded, you are fully tied by these teeny peoples, which they were tied so much that he could not move away from them. So that indicate even though these non-covalent interactions which are play a big role with a large number, they can influence the nature of material. So that means in the materials which are available, either they are liquids, solids or liquid crystalline, that will depend on what type of non-covalent interaction they are playing a role in their supramolecular formation. So with this, let me just define you or remind you the hydrogen bond. Hydrogen bonding is nothing but the attractive interaction between hydrogen atom and a highly electronegative atom that is defined by transfer in pure and applied chemistry. And you know that because of this hydrogen bonding, ice formation is happening, and you can get the nice icosaedral structure of snowfall. So let me just define you what is halogen bonding. Halogen bonding is nothing but the evidence of net attractive interaction between an electrophilic region associated with a halogen atom of molecular entity and a nucleophilic region in another or the same molecular entity. That means for a halogen bonding, the atom, at least one atom should be halogen atom. And then of course, it have a nucleophilic regions like nitrogen, oxygen, sulfur or any other atom which are more electron density. So the first halogen bonding was demonstrated by the Husserl's group, where he crystallographically demonstrated that halogen bonding is happening when you take a liquid like dioxane solvent and a liquid like bromine. When they mix together, they form a solid material. That is nothing but the halogen bonding formation of bromine and oxygen with dioxane molecule. And theoretically, it has been established that this halogen bonding tendency is basically influenced by the size of atom. That is, iodine preferred to have better halogen bonding compared to bromine, then chlorine, and then fluorine. So, if you just now if heard the first talk of Professor Elmagoda, that he talked about the one of his collaborator Duncan Bush. This is the person who is first introduced the halogen bonded liquid crystal system, and that is in case of pentafluorobenzene and alkoxy-stilbazole in pyridine. And I am fortunate to have also collaboration with the Duncan Bush. And then of course, then later on, this Duncan Bush with Resnati and Perangelo, they have also demonstrated further several halogen bonding complexes. And I am also fortunate to have postdoc work with them at Italy. So let me just explain you what's driven me to understand the halogen bonding liquid crystal system. When you talk about halogen bonding, the halogen bonding of different type like CX pi or CXO type or CXN type. But if you analyze their literature, mostly the emphasis is CXN type, that driven molecular supramolecular assembly. And particularly in CXN type, they prefer pyridine type of nitrogen interaction. But if you talk about nitrile type of halogen atom, they are very scarce in literature. So keeping in mind this, we thought, okay, why not we will emphasize the nitrile type of halogen bonding. So when you understand in literature, that is using Cambridge structural database, and from the database we found that there are only few reported CNI synthon that talk about supramolecules, and keeping in mind, we try to analyze what type of CNI interaction can be utilized for making halogen bonded supramolecules. So in this context, we have synthesized cyanobiophenyl systems, and we made the complex with perfluorodiiodo molecules, and we have demonstrated using FTIR that there is a shifting in CN stretching frequency, as well as Raman spectra also indicated that there is a halogen bond formation. And when you analyze the liquid crystalline nature, ligand versus complex clearly show there is a difference in the liquid crystalline nature, and the alteration in liquid crystalline nature is observed through DSC as well as polarized optical microscope study. So we try to understand this theoretically by computational analysis, that is MAP analysis or quantum atoms in molecules analysis or non-covalent interaction analysis, where it's clearly showing there is a interaction between iodine and nitrile nitrogen, which is about critical point indicating there is a halogen bonding formation of iodine and nitrogen. And similarly, you can see here the non-covalent interaction clearly showing the weak nature of this halogen bonding in this case observed. So keeping in mind, we thought instead of iodoperfluorobenzene, let us prefer diiodo-tetrafluorobenzene using the same mesogenic molecules, and we have successfully obtained crystal for this halogen bonding complex, and which demonstrated the Ci and nitrile halogen bonding. And further again demonstrated by FTR and Raman analysis study. And then when we analyze their halogen bonding complex, the bulk sample as well as simulated pattern, they exactly match. That indicates that is forming homogeneously halogen bonded complexes in their supramolecules. But however, when we are trying to collaborate with Duncan Bush, he pointed out this type of halogen bonding is very subtle to dissociate. So try to analyze them and evaluate them. Is this halogen bonding really intact after thermotropic analysis or not? Then when we try to do DSC, but DSC analysis is clearly suggesting that they are forming halogen bonding, but however, the halogen bonding is dissociate after heating the sample. So this analysis, we try to understand that this cyanobiophenyl system prefer a dimer type of halogen bonding, there is hydrogen bonding in case of mesogenic ligand, but in halogen bonding, they form only this heteros type of dimer formation with CNI interaction, but they are not liquid crystal. So keeping in mind, okay, we are some extent went straight back, keeping in mind that this halogen bonding is not so much useful for liquid crystal, let's think of a something application level. So keeping in mind, we try to introduce the AJO group. As you know that AJO group will play important role for optical storage devices and various application storage devices. Keeping in mind, we synthesize a series of AJO based molecules and we try to make complex with diiodotetrafluorobenzene. And from theoretical analysis, this is suggesting that this is very prone to have very nucleophilic regions which can interact with the electron region of iodine. And fortunately, again, we can obtain the single crystal for these molecules, which evidence the C111N and iodine interaction. And the strength is so angular, you can see about 167 degree, that is nearly linear, approximately going towards 180 degree. So this evidence the halogen bonding formation. Then further, we try to understand if the bulk samples are also halogen bond complex. That indicate that its simulated pattern of single crystal data is exactly matching same as the bulk sample, that clearly telling that they are homogeneous and halogen bond complex is happening. So further we have carried out different computational analysis to support the evidence of halogen bond formation, and we try to understand through TGA what is happening. But we see that why this dissociation is happening. You can see here, when you go beyond 200 degree, there is a loss of 34%. That clearly indicate diiodotetrafluorobenzene try to dissociate after high temperature. So these indicate that the halogen bonding complex is well established, but however, the liquid crystalline nature is unstable at high temperature. But when you try to understand the photoisolation study, that these halogen bonding complexes are so better photoresponsive compared to the mesogenic group, and they are fast, around 4 minutes faster than this with respect to ligand. So keeping in mind, we have also analyzed this liquid crystalline complex of alkoxy azobenzoyl derivatives of polymer, lateral polymer with 1,4-diiotetrafluorobenzene. And we have already published in molecular liquids, and we have established further this CNI halogen bonding happening in case of this molecular complex. Further we established through FTIR and Raman spectroscopy, and then again we have analyzed through...
Okay, you got 3 minutes.
Okay. Analyzed through this theoretical analysis, and further we have analyzed through DSC and TGA, which differentiate the importance of this. However, again it is one drawback that halogen bonding start dissociating when you go higher temperature. So this is one of the drawbacks, keeping in mind we have to see. And however, there are very interesting photoisomerized products are obtained, and in this context again further we try to prepare bent core type, star type molecules, and finally we successfully obtain a bent core type of molecules. Unfortunately again they are not liquid crystalline, but they are interesting photoisomerized product. So keeping in mind last part of my talk, so halogen bonding is making us more frustrated. So keeping in mind, we thought, okay, let's go for say hydrogen bonding. So when we try to analyze the hydrogen bonding, we intentionally took a molecules which is very small one with fluorinated substitution, and we could successfully obtain these hydrogen bonded liquid crystals. That is well established by this theoretical analysis as well as crystalline study of single crystal study, and we can see that the liquid crystalline nature. And here I want to emphasize that the ligand mesogenic is not liquid crystal, but the hydrogen bonding lead to liquid crystalline nature, and they are photoisomerized products. And you can see here at the liquid crystalline state, by when you apply the photons UV, then it goes to liquid crystalline to isotropic states, and when UV is off, you can come back to the liquid crystalline states. So with this, let me summarize. And we have successfully obtained trimeric, CNI and bent shape pyridine nitrogen halogen bond formation, which were established by characterization techniques. And these halogen bonded complex though did not show liquid crystalline, but interestingly they are very good photoresponsive in nature, and they are very fast photoresponsive compared to their mesogenic precursors. And further they are analyzed through theoretical analysis. With this, let me also emphasize that we are not only working on supramolecular, we are also working on a covalent approach. So two of my students are presenting poster number 12 and 30, where you can check out what type of work we are doing on based on covalent approach liquid crystal system. And with this, I would like to thank the most of the work is done by Jyoti Sarup Thakur and Omkar and Kapil Ingle. And I would like to thank the Indian Liquid Crystal Society for giving this opportunity to present. As well as I would like to thank the project SCRB DST, as well as MOE Star project and DSC Feast for providing the powder study facility in our department. Of course, I would like to thank my collaborators, particularly here in the society, Srinivasulu and Santunpal for their in other projects that we are working on with them. And I would like to thank all my motivated and dedicated students working behind this background. Thank you very much for your kind attention.
Thank you, excellent talk. Yes, so now, yes.
When you shine UV light?
Yes, halogen bonding intact.
Intact, okay.
But in some cases that I showed, halogen with high temperature, liquid crystalline is lost.
It's not. Thank you.
Okay, so as we are running out of time, so maybe we can conclude and there will be question. Professor Ramakrishna Rao, can you come and deliver? Thank you.
Yeah, thanks to Chair Professor Sushant for keeping the time and saving our life. So now we have a sponsored talk here. The sponsorship is from Bureau of Indian Standard, and today we have Dr. Harish Dwivedi. Let him join, then I will introduce him, and then we'll start this sponsored talk. Please stay here.
नहीं मेरे पास लिंक तो नहीं है नहीं वो तो आपके पास ही आपकी मेल खोल के वैसे करना पड़ेगा एक मिनट बस कैमरा सेट कर देते हैं आप बताएंगे
बस 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 सेट एक ना नीचे कर दीजिए एक मिनट हाँ सर एक लॉग इन करते हैं ओके
कैमरा सेट है क्लोज कर दो आप इसको कैमरा
लॉग इन करना पड़ेगा ना
क्रोम पे NCLC
जीमेल
नहीं क्रोम पे खोल लेते आपने क्रोम नहीं खोला शायद
क्रोम है क्या इसमें?
क्रोम है ना इसमें, इसको क्लोज कर दीजिए आप। एक बार ऊपर से म्यूट कर देता हूँ।
एक मिनट पहले रुक जाइए इस पर।
इसको ओके नहीं करना, इसको ओके नहीं करना। नो थैंक्स।
माइक्रोफोन निकालना। ये कैमरा वही हो स्पीकर।
कैमरा को थोड़ा एडजस्ट कीजिए ताकि हाँ सर बताइए कौन सा दिखाना है। ये चाहिए ना? नहीं, एक रो आएगा। हाँ एक ही रो आएगा। और जैसा जो
ये वाला
ये वाला यहाँ पे बढ़िए।
ये वाला रोक।
Please don't mind checking this. बोलो
सही रन कर ले। एक बार बैठ जाए। एडमिट।
टेस्टिंग और बाकी है सर साउंड की, वो जो बोलेंगे इस पे आ जाए, क्योंकि मैंने ऊपर से म्यूट कर रखा है, तो मैं अनम्यूट कर देता हूँ एक सेकेंड। वो यहाँ से
इनको इन कर लेते हैं।
एडमिट ऑल।
क्या करना आपको?
3 डॉट पे का वॉल्यूम नहीं क्या आएगा? सेट चेक
चेक चेक चेक चेक।
USB P&P साउंड डिवाइस वही होगा क्या? USB से तो नहीं लेगा ये। हाँ नीचे वाला ही चेक। हाँ अब ले।
हेलो।
मैं ऊपर से अनम्यूट कर देता हूँ बस आवाज उसमें।
इसको स्क्रीन पर डालूँ।
Dr. Harish, can you hear us? Dr. Harish, can you hear us? Hello? Hello? Dr. Harish, can you hear us? Can you hear us? We are not able to hear you. We are not able to hear you. कहाँ गए? आवाज नहीं आ रही है वहां से।
यहाँ पे डाल के रख देंगे। ये काम भी इसको in इसमें डालो ना, इसका वो नहीं है क्या, डायरेक्ट जैक नहीं है।
यहाँ पे होगा, मुझे भी वहाँ चाहिए, वहाँ पे मनोहर जी होंगे, 1 मिनट। मनोहर जी, हाँ आ रहा हूँ, आ रहा हूँ। ठीक है, यहाँ से
Hello. Yeah, now you are audible now. Yeah. Is it clear? Yeah, it is clear now. So put in the presentation mode. You just. Yeah, Hariji, you can put this in the presentation mode.
I am not able to listen very clearly. There is some echo from your side. But if you are able to listen to me,
Yes,
I can start.
I can able to listen to you. We are able to listen to you.
So I can start. Can I start?
So let me introduce, and then after that you start.
Okay.
Yeah. So Bureau of Indian Standard is a MOU partner of BITS Pilani campus. They are very active in collaborating with BITS Pilani, and they have sponsored us in several avenues, starting from the student exchange, faculty exchange, sponsoring the project proposals, and various other things. So, yeah, so when I reached to them regarding this workshop, they took it in a very, sporting mode, and they wholeheartedly, they are sponsoring, financially to this particular conference here. I'm Paul's here. Okay. Yeah. So, this talk is BIS sponsored talk, and we have BIS representative, Professor Harish K. Dwivedi. He is the scientist turned industry professional, later an educationalist, and now a freelancer mentor with over 45 years of experience in research, technology development, and education. He has served as a senior scientist at Siri Pilani, R&D head for the flat plasma TV, and senior consultant at Samtel Group, and director at the MIT School of Science, Lucknow, as well as the professor and business incubator in charge in MUIT, Lucknow. Since 2021, he has been mentoring students, startups, researchers, and innovators, and currently leads a 50 startup group called the Human IST, offering guidance selflessly. So with this brief introduction, I invite Dr. Harish Dwivedi to make the presentation. Dr. Sir,
okay.
Yeah, go ahead. So put in the presentation mode, your PPT in the presentation mode.
I am not able to hear properly.
PPT in presentation mode. PPT in presentation.
Yeah. So I am sharing the screen. Is it okay, or you want to share from your side?
No, it is fine. You can go ahead. It is fine.
Okay, okay. Namaskar to everybody. While I am presenting this discussion to you all, I am finding one small problem because I am not able to listen to you very clearly. And this is the place where BIS has to enter. This is one example actually, because when I worked at CSIR and then from industry, I went to BIS to help them in managing the standards of electronics displays. I found that measurement standards for some of the components or displays were not uniform. And this is one example that if BIS has to prepare a module, a standards for interfacing Google Meet with an audience in physical form, then what are the measurements it has to do so that communication is as per standards? So this is just an example I'm giving. So now I will tell my story actually. See, when I started working with BIS, I started suggesting them that they should go to the research institutions, because till that time there was a perception that BIS has only a small role of helping the consumers and forcing, I am literally using the word forcing the industry to follow its own standards. That was the perception in mind. But 3-4 years back, when we started discussing with BIS, then the first point which came to their mind was that they should start interaction with researchers, institutions, and the industry for innovation also. Although the mandate for BIS is not innovation, but what we learned from the industry was that in order to maintain standards and in order to safeguard the interest of Indian manufacturers, you have to optimize the Indian products in such a way that these products match with the requirements of Indian environment. And so they started discussing with their industry and how to design measurement methods, standards. So normally what BIS is that they take standards from IEC, that is International Electrotechnical Corporation, consortium, which is based in Japan, and they adopt the standards from IEC, and then they get it voted through the Indian industry. But since India does not have any manufacturing base for LCD or for very critical high technology products, so most of the standards are from IEC only. But once the industry started manufacturing or at least assembling, they found that some of the components or sub-assemblies of the assemblers or of the Indian industry can be optimized for Indian needs, and that is where the innovation started. So what we found out was that when we went to some institutions with the Indian assembly units, like for example in our case LCD, and we found that the front panel of the LCD is not as per requirement, or it is not as per IEC standards. So then CGCRI, there is an institute in Calcutta, Central Glass and Ceramic Research Institute. They helped in changing the color gamut of the front screen of the LCD, and this helped in creating a patent also. So this was an example of how BIS can interact with research organizations and industry in not only in maintaining the standards, but also in innovation at component level. So this was our starting point of interaction with BIS. Now, when we talk about the BIS role in LCD, then I just listed down 4 or 5 aspects. One is Indian manufacturers. But we all know that there are no Indian manufacturers for LCD, liquid crystal display. There are no Indian manufacturers. Of course, there are assemblers. So whatever LCD panels we see, either in the form of a monitor or in the form of a display television or in the form of a helmet-mounted display even, or defense or aerospace applications, some assemblers are there. So what they do is they import the LCD module, they import different components, and then they assemble it with, of course, some value addition in the electronic components. So we will discuss these aspects one by one. So let's go to the second slide. Yeah, just a moment. Yeah, can you see this? Just a moment.
You have to share the entire desktop.
Okay.
And then make it a presentable form. If you share,
I have shared the.
And now it is changing.
I have shared this presentation with you also. Yeah.
It is visible now. It is visible now. You can make
Okay.
presentation in this.
So I have shared the presentation with you also. Maybe you can share from your side. Then I will close this screen.
So I think it will be difficult because the same computer is showing your things.
Okay. 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 So are you able to see this LCD component setup?
You can zoom a little bit on the bottom right. There is a plus sign, so you can press that a little bit. Bottom right.
Yeah. Okay. I can.
It has become too big. Make it a little small.
Okay.
This is fine. I think this is fine. You can go ahead.
Yeah. Okay. Yeah. So this is also an experience for me. So anyway, so when we look at this LCD, you can consider it as a LCD TV or LCD monitor. See, as you can see, there are a lot of components. The first is the front glass, and then you have different components. But finally, I will just talk about the different coatings and different glass sheets. Then you have polarizer, then TFT, and then you have the electronic circuits, the printed circuit boards. Then you have the backlight and the final structure to to package it. Now, when we talk of this LCD, then the liquid crystal part is only at this place. But when we talk of this LCD, then you have so many components, maybe 9 or 10 sheets, and each sheet has its own standards. So what BIS is doing is that when it talks to the assembler, it gives them specifications or measuring methods to optimize their production line or their standards line in accordance with the measurement methods shared by BIS. But BIS is getting it from IEC. So, assembler, the Indian assembler has a chance to do innovations or do developments of the front glass on its own through Indian industries, and if they have certain issues in its performance, then, but if they are happy with the Indian consumer, or if the Indian consumer is happy with the performance of the Indian glass sheet, then the Indian assembler has the advantage of Indianizing the measurement methods also to convince the BIS that IEC measuring methods are no longer valid for the Indian consumer. So this is one example of how BIS is helping the Indian assembler or Indian industry in Indianizing the measurement methods for different components of the LCD module. Now, this is one example. Then similarly, I have one story about the viewing angle. Normally, the viewing angle is considered to be 120 degrees from the one end to another end. Now, but to make it the view angle so large, one has to work with the polarizer, which has a narrow angle of 45 degrees, something like that. So the optics of the front glass has to be modified. So if the Indian industry works with BIS with the help of Indian researchers, then they can work on the optics to improve the viewing angle. And through this, the cost reduction will also be taking place. So I'm just giving an example of how BIS can work with the researchers and the industry for improving the quality of the Indian products. Now we come to the next slide. Just a moment. Yeah. So this is just example of, because LCD is not just the LCD monitor or LCD TV. LCD come in different forms and for different applications. For example, we have the rugged LCD monitors for use in the mining industry or different industries which require high level of ruggedness. So the parameters which are to be used by the common consumer is not valid for the industry-based user. And so the Indian industry has to work on the ruggedness part. And one example for this is the multifunctional display in Sukhoi 30 aircraft. And since I was associated with the Samtel avionics systems after CD Pilani, and there I found that the normal LCD can work only up to 60% humidity, and maximum up to minus 15 degrees centigrade temperature minimum, and maximum 40 degrees centigrade. But the airworthiness MFDs, multifunctional displays, have to work to the minimum level of minus 30 degrees centigrade when they are airborne, and also they have to work up to plus 60 degrees centigrade. So these were the two extremes. Now, the company with which I was working, they had to completely change the structure, internal structure of the LCD monitor to make it so rugged that even the backlight was to be changed to another level and to LED version, so that this can be used at minus 30 degrees centigrade at the lower temperature, and then plus 60 degrees centigrade through a heating arrangement, because the aircraft has to bear such extremes of temperature. So this is one example of how the LCD monitor can be converted into a multifunctional display for use in aircraft. And now the Sukhoi 30, which is being assembled at Hindustan Aeronautics Limited, is using the Indian multifunctional display. So these are the examples that how the Indian standards come into in innovation, research, and make in India performance. Similarly, I will give another example of a this helmet-mounted display. Now, earlier, some 10 years back, the helmet-mounted displays were used to be from CRT. You know, CRT is still the most rugged display system when you compare with the LCD or LED. But the power consumption was much more higher. And because of the power consumption, the load on the helmet for the pilot was much higher. So in order to reduce the weight of the helmet, and the heat generated was also to be reduced, the LCD was brought into picture. And then the Indian industry was assigned a task to develop the helmet-mounted display in collaboration with, of course, international manufacturers. So wherever the Indian component was tried in the helmet-mounted display, the BIS standards, the BIS specifications started playing a role into it. So that is how the BIS plays a role into different aspects of LCD manufacturing or LCD performance. Now I will just touch upon some small parameters which come into play. So just I will just share with you another slide. Yeah. Yeah. These are the very basic parameters. Although there will be more, 15, 16 more parameters, but I'm just giving some examples actually. Like transmittance, the quality of the glass. In our case, front glass had some color tinge because of addition of boron. So because of that, the transmittance was reduced. So the performance of LCD monitor got down. So the Indian manufacturer, in our case, it was CTCRI Calcutta. They had to develop a formula for improving the transmittance of the front glass so that the light from the backlight could be transmitted at high efficiency. So this is one parameter. Similarly, response time is another parameter which is very critical. And if it is a passive matrix LCD, then it will be slower. Active matrix, this LCD, it will be higher on the higher side. And then the polarizing speed will also play a role. So those who are working on liquid crystals and its polarizing speed, then they can also think of improving the response time, which will finally help into the improved response time of the LCD. That's it. That is how the result at the research level comes to the product level. So I'm just giving examples. The other parameters are, of course, viewing angle, and then weight, the contrast issue, measurement methods for standardization, color gamut, durability, and then other mechanical features. So all these are defined by BIS with the help of IEC. So this is how we play. Now I will move on to the next slide. Yeah. Yeah, this is just a small example of how BIS intervened in helping the Indian industry. See, this is, and I experienced this case, so I am sharing it here. See, the first case is the strength of the glass on the front screen. See, normally, as per the international standards, the front glass has to have a strength so that a vibration of 50 G should not break the glass. But the Indian glass could not withstand the international standards. And so the international products got the entry into the Indian market. So this was a challenge for the Indian manufacturer, either to improve the quality of the glass or to modify the measurement method and recommend it to BIS to lower the standards. And finally, what happened was that the Indian manufacturer was able to manage with the Bureau of Indian Standards to lower the test standards to suit to the Indian consumers. And that is how the Indian front glass started being assembled in the LCD monitor. Second example was the role of assemblers, which I just mentioned about. And the third is a very interesting case of LCD, LED, TV, Samsung story. See, in 2008, the LCD TV was already there from 2005 or 2004. And at that time, plasma TV was also there. But the backlight of the LCD TV used the CFL, compact fluorescent lamps, for backlighting. Now, because of the compact fluorescent lamps, the thickness of the LCD monitor used to be around 1 inch to 2 inch. Now, what happened is that in 2008, LED backlight was now available. But Samsung had to give a different name. So what they did was that they started telling that LED TV. They did not mention LCD TV with LED backlight. They mentioned LED TV. And the whole world, even Panasonic, LG, and other companies, they were stunned with such a discovery because they knew that LED TV cannot be made for home viewing or for close range viewing. So they started digging into it and they found that the Samsung TV was not a LED TV, it was a LCD TV, but with LED backlight. And because of LED backlight, the thickness of the LCD TV reduced from 1.5 inches to around half inches. And this started setting up a new standards. But now in India also, backlight industry is now in full swing. In fact, India has got almost self-reliance into backlighting manufacturing and assembly. So these were just small examples of how BIS is helping the Indian industry. Maybe if you have some question, you can ask. I just prepared it quickly to put to your needs. So thank you so much. If you have some questions, you can ask.
That you have, we would like to hear you more sometime later, but it's a very informative talk that you have given today to this LC community. So you have to come here. So there are a couple of questions. There are some questions. I request audience, they can come here near to the dais and then they ask the question.
Maybe you can give a phone to them. It will be easier to listen. Anyway, you can ask. Yeah.
Professor Dwivedi, my question is that if you are not manufacturing, we are not manufacturing LCD panel, then how can we control? They have their own standards.
Yeah, you are very right. So that is why there is a need to start manufacturing. Of course, I understand that LCD now, no businessman, no industry will put their money into LCD because now it has become a mature technology.
Right.
Right. So unless you start investing for a large plant, large volume plant.
Okay, I agree with you. I agree.
Yeah, so that this cannot be done, and Samsung is already doing it with mobiles at different places.
Okay, thank you very much.
So are there any questions? So Dr. Harris, now there are no more questions. So I sincerely thank you and BIS for taking part in this conference and convey my thanks to the other officials of the BIS.
Thank you
very much.
Thank you. Yeah. So I close this here. Thank you.